state that one of the topics of this talk is also about fiction. There is a fiction out there that Aristotle would have been the one to first say that the gecko walks upside down, but in reality, he didn't mean that. He was not talking in that context. I mean, he was completely taken out of context. Okay, and Aristotle would not have spoken about the forces between atoms and using the gecko as an example because Aristotle was against the atomistic theory. So it's completely out of context in case you come across that mention. But more recently, people have wondered, how the gecko does it. How does the gecko do that? So there is an article by Autumn and colleagues. This one was in the American Scientist, but of course the original contributions came earlier, in which they analyzed whether this was due to atmospheric pressure, again, whether by hooks or glue or some kind of other liquid. And eventually they discovered most of the force that allows the particular gecko in question to perform this feat is due to the Casimir effect. And you can see here a sign of the times is when The Economist talks about the Casimir effect, because the Casimir effect wouldn't ordinarily have attracted the attention of a magazine called The Economist, but in reality, at some point it did. And so here you can see a drum set in which I suppose the photographer, the artist, meant to represent here is that you can make one plate vibrate although you are in a vacuum. Now, usually a drum set would require air to vibrate. Okay, and well, this one doesn't, because the Casimir force is the vector, if you want, the carrier of the force. The reason that the economists became interested in that is that, of course, at some point, DARPA wanted to know, well, this force is creating problems, because as Feynman noticed as early as 1959, stiction is a problem. So parts that adhere to each other will not come apart. So in a microelectromechanical system, if two parts stick, you can consider the device fail. So DARPA wanted to know at some point in the early 21st century, how can we undo stiction? How can we avoid it? I think even more important, from my perspective, is how can we use this force instead of just trying to avoid it? Amusingly, again, in pursuing the idea that, let's not forget, this is a weak force, remember? It's a tiny force. Remember, it's too weak to command great attention. And here we have a graduate student at Stanford climbing up sheer glass by only using Casimir forces. This actually is better than Tom Cruise in Mission Impossible when he climbs up the skyscraper in Dubai, in the famous scene in which he is almost falling off the building because the gloves run out of battery, remember? Well, here, the uncertainty principle of quantum mechanics never runs out, and this student could go all the way up without any problem because no batteries are required. So the force is neither strong nor weak, and no batteries are necessary. So I think that this particular implementation use, if you want, you can see that I've been trying to kind of give you an idea, an abstract of how Casimir forces have evolved from a philosophical concept to a market concept. So understandably, these particular glues, we can call them, although they're not chemical, are called Gecko glues. And they are becoming, probably, I would argue, one of the first products enabled by nanotechnology meeting with Casimir forces. The first product, I would say, was indeed the Johansen blocks. The Johansen blocks would have been impossible without Casimir forces. So here we have such a manifestation. Now, I would like to say that one of the most difficult things to do, and in this sense, this may explain why people talk about Casimir forces as being weak, is the fact that these forces are not weak, but they are certainly short range. So I will talk a lot about this experiment, which is one of the ones I like the best. There are several experiments that have proven the existence of Casimir forces. Remember that Casimir was a theorist, and I would like to remind you that Casimir, as we will discuss later, in 1948 was trying to explain the fact that forces in colloidal applications, if you want, didn't appear to respond as expected from the ordinary London force, van der Waals forces in the unretarded regime. But van der Waals, of course, was long dead. London didn't measure anything. He was a theorist. Casimir was a theorist. So the measurement of Casimir forces between macroscopic objects, especially in the retarded regime, was a challenge to experimental physics for decades. And there were many attempts. I will show some of these gadgets and devices over, in the course of the presentation. But the one that I find the most beautiful, and for me, it remains the most elegant today, is the one by Hunklinger. And I have spoken to him. I am preparing an article on the history of their experiment for other reasons that I will describe also in this presentation. I've spoken also to Walter Arnold, that is the last author. They were part of a team led by Dransfeld in Berlin in the 1960s and 70s. They published only 2 refereed papers on this subject, but implemented a very, very fascinating way to measure the Casimir force. So here, this is an article that I wrote for the American Scientist in 2014. So the art is mine, but the idea is theirs. Hunklinger, Siegfried, told me that he was given by Dransfeld as a PhD dissertation the goal to measure the Casimir force the way that he could. At the time, this had been done by Deryagian by means of basically scales. So you take a balance and you measure the force between 2 surfaces in a static manner by using a scale in feedback mode. Deryagian succeeded, but honestly, his error was about 100%. I mean, it was not enough to really confirm the expectations about the Casimir force behavior as a function of distance. Hunklinger told me that at some point he basically took his own Deryagian setup and threw it into the trash. And he went back to the drawing board with a new idea. And the idea was to use a microphone, something that I found genial, really. I mean, this is, in my view, a Nobel Prize caliber idea, although he hasn't yet got the Nobel Prize, but he should, really. This entire group should get it, I believe. He basically had the idea of epoxying, and keep in mind all this was before microtechnology, before digital technologies. Okay, so we're talking about 1969 or so. And he basically epoxied a small glass disc to the membrane of a microphone. And then he assembled a spherical lens facing that disc. This lens, as you can see in the far left, attracts the small disc attached to the membrane of the microphone. Then, by taking the lens and by making it vibrate up and down, he led the microphone into resonance. Obviously, all this was done in a vacuum, so that you would have a very high Q, okay, a high quality factor. But basically, what he was trying to do, he was making a microphone respond to the quantum vacuum in the absence of any air. And this is absolutely beautiful, I think, as a way to detect this Casimir force in a dynamic fashion. In other words, he played a trick that is a classic in experimental physics by taking a static object and transforming it into a dynamical signal, which of course allows you to filter out noise, all kinds of things like that. So this was a genial approach, I think. But he went further. Walter Arnold told me, I also interviewed him, that at some point what they were trying to do was to measure the Casimir effect between different boundaries made of different materials. As I will describe later, there isn't just one equation for the Casimir force. So for instance, my students in the past semester have seen the Casimir force between ideal boundaries, but that is, the simplest case. In reality, we are not dealing ever with perfect boundaries. Casimir dealt with the perfect boundaries because that's the simplest thing to do. But if you got real boundaries, well, then it's not so simple. We will talk about the Lifshitz theory in this presentation. So what Hunklinger and colleagues were trying to do was to measure the Casimir effect between real boundaries, not just between two ideal boundaries that don't exist. So what they did then was to basically change the substance that was interacting with this small disk attached to the microphone. So maybe they had, silica, and they had silicon and other gold. They deposited gold at some point on this lens. Now, at some point, they decided to deposit a dot of amorphous silicon on the facing part of the convex, on the if you want, the apex of the convex lens that is facing the disk attached to the microphone. Now, I don't know if Walter Arnold really, means this, but he told me that at some point, as he was making the measurements, graduate students spend long hours in the lab, daytime and nighttime hours. He realized that when the neon lights in the room were on, the measurements that he was receiving for the Casimir force between these two objects was different than when the lights were off. And so that led the group to decide to aim a powerful white light into the back of the convex lens, as I described here in the center of the figure. And they discovered that the Casimir force was dependent on illumination. So if you back illuminate the semiconductor, you're going to get a different force than if you do it in the condition that is at the far right. I believe that this is one of the most remarkable discoveries in the entire history of this field, because this means that we can modulate Casimir forces in time. And I believe that this is probably the first time that anybody even thought about doing it. As I will describe later, in a way, this is simple to understand. If you back illuminate a semiconductor, you're simply creating pairs of carriers, charge carriers, and the change in the charge carrier number density causes a new contribution to the dielectric function. So in other words, the optical properties of the material change. And because the Casimir force depends on the dielectric function of the materials, you expect this force to change. So, hey, after the fact, post facto, you should have expected this. So they did a beautiful experiment in which they measured this, the Casimir force in the presence of illumination and in the absence of illumination. Now, obviously, as anybody here is thinking, you need to be very careful, because you need to, of course, make sure that the radiation pressure on the back of the lens is not causing, spurious signals. You need to make sure that the radiation re-emitted by the semiconductor is not causing a force acting on the small disk below. So there is all kinds of things that need to be ruled out, thermal effects fundamentally, which they considered. Now, I will say that the discovery was great. The only problem that remains open with the results of the, let's call it the Hunklinger, Geiselman, Arnold Dransfeld experiment, is that the effect should have been larger when you get close, when the two boundaries get closer, whereas it got larger when the two boundaries go farther. And that is kind of confusing, really shouldn't have been like that. But it is believed that by the group that, you see, one of the great challenges of these experiments is the presence of spurious charges on the two boundaries. And because electromagnetic forces are always larger than anything, in fact, I would say that any force other than the Casimir force is larger than the Casimir force if that force is present, other than gravitation. So fundamentally, when you try to go at a large distance, which is when you would like to see the retarded Casimir effect, at that point, the presence of these charges is, dominant. So that was a problem that they had. However, the same experiment was repeated with the atomic force microphone by Mohideen and others, and they confirmed in full the expectations from theory. So I would say that if one has to be fair, the merit historically still belongs to Hunklinger and others. Now, I know that one of the reasons that I eventually became involved in the Casimir Effect was not all that. I was looking for technological applications. At the time, I was working in the Jet Propulsion Laboratory when I became aware of all these things. And as you may know, we were involved in a project called the Interstellar probe, which was a challenge thrown at JPL from headquarters. What would it take to throw a metric ton at Alpha Centauri? I mean, can we send spacecraft to other solar systems? And this was a remarkable challenge. That's how I met Robert Forward, by the way, and others eventually that I had the opportunity to meet, including Tim here, because we all kind of congregated around this challenge of interstellar exploration. So the reason that I became interested in that is that when we were discussing the interstellar probe, there are two strategies that we can follow. Keep in mind, we are not talking about human travel here. We are talking about sending anything, no matter how small, to a nearby solar system. So one of the strategies by making the spacecraft as small as possible. So in order to do that, you need to make the subsystems as low mass as possible. Now we know that this is the way to go because nowadays we call it the star chip, right? That's what Stephen Hawking also eventually endorsed. A microchip by radiation pressure. So it was the correct way to go. One of the things to do that you need to do if you want to do that is to miniaturize everything to a level that becomes unthinkable. So for instance, can we have energy storage with densities that are much higher than we have today? Can we have nanorobotics, computation, everything on a scale that is maybe 1,000 times smaller in length and larger in density? So one of my contributions to the field that I believe has stood the test of time is the idea of using the discovery by Arnold and others to design an engine cycle in which we have, this will be the bottom 4 A, B, C, D planes. We start with the two interacting surfaces at a large distance. We illuminate it. We allow these two boundaries to get closer. We let the semiconductor decay. That causes the semiconductor to go back to its original unexcited, if you want, state, and then we pull it away. So this creates this engine cycle that you can see here in the far left. I guess that the A is missing. And fundamentally, if the other side, the opposing side of the illuminated lens is charged by a positive charge, and there is a capacitor on the other side, you can use this system to convert the energy that the system has converted to increase the Casimir force field into electrostatic forces. For instance, you can recharge a battery this way. So this is very important because on the nanoscale, when you're starting to talk about nanotubes, for instance, you cannot have wires and ordinary circuits. So you need to think of another way to convert energy into mechanical energy. That's what I was looking for. Now, eventually, this invention that was patented, I got about a dozen patents worldwide, the United States, Europe, Japan, and Israel, became famous for another reason that wasn't really meant to be, but because of the limitations of the theory, I believe. if the two boundaries are very close, and I mean closer than a nanometer, you have the appearance of energy extraction from the zero point field. I almost took it as a joke at the time, but that idea took on a life of its own. And I want to specify clearly that at the time I didn't think that was going to be the biggest thing to come out of this. What I wanted was a nano device that could be actuated and that could store energy by using the Casimir force. I wasn't thinking about creating energy. And I would like to stress still today we have no experiment that does that. It remains an open question, but as I will describe later, in a way, I am more interested in pushing forward towards devices that can actually use this aspect of the invention that is absolutely uncontroversial, as opposed to more controversial questions such as 0-point energy extraction became to be called. There is a connection from the thermodynamical standpoint with the typical four-stroke reciprocating engine that I represented up here, up on top. However, of course, in a PV diagram orbits in the opposite direction, because in a four-stroke reciprocating engine, the gas pressure is, if you want, repulsive, whereas the Casimir force in this case is attractive. But the concept is the same. So, because I see the time is going by, I will probably do what Tim says and take a few more minutes for taking questions. And I hope that it is of interest, because I want you to know that a lot of the things you are seeing have not been seen before. This is a lot of the background history of what happened. With the courtesy of Bunker and Arnold, I wanted to show you some of the original photographs of the device, the instrumentation that they were using. There is an article by me that is upcoming to appear on this issue. And the whole instrumentation, unfortunately, no longer exists. There was a fire at the TU, the Technical Institute in Berlin, where this happened. And from what I understand, the fire involved radioactive materials, so they had to, when the firefighters came, they had to throw everything away, basically, so there isn't anything left. This diagram on the right is nothing but the original notes by Arnold that were eventually published in the Physical Review B. Now, let's rewind the movie so that we understand where we are. First of all, I want to stress the relationship between quantum theory and the existence of Casimir forces, because this is a big, huge issue that again goes under the heading of fiction. You're going to hear people repeat obsessively that the Casimir effect is a manifestation of the quantization of the electromagnetic field. Well, I have no doubt to tell you that I believe fully that the electromagnetic field is quantized. No doubt about it. However, the Casimir effect is not a tool to prove that anything is that the field is quantized. People will reply to this by saying that the Casimir force and the van der Waals force have an H bar in the beginning. That proves that if H bar goes to 0, that is, if you are in the classical limit, the Casimir force doesn't exist. But this is no proof. This is a very disingenuous way to state the issue. Yeah, of course there is an H bar is a factor of the Casimir force and the van der Waals force and the London force. But the reason is that the internal degrees of freedom of the atoms are quantized. So, for instance, here you can see that Fritz London, writing in 1936, remember that London and Eisenschitz were the ones who formulated, if you want, the first quantum theory of van der Waals forces in 1930. Okay, they were not exactly the first. It was a Chinese student by the name of Chan that did it first before them, but he made an error. So they were the first to do it correctly. And so in 1930, they did that. In 1936 here, London, kind of looking back, explains the concept. And the concept here is that the molecular forces are due to the interaction between quantized atoms, a very important paper by London. Keep in mind also that London was the one who gave us the terminology of dispersion forces. We use those words to mean that these are forces that depend on the polarizability of the atoms as a function of frequency. Let me give you a quick explanation about what this means. So this is nothing but the London theory of dispersion forces in one dimension. There are many people who have done this, and another thread of my conversation, the Casimir Effect, that is dear to my heart is the fact that this community is very bad at citations. This causes all kinds of problems. So I would like to warn anybody who is interested that if you become interested in Casimir forces, you need to read a lot, because you will discover that these groups simply don't cite one another. It's kind of a shame, and I always call them on it. So here we have, I would say London was the one that simply said, let's take two harmonic oscillators of the type that students in undergraduate quantum mechanics study. Let's write down the electromagnetic force between these two dipoles. This is a classical force. And let's calculate the change in the eigenfrequencies of these two atoms due to the interaction of these two dipoles. This is a change that is actually to second order, because to first order there is no change. You need to go to second order. That makes the change, if you want, in the energy of the two oscillators inversely proportional to the sixth power of the distance. Plus and Porter, in a textbook, did it in one dimension. They were not even the first ones to do that. Kleppner wrote a very cute article in Physics Today with apologies to Casimir, but really he should have apologized to London, because he uses the same exact argument by London without citing London, which is bad. And Milani did the same. So nobody cites anybody, although Milani cites everybody. I would say that Peter was the best one from the citation standpoint. So here, look at what London says in his paper. According to quantum mechanics, are isotropic oscillators. So that means three-dimensional harmonic oscillators, because he did it in 3 dimensions. Even in their lowest states, make a so-called zero-point motion. I would like to stress this word, because I know that sometimes people that are interested in this field get a hard time from professionals, because the word zero-point field has become a synonym with, science fiction, because in The Incredibles, I think that there is a zero-point gun or something like that. So it's become kind of ridiculous. I would like you to know that if you use the word the zero-point field, you are in the footsteps of Albert Einstein, who used it first. This was Nullpunktenergie. So it's a very reputable concept in physics to say that a harmonic oscillator in the ground state can be considered as moving, if you want, although we need to, that's a semi-classical statement, due to the zero-point field. So here we have the energy of the harmonic oscillators. So this is called the zero-point energy, obviously. So this zero-point energy is multiplied by the interaction between the two dipoles. That's all. There is nothing else that you need to explain the van der Waals forces. You do not need to quantize the electromagnetic field. Now, I know what people will say. They will say, well, but if you are in the retarded regime, when the atoms are very far, then you need to have the propagation of the field included in the calculation, and then the field has to be quantized. That's false. In fact, in a paper that is not very well known, in a series of papers, McLachlan in the 1960s reformulated the exact same calculation that London did, but in the framework of retarded fields, and he obtains the same exact equations that Casimir did, the Casimir-Polder force that I will discuss shortly. All this I want to say fundamentally is be careful, because it's not true that the Casimir effect proves that the field is quantized. The field can be classical. There are Casimir forces involving classical fields all the time. What needs to be quantized is the internal degrees of freedom of the polarized particles. So here it is. Here we got now an explanation circa 1930 of what's going on. You've got these two particles now. So At this point, we can say we had two atoms, if you want to call them that, two three-dimensional harmonic oscillators of polarized stability alpha, of ground energy h bar omega 0, and that's their distance s. Sometimes I call it s, sometimes I call it r. Apologies. So now Hamaker and others had the idea to say, let's now take two slabs, if semi-infinite slabs. So imagine this slab on the left goes on to the left to infinity, and the slab on the right goes on to infinity. And let's take all these atoms that are interacting with each other by means of the London force, and let's add up pairwise these interactions. It is not a completely trivial calculation, but it can be done. Interestingly enough, it's kind of amusing that these calculations were first done by Newton, but they didn't know when this was done, and so it was they basically redid the calculation. They rediscovered this, if you want, and you obtain the van der Waals force in the unretarded regime that is inversely proportional to the distance to the third power. This is A, is the Hamaker constant that physical chemistry students study. Once again, the field is not quantized. Now, what happened in the 1930s was that when they started making experiments with colloids, they discovered, and these particles were in that case spherical particles approximately, when the distance was larger, when the colloids were rarified, if you want, well, this equation didn't hold correctly. And so that's when Casimir became involved in Eindhoven at Philips lab. So this was shortly before World War II. Just for you to believe me, it's a page from the mathematical papers of Isaac Newton. It's not in the Principia. When he did the calculation of the sum of the interactions of two spheres that are interacting with forces that are not inversely proportional to the distance squared. Can you imagine that Newton did all that without calculus? Although he had calculus, he didn't use it. He did it with geometrical methods. I mean, I think that it's shocking to imagine the mathematical genius of this man. Don't forget that Newton didn't publish his results until Robert Hooke and Edmund Halley begged him to do so when they discovered that he knew that the orbits of the planets had to be ellipses if the gravitational force is inversely proportional to the distance squared, which was 25 years after he had made the discovery. So this is Newton's genius is just difficult to grasp, I would say. So now, as we skip into the 1930s and early 40s, Verwey and Overbeek at Eindhoven were investigating this discrepancy between the expectations from the, we can call it maybe the Hamaker theory, the pairwise summation of London forces to explain the interaction of colloid particles, and the experiments, especially in the case of rarified particles. So it was this group that had an idea, and they basically, the idea is, I'm going to wave my hands explaining it just the way that they did. At the time, the interaction of atoms was schematically described as the interaction of radiators. So imagine that you've got two atoms that are vibrating, these are harmonic oscillators, and they are at a large distance. So this electromagnetic field is propagating from an atom to the next, just the way that an antenna would communicate to another antenna. So they said, what if at a large distance, what happens is that the wave that's coming from the atom on the left reaches the atom on the right out of phase, so that the atom on the right cannot respond properly simply because the distance is such that the vibration of the electron of the atom on the left is out of phase with the radiation coming from the atom on the right, and vice versa. So in other words, they thought that retardation would cause the two atoms to interact out of phase. Now, this is a completely classical explanation. I cannot even begin to say that this is quantum mechanical as an explanation. This is an explanation that you could actually assign as an undergraduate problem. This is an interaction of two antennae, basically, with oscillating dipoles. Now, Casimir and Polder took it from here, and in fact, they cite this intuition by Overbeek in their paper in the Physical Review, and in a later paper, Casimir-Polder forces. But then they didn't do anything to pursue it this way. They, of course, developed a genial application of an early form of quantum electrodynamics. So this, at that point, we're talking about 1948. So quantum electrodynamics did exist, and so by quantizing the electromagnetic field, they developed, Casimir and Polder developed the theory that we today call the interaction of two atoms. Now, notice that I'm referring sometimes to the Casimir force, sometimes I'm referring to the Casimir-Polder force. So more properly, we talk about the Casimir-Polder force when we talk about the interaction of two atoms. The Casimir force is the interaction of two macroscopic, perfectly conducting particles. I would like to say that from that point forward, much happened. So, for instance, there is this fascinating discovery by Edward Teller, the same Teller of the atom bomb, the hydrogen bomb, that, if we take now the idea of London of two harmonic oscillators in the unretarded regime, and we put three of them instead of two, you discover that it depends on how you place them. If you got three at right angle, it becomes a repulsive force. So this was the first time that people discovered that dispersion forces can be repulsive. This was very early, 1943. This was before Casimir even came on the scene. And there is another very nice article in the American Journal of Physics by Farina and others on this issue in 1999 that you may want to look at. So when Casimir and Polder came up, eventually discovered the Casimir-Polder interaction, something that happened was that, as you will see shortly, the equation is dramatically simple. Instead of being a potential that decreases as the distance to the sixth power, it is a simple equation with the distance to the seventh power. And so they wanted to understand how this could simply be due to something uncomplicated, but they were unable to find an uncomplicated explanation. In fact, I will tell you that there is a subfield of Casimir force research that has got to do with deriving a simpler explanation of the Casimir-Polder force and other, So what is the simplest thing that we can do and get the result? I would say in my book, McLachlan wins the prize, but that's an argument of taste, obviously. The reason that I believe he does is that he doesn't quantize the electromagnetic field. So this is kind of a violent summary of everything that happens. I would just provide the references here. I would say that Sprucht did a fantastic job in explaining why two atoms that are in the retarded regime are expected to interact. And so basically he told us this, now I would like you to understand what's happening that is very different than before. This is now, keep in mind, this is 1978, 1986 even. So now we are acting under the effect of a well-developed quantum electrodynamic theory of the electromagnetic field. So now the field has become an independent quantity. So here, Sprucht says, we've got two atoms at a distance, two quantized atoms, obviously, with dipole moments mu1 and mu2, but now they are immersed into this quantized field. We call it the 0-point field without any further shame about it. And he says, okay, he first deals with an equation that you can find this article in the Physics Today, that's easy to find. He obtains a potential interaction between these two atoms, that is only due to the existence of this classical field. And in fact, Sprucht jokes there. He says this is a result that Maxwell could have derived and perhaps did. But Maxwell didn't, because Maxwell didn't even have a fully developed atomic theory. Certainly, Maxwell never schematically described the atoms as dipoles. That was done later, so by a few years, I would say. So, but then by quantizing the electromagnetic field rapidly, Sprucht derives an equation in which the Casimir-Polder force is inversely proportional to the potential to the distance to the seventh power and the product of the two polarizabilities. The correct factor is 23 over 4 pi. A great mystery, by the way. I think the Casimir was on vacation in Sicily when he was reached by the first confirmation that his result was correct. This is a very famous little episode in the history of the Casimir-Polder force. Now, the question now is, Casimir went back independently to the Polder and said, okay, now imagine that we have two boundaries now, macroscopic boundaries, and we want to know, and before Tim becomes worried, I am shooting, I promise to be done at the half hour, okay? I promise. I'm accelerating. So two perfectly reflecting boundaries. And Casimir said, now, what about the interaction of these two? So this is an interesting problem, because if the boundaries are perfectly reflecting, then the constituent matter of the boundaries no longer matters. The only thing that matters is the field. And Casimir, in a later paper, described this as poor man's quantum electrodynamics, poor man's QED. In other words, he says, the only modes of oscillation that are possible between the plates are the ones that bring the field to zero at the boundary because of the typical boundary conditions of the electromagnetic field. He then calculates the energy between the plates, the energy outside of the plates, and the change between having the plates and not having the plates, technically speaking, is a difference between two infinite quantities. And then Casimir does something that we have become familiar with. He takes the difference of those two infinite quantities. Today we call it renormalization. Some of you who are familiar with the history and philosophy of science may know the name of Feyerabend, who was laughed openly at quantum electrodynamics for the concept of renormalization. He stated in a famous correspondence with the famous physicists of the time that QED was a theory in which you first know the answer and then you take the difference between two infinite quantities and you obtain exactly that. And there was a debate, but he never was convinced of renormalization as an appropriate way to extract quantities from the theory. Well, Casimir did that. And so by normalizing, he obtained the correct answer. I would like to say that there is an ongoing debate even today as to whether the Casimir force is intuitive or not. Milonni falls on the side that the force is intuitive, in the sense that he says, what do you expect? Once the two atoms are interacting, a slab made of atoms, two slabs made of atoms will attract. On the other hand, another Nobel Prize winner, right, Julian Schwinger, who got the Nobel Prize with Feynman and Tomonaga, states that it is one of the least intuitive concepts of quantum QED. So Schwinger said, we got two boundaries here whose structure doesn't matter because they are perfectly conducting and they happen to attract. How that would happen to Schwinger is something just short of a mystery. For Milonni, instead, Milonni says something else. Milonni says, well, okay, let's look at it. Let's take two slabs made of such atoms. These two slabs are not ideal, but then by using a very famous relationship in which the polarizability of the two atoms, this is called the Lorentz relationship when the functions are dependent on frequency, down here at the bottom left. This is the connection between the dielectric function and the polarizability of the atoms. You can connect the polarizability of the atom in the Casimir-Polder equation to the dielectric function of the two boundaries. Finally, by taking the dielectric function and sending it to infinity, as you would in a perfectly conducting boundary, you obtain an equation that is wrong, but not by much, by about 30%. So Milonni says, so it's not so strange, considering the fact that Casimir-Polder forces are not additive, as discovered by Teller. It's not so surprising that the Casimir effect exists. So I tend to agree with Milonni personally, that there is no mystery here. And let's not forget that the Casimir limit is unrealistic. The fact that the Casimir-Polder force, that the Casimir force it's an interesting mathematical problem, but you cannot have perfectly conducting surfaces. So the lack of intuition that Schwinger complains about is not so critical to me. But I do understand that we teach children that conducting surfaces that are neutral do not attract, neither attract nor repel. And now children need to be told that they attract if these two surfaces are parallel to each other and parallel plane surfaces. There is a different way to look at it. I mean, this is kind of the Casimir way, if you want. So this is from Power's beautiful booklet on quantum electrodynamics from the 1960s, in which he basically says, hey, let's just calculate the 0 point energy inside the boundaries, and by again extracting. But there is something else that he does instead of renormalizing. I mean, in a way, Power does renormalize, but what he says he does, he introduces a cutoff, and this is a cutoff that is completely arbitrary. But it's I mean, at this point we are trying to extract the Casimir effect from mathematics in 4 lines. That's not easy because it's not it's something you need to say. It is that this is not a simple effect to really calculate. Now, I want to claim that Milani, in his attempt to make it even more natural, came up with a very provocative explanation that I always like. This is very cute to find in the literature with Cook and Dogen. Milani wasn't technically the first to discover this, but he certainly was the most famous to publish it. So basically, he says, let's imagine that we got 2 boundaries that are perfectly conducting, and now we got, if we want to put ourselves inside of the framework of quantum electrodynamics, we're going to have virtual photons of the 0 point field. Well, these photons will bounce around, right? And we have boundary conditions of these photons, in that only some frequencies are allowed within the gap, and all frequencies are allowed outside the gap. So if you are inside the gap, you're going to write the radiation pressure. This is a classical equation for the radiation pressure due to the virtual photons inside the gap. So that pressure is pushing the plates apart. But then you have, of course, the force due to the outside of the plates pushing from the left on the left plate and from the right on pushing towards the right on the left plate and on the left from the right plate.
Yeah.
And
good.
That force is due to.
All right. Well, I'll let you know. I'll call you in an hour.
Now, obviously, these two pressures are both infinite. So once again, you've got to renormalize. Right. This leads you to a nice, beautiful problem with the Bernoulli numbers. That is this equation here at the bottom. A beautiful mathematical problem that was. There is a very nice article by Jonathan Dowling that really, in a fun way, describes this calculation in a way that is very entertaining. Unfortunately, Jonathan died untimely a couple of years ago, but I mean, a beautiful paper that you may want to find by Jonathan Dowling on the Casimir effect. I think it's in the Mathematical Journal. So anyway, once again, it's a form of renormalization. Now, this is the closing of the article by Casimir in a very difficult to find journal, I would like to say, but it's out there. A Dutch paper. as we approach the close here, I know that this is a lot of stuff, and I will accelerate towards the end. But I would like to say that post Casimir and Polder, the field was in a way an impasse, because now you have the real boundary. Like we have the Casimir-Polder interaction, which is an interaction between the two actual atoms, if you know the polarizability. And then you have this very idealized case, which is the idealized case of two boundaries that cannot exist, perfectly conducting. What do you do if you have it is a remarkable accomplishment in any sense. Not an easy piece to digest, but genial, because Lifshitz was able to, basically what he did was a again, I think some of the things that you see with the geniuses of physics is how they cheat the rules of the game. Because if you had wanted to do this right, you would have had to apply quantum physics to a solid and obtain the Casimir force, the Lifshitz theory that way. But that cannot be done. Even today, we have difficulty to do that. So what Lifshitz did, he basically recycled a device by Ritov, in which he injected noise inside of the solid and wrote down the properties of the interaction of two slabs starting from this semi-classical noise. I mean, he doesn't start from the commutators of quantum electrodynamics, to give you an example. So technically speaking, this theory has always puzzled theorists because it's not a fully quantum theory of the Casimir force, but it works fine. It is the most modern theory that we still have today. So I'm not going to go through that because that would require another seminar by itself. I just want to say that the closing here, I reproduce the equations from my paper. This is not what, I didn't do this. Lifshitz did. The only thing, I'm just citing this paper because you can find these equations written in terms of this Lifshitz integral. I just want to tell you, it's not a friendly integral to calculate because it goes into 2 dimensions to infinity. So it is an improper integral in 4 different places. And in fact, you might wonder, how did Lifshitz calculate it in 1955? I use Mathematica to do this. Okay, how did he do it? Well, Lifshitz had the genius. It really required a deep knowledge of physics and a mathematical sensibility that is uncommon. He realized that the dielectric function on causality considerations, if calculated on the imaginary axis, becomes a real function. This is due to the Kramers-Kronig relationships. I repeat, the dielectric function, which would cause any solution to the Lifshitz theory to be impossible to calculate, become a piece of cake if you just realize that you can transform the integral from the real frequency axis to the imaginary frequency axis. Because if you do that, the dielectric function calculated on the imaginary axis is a real function. So it is pretty amazing. And eventually he was able to tame that monster. And the only thing that he didn't have was the dielectric function for real materials. And we have been accumulating knowledge on this calculation ever since, fundamentally. But you can do this calculation today. I want to state that, especially if the slab is of finite thickness, even Mathematica, even with parallel computing, this is not a trivial calculation. It takes some time for a machine to do these things. At the end of the day, what you get is something that looks like this. Again, this is from my paper cited before. If you are at a large distance, the Casimir force decays inversely proportional to the distance to the 4th power. As you get closer, it decays inversely proportional to the distance cubed. So here, somewhere in the middle, you got the transition from unretarded to retarded regime. What's very interesting, philosophically speaking, is that you got 5 here, but I mean, there are more theories that lead to the same equations. What does that mean? I mean, the bad news is that the Casimir effect is not an effect that allows you to discriminate amongst any of those theories, because they all give you the same equations. It's a very robust conclusion, but it doesn't even depend on whether the field is quantized or not. So you can find it, it's proportional to h bar, but unlike what they will tell you, not because the field is quantized, but it's because the atoms are quantized. In fact, Lamoureux, who was the first in modern times to measure the Casimir effect, by using, Steve told me, I interviewed him at Yale, by grabbing stuff literally from the store. He and another student measured this Casimir effect in 1996, I believe, to within about 5%. Later, he downgraded himself to 30%. There was a furious debate with the Russian school. I mean, this goes under the heading of these terrible debates inside of the Casimir force community. But at any rate, Lamoureux eventually states here very clearly in Physics Today that photons, it's not to say the photons don't exist, but that experimental proof for the quantization of the electromagnetic field must be sought elsewhere. Nobody doubts that the electromagnetic field is quantized. Now, the reason that I want to state this very clearly is that there was a paper more recently by Kwak and others in Physical Review Letters stating that if a gravitational Casimir effect were to exist, that would resolve the problem of gravity quantization. That's false. You can very well have a gravitational Casimir force with a completely gravitational gravitational force. And I mean, you can have general relativity that has got the field as classical, not quantized, and still have a Casimir force that is gravitational. And I have proved this in a paper in Symmetry that is, you can find that open source published by Jordan McClay last year. I'm gonna run through the rest of it here. This is the Deryagian experimentation with the scales, balances, 1960. State of the art in 1960 with an error of about 100% plus or minus. This is the paper by Kwak in Physical Review Letters, in which he also made a computational error that I corrected. It was a battle. The Physical Review Letters didn't want to even admit that the computation was incorrect by a factor of 2 pi. But bottom line is, interesting idea. But remember, even if the gravitational Casimir force is detected, that does not prove that the gravitational field is quantized. We don't have the time to get into it, but I want to say that this is, in my opinion, one of the most remarkable final frontiers for the Casimir effect is its application to Casimir forces. Any field of the gravitational fields, any field that has got fluctuations, eventually any field between interacting fluctuating oscillators will contribute a Casimir force. I would like to say that from the numerical standpoint, so far, I have only spoken about the archetypal geometry of parallel planes, but obviously this is not the case. So I published a paper that was some kind of a generalization or let's call it a simplification actually of the imaginary frequency green function method introduced by Rodriguez and others at MIT. They used FDTD. I showed that it can be done with ordinary FD, finite differencing, but it's a long calculation when the boundaries are not parallel plane. It can be done today. Once again, you don't have to quantize the field. In fact, it's kind of interesting because Rodriguez and others and I only use the machinery of classical electromagnetics to do it. I wanted to close a second with a funny subject here. That is one of the myths. There are several. You are gonna hear people tell you that ships at sea attract due to the Casimir effect. So if you got 2 ships in the ocean, they attract. This is a very widespread myth that you're gonna find in the literature. And I would like to say that you need to really be careful. This is just not true. there was a debate between me and the author of this paper. I basically was fascinated because in the American Journal of Physics, Boersma published a paper in which he says, if ships are atoms and you put them into a wavy sea, then you're going to have a Casimir force corresponding to their attraction. Now, this is a very legitimate question. In fact, I believe that that is true, that if you can put, two plates in a tank and you make waves in that tank, you're going to have a Casimir effect due to these waves inside of that tank. But then Boersma went to an old book about navigation from Causet in the 1800s. And he published this figure in which he says that two ships attract each other if placed in a storm, in a stormy sea when the wind has abated. I was absolutely driven by curiosity. I mean, this was an amazing book, very difficult to find. Eventually, I found the book in a bookstore in Australia. I ordered it online. And what I found shocked me, because what I found is the opposite. So this is the French. I'm not going to try to read it because my French is not good. But basically, the French doesn't say that two ships attract in that condition. The caption at the bottom is not the correct caption. The caption at the bottom that Boersma took came from this one. It says in here that two ships attract each other in flat calm, not when the sea is rough. When the sea is rough, in fact, the book warns sailors to stay apart from another ship, simply because the riggings may become entangled. It's got nothing to do with any force. It is in this situation that the two ships seem to attract. It's got nothing to do with waves, which completely invalidates the argument. So I wrote to the editor of the American Journal of Physics, and I said that this, basically, despite the physics, it's unethical that the two captions were switched. And the American Journal of Physics refused to publish any comment on that. And so it ended up to Nature. Nature was the one that kind of embarrassed everybody, because Nature likes to do these things. So you're going to find a paper by Physics Paul, kind of a funny one, entitled Popular Physics Myth is All at Sea. So there are several of these that I've spoken about today. Be careful when you analyze Casimir forces. Don't believe everything you read, because sometimes people just want to push a story, and I've given you a few today. In closing, I would like to say, I'm really accelerating, I promise, Casimir forces in microelectromechanical systems. This is what we've covered with my students this semester. Jordan McClay was the one that put the two together, although we need to not forget that a great genius of physics, I think, Robert Forward, who unfortunately left us too soon to brain cancer, was the first one that really understood the interaction of energy and electrostatic energy in Casimir forces by introducing something that looks like a battery, basically, a Casimir force battery. In his implementation, it cannot work, but he showed that also the numbers are not interesting. But conceptually, it was the first time that he showed that the Casimir force and electrostatic forces can exchange energy. Okay, that's what fascinating. Jordan McClay was the first to show that microelectromechanical systems are heavily affected by Casimir forces. So we are talking about the early 1980s. In his system, energy is conserved. There is no friction. There is no outside resonance or anything like that. But this was the paper that Capasso and others used as a guide in their experimentation. So I think that Jordan McClay must be credited with the idea to put the word Casimir force and the word microelectromechanical system in the same sentence. We are kind of going towards the end here. I want to say that we have spoken about the physics a lot, okay? But let's not forget that now we're talking about the marketplace. And as you all know, I think that Elon Musk has got the story that it takes a lot of energy to transform a good idea, a rocket in his case, into something that can revolutionize the market. I'm not talking revolutionizing physics, because rockets still fly for the same reason. So the Casimir force solution, let's call it that, I am pursuing it personally now from academia because it became just impossible to do it from inside of the marketplace because the time horizon of 20, 25 years is unrealistic. I'm very happy to see that the Gecko glue group is now getting to the point that they are making products that are being marketed. But remember that when I said the word Casimir force at JPL, it wasn't well received. Now it's considered obvious that the Casimir force is an application for adhesion. But at the time, it wasn't very reputable. In part of it also, I believe that the Casimir force community of enthusiasts embraced fiction. And that didn't give us a good name. So we need to be careful that we stay to the physics that is demonstrated in the laboratory without taking unnecessary leaps. You can revolutionize the market without leaping anywhere, fundamentally. I would like to state that among my more recent contributions, I have proposed a particle accelerator in which the particle that is being accelerated is a core of a nanotube. And this is an alternate, this is a section that repeats itself for thousands of times. And so by illuminating the different sections of a nanotube and using the same strategy that we've described before, you can accelerate this core and expel it at super high speed. I promised Tim some propulsion idea. So this is one. You can take a core and expel it at tens of thousands of kilometers per second, much higher speeds than with ion propulsion engines. And if you can create a carpet of these nanotubes that are sucking nanoparticles and accelerating them, provided that you can provide the energy, you can get thrusts that are at the level of chemical engines while having specific impulses proper of ion propulsion engines. And I presented this at the Joint Propulsion Conference of the AIAA a few years back, well, almost a decade ago. I would like also to say that I published and at some point patented a system in which energy, electrostatic energy is stored, again, by using the nanotubes as a strategy. So this is a way to use the forward idea of simultaneous interaction on electrostatic interaction and carbon nanotubes, along with the fact that nanotubes allow you a form factor that is much higher. And I would like you to start to see that, you know, we got astronauts here. This is in the Vomit Comet, grappling objects by means of the Gecko glue. So it's going to space. In fact, I've seen there are two small robots now in the International Space Station that grapple to their charging stations by means of Gecko glue. The Gecko glue is one of these applications that I would say, you know, shows that the Casimir force is going to space. There is another one that is less known, and that is a transistor, if you want, that again would require too much to talk about. But basically, transistors introduced by Rooks and others, the company is Nantero, in which interacting carbon nanotubes touching each other and sticking by the Casimir force create, you know, zeros and ones, and that's flown in the space shuttle already. So this will be a transistor that doesn't require semiconductors. I kind of I'm getting to the end here. This takes us back to the table that I showed you at the beginning. A lot of stuff that can be pursued, and I would like to again encourage anybody who gets into the field to understand that, yeah, new physics may very well happen. It will happen. I'm enthusiastic about it. I am my interest in the breakthrough stuff is on the fundamental structure of space-time. So I look forward to discoveries in that field. But I would like you to understand that, again, going back to Elon Musk, it is the transition from what we know to the marketplace that is the battlefield for Casimir force research right now. And it takes a lot of work, even to make a new battery based on Casimir forces. I have presented in Silicon Valley dozens of times to people who, including Nobel Prize winners, who never had any doubts that I was right. The question is the market strategy. So that is where the battle is really happening right now. So I will stop here and thank you for your patience. I apologize for going over. So best wishes from beautiful Izmir, Turkey. This is one of the most beautiful places in the world. I hope that you will visit someday. Thank you, Tim, for your patience.
Well, thank you, sir. So let me do this. Let me see. Let me stop your screen share. And I want to put this on gallery view. And everyone, please give an enormous applause for Dr. Fabrizio Pinto. Sir, I think you may be the world's leading expert on Casimir force. If not, you are certainly one of the world's leading experts. So thank you so much. Thank you so much for presenting on this.
My pleasure. My pleasure. My pleasure.
And then you have the focus on propulsion as well. So I mean, this is, you have a really novel specialization, and you're applying that towards breakthrough propulsion, which is just an incredible combination. So thank you, sir.
Thank you.
So we only have probably about 20 minutes for questions. So let me bring that up again. Option Y on Mac or Alt Y on Windows for questions for Fabrizio. And let me see. Robert Diaz, go ahead, sir. Oh, I'm sorry. I'll allow participants to unmute themselves. There we go. Asked to unmute.
Okay, thanks.
Yes, sir.
Basically, I'd like to get your reaction on some results from quantum field theory. There have been a number of papers that have been published on this, where it's about Casimir wedges, and they allegedly produce torque forces. And using a little bit of high school vector analysis, you get this anomalous force in the direction of the wedge angle bisector. So I'd be interested in your reaction on that.
So, I mean, I always react to, and again, Robert, if you would like to email me or email Tim with references, I would like to see the references. So
I can tell you, I mean, 1979, there's a paper by Deutsch and Candalis.
Right.
And
so on the wedge, the calculation of Casimir forces with wedges, again, very complicated because it's a non-standard geometry. There is no doubt that there are torques in that case. That is very interesting and technologically applicable. But I want to be careful about the implications. So torques, yes. But when we talk about the non-conservation of momentum, I get more suspicious. So I would like to see whether Candelas claims non-conservation of momentum, because I think that they claim torque, which is a correct statement. But whether you can extract momentum from the quantum field, I don't know if they've done that. So because you talk about application of vector calculus, at the high school level, I would like to make sure that I mean,
I have corresponded with Ivor Brevik, rather. He's another author.
Yeah, Brevik, yeah, sure.
Yeah, and I was suspicious myself. I said, is there some vector in the R direction that would cancel out this anomalous force? And he told me, no, there's no vector in the R direction. In fact, he agreed that there is this anomalous force in the direction of the angle bisector. And he says there is no contradiction, conservation of momentum if you keep the entire system in mind.
Right. So, and I agree. So if we keep the entire system in mind, then there is no violation. So what that means is that you can actuate the devices that way by introducing this torque. I have no doubt about it. I become concerned when we trust the models too much, because then you can imagine making a machine that harvests energy from this object that is spinning out of control. So I want to make sure that we don't, because then we build things on false conclusions, So, but I agree with Brevik on that issue.
Okay. Well, I went a little further. I actually proposed an atomic force microscope experiment to see if we could see these lateral forces. And I'm in the process of putting together such an experiment along with a collaborator in Germany.
Yeah, and is probably I know the collaborator in Germany also, but
I don't. Yeah.
Yeah. So no,
I don't want to say his name.
No, that's okay. Probably a good friend, but
Yeah,
so what I'm saying,
him.
yes, but what I'm saying is that I think that he and I have discussed this issue, and I think that the AFM allows exploration of Casimir forces in non-standard geometries, and I think that that's an open field for the AFM. Of course, the challenge is the fabrication of the structures themselves. You know, that's the issue.
Well, we've gotten beyond the structures. That now it's actually putting together an apparatus that can unambiguously disentangle the normal forces from the lateral forces.
Right.
And this is where we are right now.
I'm impatient to see this publication.
Okay.
Good luck.
Thank you very much.
Sure, good luck.
And thank you as well, Robert. Okay, let me go to Michael Boyd next. Sir?
Hello, sir.
Hello.
I'm curious. I've heard when I hear about the Casimir force, a lot of times I hear mentioned the vacuum energy. What would you disentangle that for me, please?
Yeah, of course. I mean, this actually goes back to Casimir himself, you know, because Casimir, I showed a slide before in which Casimir said, let's calculate the energy due to the quantum vacuum oscillations between the two plates. And I don't know if Tim wants me to go back to the slide or if I should just wave my hands. What should I do with him, Tim?
Oh, yeah, if you want, you can put the slide back up. Or yeah,
Okay.
we have a few minutes left, so.
Okay, I'm going fast. So I want to answer the gentleman in the way that is, did you get the thing back?
Yeah, yep, it looks
Okay.
like it's perfect.
Okay, so I'm going to go through it. Okay, let me go back to that slide in particular. And I mean, this is fine. So basically what Casimir said is we got the vacuum, what you call the vacuum, doesn't exist in quantum electrodynamics because of the uncertainty principle. So whereas we teach in school that if in a area, in a region of space without charges and currents, the field is empty of energy, in quantum electrodynamics, you cannot say that, simply for the reason that the uncertainty principle says that you cannot have all components of the electromagnetic field zero at the same time with infinite accuracy. Consequently, the energy of the electromagnetic field is not zero at any given point. And this is one of the great mysteries that remain, in the sense that if you take quantum electrodynamics at face value, the energy of the electromagnetic field should be infinite. Or as Weinberg said once, would be like, 10 to the 122nd power or something crazy like that. But it isn't, obviously. So we don't know what's going on there, but what we do know is that there is some energy in the vacuum of space. And the only thing that Casimir did was to calculate not that energy, because we don't know what that energy is, but the energy change. So because forces are the derivative of energy with respect to position with a minus sign in front, even if you don't know what the actual energy is, and you take just the derivative of this thing that we don't know, you can get the force correctly. So that's what I'm trying to do for you. I'm trying to tell you that the reason that you hear the word Casimir force and vacuum at the same time is that one way to explain the existence of these forces is that you need to think of the vacuum of space as not empty, not vacuum, but there is energy there.
But don't reflections of the surfaces cause different oscillations?
Yeah, so the presence of the boundaries, as in this slide.
Like projections causes, like, see, even the vectoring right here, the right side, my right, has a darker color than lighter, so light reflections changes, so the frequency would change. It just depends on, you know,
the
reflection
frequency,
and the
right?
angle.
So the frequency, the calculation that Casimir did, if that's what we're talking about,
Yeah, because
was
there's light reflections, so the frequency
Yeah.
goes up.
Well,
Right.
and Lulu, if it's okay, let me have you
Yeah.
wait until.
Thank you.
that's so I don't.
A follow up on that question about the vacuum energy. So
Yes.
do you know who Dr. Hal Puthoff is? He's he's done some publications on this Casimir vacuum energy too, and I asked him this question. My background is in infrared and semiconductor physics, that kind of stuff, and in a semiconductor has what's called a band gap. You understand what?
Yeah.
So my question is this let's call it a field, this Casimir field, does it have a band gap like a semiconductor?
So if you are talking about the band gap of the two slabs, if you can imagine the two slabs made of a semiconductor, then the optical properties of the slabs do affect the Casimir force greatly.
Well, no, I'm actually talking about the region in between the two slabs.
No. So if the vacuum is a vacuum, I mean, of course you can put water in the middle, you can put alcohol in the middle, okay, you can put anything you want in the middle. But if the gap between the two is empty of any other substance, then the frequencies are determined only by the boundary conditions between these two plates. Just what they teach you in school, because you know electrodynamics, so you know that the electric field at the two boundaries will vanish, to give you an example. So that determines which kind of oscillations you can have due to the vibrations of the electromagnetic field that are caused by the uncertainty principle. On the outside of the region between the two plates, there are no such constraints. So on the outside, all vibrations are possible. In between the plates, only some are possible. I would like to stress that this doesn't explain why the force is attractive, because in reality, technically speaking, there is an infinite number of vibrations possible both inside and outside. So you need to be careful.
It could be repulsive too.
It's possible. It's possible. Yeah,
Yeah.
it is possible.
Well,
Yeah.
well, and Michael, yeah, if it's okay, I have some more.
My questions. I appreciate it.
And thank you, Michael. Sorry, I'm trying to rush because we're getting towards the top of the hour. So let me see. So next, actually, I had one in chat. Monomorph he asked, please ask Fabrizio what he thinks of Sonny White's recent work with Casimir cavities, and if he thinks there's any potential for using the Casimir effect for reactions propulsion.
So I know that I have been cited in the context of that research. I don't know why, though. I mean, what I think is that, to the very least, the jury is still out on whether Sonny White has got something or not. But typically, when people don't know where something is coming from, they say it's got to be the quantum vacuum. So my fallback position when people say that is, if the vacuum were not quantized, if we had a completely classical electromagnetic field, would you still have this effect? So if the answer is no, I don't trust it. So that's my opinion right now. But I understand that maybe I am being too conservative. So I would like to see the final data on Sonny White's device, though, because that's still, I don't think that we have seen the end of that. So
okay. Well, thank you. And then let me go back to Lulu, if it's okay. Lulu, you're still on, right? I'm not sure. Okay, yes. And then you had a question a moment ago, and could I ask you to turn your camera on, if that's okay?
It's on. I turned it on.
Oh, okay.
Yeah. Hello.
Hi.
Hello.
I had a question. Well, a couple of questions, but with wave frequency, it doesn't, depend if the particle that it's touching on one side, when it bounces back to the other place where the particle's touching, wouldn't those two things for it to create a harmonic would have to be, like 100% of a pure element in order for that to be perfect. Otherwise, things are, you You don't know what
Well,
what
right, right. So yeah, but it is in this case, because in this calculation that I have on the slide right now, if it's still visible, which is the proper, this is the calculation that the Casimir did. These are two perfect reflectors. So it is exactly what you're asking for.
Okay, so like, and then you had the angle of the arrows on the two slabs from that side,
right.
all coming vectoring down, or it's plateauing, but you still have a wave propagation, even if it's at zero. That's the only really one that's going forward.
So and what you see in the calculations here, which is not friendly, but it's the sum over all of those. So it's not just one of them; it's all the possible directions in all possible times forever. So it's a calculation done from 0 to infinity, from 0 to infinity, from 0 to infinity. That means that we are calculating all possible directions for these arrows to go, because
errors. Okay, so you're calculating for errors. You're not calculating for possibilities, like like.
No, I think he said arrows. I think he said arrows.
Arrow, as in this thing here. Arrow, the direction of the motion. Yes. No, there is no uncertainty. We haven't even talked here yet about the noise of the Casimir force, which will be the uncertainty on it. That's a very, very small number. So right now we're talking about a static Casimir force.
Yeah. Okay. Well, let me, Lulu, thank you. Let me go to Bernie next, really quickly, and then I'll go to Will after that, and we're probably out of time.
Thank you.
Hi, thank you so much. That was an amazing presentation, Dr. I hope your students call you Dr. Fab, because that was fab.
No, but it's okay. Fabrizio's fine, and it's the same for you. Thank you.
Thank you, Fabrizio. Very fascinating. Are you familiar with Nassim Haramine's work at all with the Casimir effect, and how he ties it in with Coulomb's law and not quantizing, but tying it into the holographic memory of the structure of space-time?
Can you repeat the name? I didn't grasp the name of the person.
Nassim Haramine. He's an Iranian Canadian, but now he runs the Resonance Academy out of Hawaii.
I cannot say I'm familiar with what he has done. If you would like to send me the reference, I would be happy to give him a response on that.
Absolutely. His main paper that would be relevant is the Schwarzschild proton.
Okay.
Thank you
so much.
Yeah, thank you.
That was fascinating. Sorry, one last quick question or comment was how you noticed that shape when you're showing your very first pictures of what looked of that experiment from the past, and how it resembled to me all the alchemy experiments of stuff.
This one?
Yeah, well, at both of those. And just quickly to tie in is that I've been reading a lot of Sir Isaac Newton's alchemy writings, and then in my own experiments reproducing some of them. And you started out talking about Isaac Newton, and a lot of his theory that was missing is in those writings. So gather up them.
Okay, and Bernie, thank you, sir.
Thank you.
So let me apologize. I'm rushing here. I want to get to Will, and then I think that we've wrapped things up. So Will, go for it, sir.
So in Lulu's question, you mentioned that the frequency was important, but then in Michael Boyd's question, you mentioned that whatever the material between the plates was not important. But my understanding was that one of the reasons of going into to use the vacuum was because dielectric constant is important. So which is true here?
Yeah, it is true. Good point. So we're talking about two different things. That's why, unfortunately, the conversation has been very long today. But in all these discussions, we have talked about the Casimir force. But this is the
possibilities. You guys were seeing exclusions. You know,
Lulu,
that was the difference.
yeah. Let's
Sir.
yeah. If we're okay, let's wrap this one up, and then we need to move on to our next speaker.
So what I'm trying to say is simply that in the Lifshitz theory, you deal with the dependence of the electric properties on frequency. So in the imperfect materials, in the real materials, you use the Lifshitz theory. And so then you have the dependence on frequency, the dielectric function. In the ideal case, however, epsilon goes to infinity. And so at that point, it doesn't matter. So be careful when you're talking about the Casimir force. Are you talking about the ideal case or the real case, in which case you need to use the Lifshitz theory?
You explained like quantitizing packets between platelets
Lulu,
and
please.
sending them to Centauri.
Lulu, I'm sorry. I have to mute you. We're almost out of time. Okay, I'm sorry. Fabrizio, could you finish, sir?
Oh, you know, what I'm saying is simply that I think that I agree with the last gentleman who spoke that generally speaking, the properties of the material as a function of frequency are crucial. However, they are not crucial in the case of the Casimir effect proper, because in that case, we have taken the reflectivity to be infinity, to be equal to 1, sorry. So in that case, epsilon is equal to infinity, and in that case, it doesn't matter. It's a property of the quantum vacuum and nothing else. So so there is no contradiction.
Okay, sir, thank you very, very much.
Thank you.
Okay, and we're out of time. I should apologize. Lulu, I apologize for cutting you off. And so let me do this. Let me put this back on gallery mode, and I'm going to stop your screen sharing.
Thank you.
Yeah, and again, everyone, please give a giant applause for Dr. Fabrizio Pinto. Sir, thank you very much. And I apologize for rushing through the question and answer. This was a wonderful presentation, incredibly educational.
The fault is all mine, Tim. I kept talking. So.
Oh, no, not at all. Not at all. It's wonderful, wonderful content. Wonderful content.
Thank you.
Okay, so let me do this. So our next guest is, let me see. Our next guest is Mike Melia, and unfortunately, I have several Mikes with no last name. I believe it is this gentleman here.
That's me, Tim.
Ah, okay, sir. If it's okay, if you can give me just one moment, let me do this. I'm going to spotlight myself for just a moment, and let me do a brief introduction. So Mike Melia is a retired mechanical engineer. He's going to present a new approach to inertial propulsion, and he'll discuss a video showing a proof of concept prototype as he will demonstrate a primary drive is delivering perpendicular rotation, and in normal circumstances, any peripheral force generated by this movement should manifest itself within as part of the rotation. But contrary to this, the drive is creating linear thrust that's emanating in a 90-degree angle to the direction of rotation. So without any further ado, let me hand things back over to Mike, sir, and I will spotlight you for your presentation. Again, we're going to do, if you can do an hour, and then we'll just do Q&A after that.
Okay, Tim, I'll try and stretch it out to an hour, but my presentation is fairly simple. Have a look at complex scientific presentations I've just seen.
And Mike, I'm sorry, sir. If your audio is a little faint, could you move your microphone a little closer?
How's that, Tim?
It's a little bit better. A little bit better.
Is that a bit better?
That's perfect. Thank you, sir.
Okay, it hides parts of my ugly mug. Okay. I think no need to you, Tim, but I'm very new at this, so I hope the assembled audience will forgive me if I make a few mess ups. My last presentation, as you just said, I'm retired. I'm knocking on in years now, and my last presentation was before a live audience, so this is entirely new to me. But a little bit of background on myself. I have been an engineer for as long as I can remember, 40, 50 years. I've been a consultant, I've started my own business, and mainly in my engineering career, I've been a problem solver. And I like to think that I can't think of a failure, but I do have 100% record on taking on a problem and sorting the problem out. It may not be the last and final end to the problem, but it will be a resolution. And many years ago, I was quite fascinated by looking at a TV in the UK, a TV documentary. It was a Christmas lecture, and it was run by a man called, I've no doubt all fans will remember his name or know of him. It's Eric Laithwaite. Professor Eric Laithwaite is the originator, I think, of the magnetic levitation motor. But he had a fascination with gyroscopic forces and gyroscopes, and that fascinated me. I wondered why a gyroscope operated the way it did, and it was a bit of an interest thing to me. And about 35 years ago, I decided to look at it and see what I could do with it, because the concept of space propulsion was talked about quite a lot at that time, and the need to provide an alternative propulsive force. And I thought, as a mechanical engineer, the answer will lie in mechanical solutions. I'm not a scientist, I'm not a physicist, I'm purely a mechanical engineer. But I look at the universe and I say to myself, the whole of the universe is one big machine. It's one big rotating machine. The physicists can get involved when it comes to the building blocks of the universe at atomic and subatomic particle level. But for the rest of us, the universe is one big mechanical machine. And more importantly, it works on rotation. Everything is in rotation. So at the time, I thought that rotation might be the answer to a propulsion system. If you look at the whole world we live in, nothing works without rotation. We can't even move along the ground unless we have wheels. So everything works on rotation. So at that time, I took an interest in it, and I started applying my thinking to a method of inertial propulsion. And I thought I would start with rotation. And I built a machine 30 odd years ago. And I got some strange results from them, but because I didn't understand what I was doing or what the machine was actually doing, I discounted it. I've discounted an awful lot of machines since then. And I've discounted an awful lot of machines I've seen on the likes of YouTube because of what I've learned by what I've done myself. So for a lot of years, I got on with my career and I sort of dealt with this as something of a hobby. Not taking it too seriously and not working too hard at it. And when I retired, I thought I would take another view and have a really look at this. I was determined. It's a problem. I class myself as a problem solver, and I criticize myself for not solving the problem. So I started looking at the whole thing in depth. I'll have to refer to a few little notes at the moment. I thought I'd look at it more in depth because I'm driven by it. And I thought I've always been driven to try and solve a problem, and the biggest problem of all was a viable deep space propulsion engine. Because I honestly believe without such an engine, humanity has no future in believing it can progress any further into space than the moon. I mean, rocket power is fantastic, it's wonderful, and it'll get you up into orbit. But the amount of fuel that's required and the amount of effort and expense to do that and the limitations of that fuel leads me to believe it is no real use. Certainly in manned exploration of space, it's of no real use at all. And we really do need what your whole raison d'etre is, an alternative form of propulsion. Excuse me one moment, Tim. I may just have a... and the machine I've come up with now, I have worked on for quite some time. And I started getting some results, very minor results, and I couldn't explain them. And unless you can explain a result and why it's happening, you cannot further it or improve on it. So it took me quite a few years to actually find out what was happening or why it was happening. And once I did that, I was able to build a prototype that could give clear demonstration of what I'm talking about, what I explained, and that it is true inertia movement. It reminds me at this stage of the jet engine. I think when the jet engine was first invented, it's Sir Frank Whittle. He got, correct me if I'm wrong, but he got something like 3 pounds of thrust from a substantial engine. But that was sufficient to prove the point. The rest is history, because once his findings were given out to the world of engineering and aeronautical engineering, then that 3 or 4 pounds of thrust developed into 300,000 pounds of thrust. And I think the apparatus I have right now is at that stage. It's in the early stages, and I consider this on a par with the jet engine. I hope that doesn't sound too conceited, but I'll let the audience be the judge once we go into demonstration mode. I will like to screen share, Tim, if I may, if I can sort of demonstrate it myself. And again, bear with me because I'm new to this.
Yeah,
So
absolutely. So Mike, let me do this again. That's the green screen share button that is down. Yeah.
Yeah, I got that. I'll put the screen share on and I'll run through a few notes that I have there, but I'll just think, was there anything else I need to tell people? Just basically, I mean, my sort of whole life has been simplistic enough man, but I do have, I believe, a God-given gift to solve problems. And I've hopefully used that gift, and that will be reflected in what I'm going to show you. So the main screen share.
There we go. Okay, and so it is showing the slide outline. Yeah, so
I'm showing a slide outline, if that's okay. I mean, I've not separated it. As I said, I'm new to this whole thing, Tim. So my presentation will be a bit amateurish, but hopefully simple and understandable. So the whole thing is about inertial propulsion. And I asked the question, is inertial propulsion impossible? The answer to this question, you have to be aware of the problem. Most people are not aware of the problem. You don't think about it. You know, who thinks about inertial propulsion? There isn't a problem because you don't think about it. But in simplistic terms, it is as follows. You have an electric motor you wish to use as a propulsion unit. If you fit it to a land vehicle, you'll need a linkage to join the motor drive to the traction of the wheels. If you fit it to a boat, you'll need a propeller to use water as the drive medium. Similarly, if fitted to an aircraft, you will need a propeller using air as a drive medium. If you wish to drive a spacecraft, what can you connect it to that will provide propulsion? Wheels? No. With no gravity, there can be no traction. Propellers, having no air or water, means no propulsion. So how and what can be attached to your motor that will provide thrust in the airless vacuum of space. The more this is thought about, the more mind-numbing the problem becomes. You will realize it is a seemingly impossible situation, and the reason why so many notable people have declared it impossible. I think if people really do think about that, they will. I had that stage many, many times. But as I said, I'm driven and I do not believe in the impossible. If I look at the next slide, because is it possible? And I believe the answer to the above is yes. Like everything else, it's only impossible until it's invented. As an engineer, my thinking was always going to be mechanical. And for inspiration, I looked at what I consider to be the power of the universe, which I mentioned before, rotation. The building blocks of creation, atoms, only exist with rotation. Moons rotate. Moons rotate around rotating planets. Moons and planets rotate around rotating suns. Suns rotate around galaxies ad infinitum. And I believe if the great engineer can create a universe of rotation, then that for me is surely a good place to look for answers. Right, and rotation creation. Ever since the invention of the wheel, rotational forces have been undervalued. We've taken them for granted. For example, we build, say, a jet engine, and we claim it works by igniting compressed air and combustible fuel, with little credit given to the rotational forces that make the whole thing work. Is it possible this lack of appreciation of the potential of rotational force is one of the reasons not enough has been done in exploring its potential as a solution for the creation of an inertia propulsion drive? I will be showing a video, and the following video shows a proof of concept prototype. As will be seen, the primary drive is delivering perpendicular rotation. And in normal circumstances, any peripheral force generated by this movement should manifest itself within and as part of this rotation. But contrary to this, the drive is visually creating linear thrust that is emanating at a 90-degree angle to the direction of rotation. I've left the prototype basically exposed. A lot of people would have put it in a box to sort of hide their, if you like, intellectual property rights. But I've seen so many boxes that do not give me any answers because I want to know what makes it work. And when I built my prototype, or when I put the prototype or filmed the prototype, I wanted it to be clear to the onlooker that what they were seeing was not some kind of angled pendulum working with the aid of gravity and various other things, that they could see basically that it was a perpendicular rotating device. Now, it does not give everything away because the how that rotation is turned into linear thrust is the proprietary know-how that I have. So I'm quite happy to show the video in its form, that it shows to people that there is no trickery or gimmicks involved, that what you see is what you get. And I believe it's a clear demonstration of rotary force engineered to create recoilless linear thrust. If I may go on to the video, if I can just take another unaccustomed as I am, I'm a bit dry. I will go on to the video. Okay. Right. The video. I will stop it now and again. I will hold. I will read this out, although it is part of the video. The prototype machine demonstrated in this video has no conventional drive mechanism connected to any part of the unit or the underside of the machine. I will actually demonstrate that. The drive method of perpendicular rotation is clearly visible and demonstrates no pendulum action is responsible for the demonstrable linear force being created. The mechanism is in a closed unit demonstrating no propeller power is responsible for the linear force created. The linear force being created is not random imbalance or vibration. The video demonstrates it is a powerful and controllable directional force acting contrary to the direction of the primary rotating force. Existing propulsion engines require wheels or propellers, rockets or jets to facilitate drive. The machine demonstrated has no wheels, no propeller, no jet or rocket, showing it to be an entirely new form of powered drive. This is the start of the video, the machine itself. It's been demonstrated on literally the dining room table it was built on. But you can see there is completely enclosed. It's clearly rotary. I'm not hiding that fact. It's clearly perpendicular. There's the motor, straightforward. It is driving and it's rotating something in that shell. It's not a propeller. There's no way the air can escape out of there. There's no way, as you will see, it will escape out the back. So there's nothing to hide except the final little bit of information that lies inside the machine. So I'll start it and you can have a look at that. This is demonstrating the thrust that's been actually generated. You'll see some bungee rope there that'll level it out a bit. You'll see the thrust on this will reach 5 pounds. I have actually had the unit up to as much as 11 pounds, but for demonstration purposes. Now this particular part, you will note there is a small nylon tie at the back. I'm showing the machine actually acting as a lift mechanism. It is pulling it up and the toolbox that it is pulling up is filled. Now, on this one, as you can see, the machine is being lowered onto a standard steel tray, much to my wife's annoyance. It's one of her favorite roasting dishes. But it's just being lowered on. There is no mechanism under the machine that is facilitating any drive. So it's relying purely on the conversion of the rotary movement. Now this next one, I clearly lent it over. You can see with complete clarity there is nothing there. There's no drive. And it is, again, reliant completely on the conversion of rotary forces into linear. The vibration that can be seen is caused by setting the machine to ease its gravity-induced weight. This gives a better demonstration of the linear force created. Video shows the machine is producing thrust from relatively low revs. Again, another thing I wanted people to see, there's nothing to hide. They are low revs, it's only in the small hundreds. If it was developed and engineered up to a high rev standard, the thrust, I believe, would be substantial. Right, you've seen the video. The concept, function, and simplicity of the drive potentially ticks all the boxes of reliability. I believe is essential to long-range space exploration. Keep it simple. Simple is reliable. The drive can be engineered up to create substantial thrust vis-a-vis the jet engine. Inexhaustible fuel supply, powered by the sun in the solar system, nuclear generator outside of it. The particular drive you've just been looking at is a 500 watt motor driven by a 24-volt battery, easily supplied by solar power. But to me, any space exploration, the engine, like everything else in life, has to be as simple as possible, because simplicity creates, if you like, reliability. Really, there's not a lot more I can say, if I can just. Well, maybe ask some questions. Shall I take your share, Jack?
Okay, so Mike, it sounds like, let me do this. We have a bunch of people lined up for questions. Let me stop your screen share.
Okay.
Okay, and let me see. So we're half hour. So we are a little bit ahead of schedule, but that is totally cool. Okay, and first things first, sir. Let's do this. Let me see. I'm going to remove your spotlight. Okay, so everyone, please put your hands together for Mike Melia. Give him a big applause. Mike, thank you for the presentation. Thank you for the demonstration video as well. That's wonderful. Okay, so let me do this. And again, we're a little bit ahead of schedule now. So let me go to Elzbieta Vine first. Put it back on speaker view. Elzbieta, would you like to go, ma'am? Oh, you're muted. I'm sorry. I'm going to ask you to unmute. Okay, and I'll allow.
Hello. Yes. Hello. Thank you very much, Mike. That was really great presentation and a very great machine you built. Well done. I just have one question. How fast was the disk rotating in your machine?
Well, first of all, I'll say it wasn't a disk. But it was maximum of about 200 reps.
Okay, maximum, but you didn't have a way of like measuring or?
No.
Because it's
As I say, I'm
interesting
a very-
if you were to spin it faster or rotate it faster, whether it would go faster.
It would go faster, but I am at the limits of what I can do in terms of finance and development. I mean, the machine you see was built on the table it was demonstrated on, which is my dining room table. It's something, I'm a retired engineer, so I no longer have a workshop. So anything I've done, I've built literally on the dining room table. I could make it go faster, I could go on and on and on. But once I established the principle of the function, which is the main thing, I knew it is now out of my hands, or should be taken out of my hands, because it needs a great deal of resources and a great deal of thinking behind it to develop it. I made an analogy before in saying that it was like the jet engine. Frank Whittle, the originator of the jet engine, only took his invention to a couple of pounds of thrust, but he proved the principle. And then he took the rest of the world to take hold of that principle and develop it. Working out, I'm not a mathematician. I could work out the revs and various other things and work out what speed it'll go at it, what revs it goes at, but that's not what I'm about. I was about creating a machine that worked and the principle of that working. And then that principle needs to be passed over to the world and everybody else because it needs the collective thinking of lots and lots of people. There's innumerable ways I can think to make it go faster now. There's any number of ways. I mean, if somebody takes it up, I'm very happy to keep involved in the machine and tell them how they can do it and how they can make it go faster. And once they understand how it actually works, they can then think of developing or engineering it up to provide a lot more thrust and power. But that's the main thing, knowing how it works. With an awful lot of things, people say, oh, that's strange, that's an unusual thing. And, oh, but that's no good. And unless you actually take the strange and unusual thing and you actually find out what's making it tick, you can't improve it or develop it. Now, I know what makes it tick now. So I can pass that knowledge on to people with lots of money and lots of brain power, lots of engineering brain power, to take that little engine that I've created and turn it into something wonderful. I mean, that particular engine will provide ship's power. It will provide power without propellers, without the fouling of propellers, without a rudder even. Which just on a simplistic viewpoint will save ship owners millions in terms of damage to ships and maintenance alone. So it would provide power to a ship. It would provide power to a vehicle, motor vehicle, without transmission. But most importantly of all, I mean, my raison d'etre was that it should provide power to a ship in space. I mean, currently, the likes of NASA, they have, ion drive and plasma drives, but they require enormous amounts of fuel, and the power that they generate is equivalent, from what I've read, is equivalent to the waft of a budgie's wing, which is practically immeasurable. Now, what I have there is a very crude prototype machine that's demonstratively creating five pounds of thrust, which is probably several thousand times more powerful than what NASA are using now with ion and plasma drives. So,
yeah, thank you so much. Yeah,
does that answer your question, or?
Oh yes, yes, and I really hope you will go your way, and then that will be all worked on by those with lots of money and resources, and then we will know more. But there is one more question that came to my mind: is that if you were to make it heavier or lighter, how will that change? How it works. Say if you will make it heavier, double the weight, will it be harder to get it moving? Will it go faster, slower? What would happen?
No, it's if it was used in space, it would be irrelevant. it would only matter where gravity existed. I mean, if I made it lighter, it'll go a little bit faster than you've seen there. If I increased the motor power, it would go faster. If I made the drive itself bigger, it would go faster. But that again it's where I stop. I've had to stop now. I've spent years establishing the principle, and once I've established the principle, I believe I've gone as far as I can now. The principle is there. It's down to everybody else to develop it up off that. But certainly from a spaceship point of view, the weight of the engine is not relevant. The drive will be the drive. The engine weighs 1,000 tons and it's produced 1,000 tons of thrust. It really doesn't matter in space. But if you put the engine on a ship on Earth, then it maybe will go a bit slower, obviously. But,
thank you. So you would be interesting to know what force drives it.
Well, that I would think will be told to somebody who's going to give me some books and some support. The force that drives it is within the unit, and that is the secret. I've demonstrated basically everything else to show that there's no sort of ulterior force and there's no ulterior motive, because I've seen lots and lots of those, and you've only got to look at YouTube and you'll see loads of them. And when you've worked on such a drive for so long as I have, you can look at those and you can say, I know why that's doing that, and it's not because it's creating linear thrust, it's because of, and you can explain it. But you've got to have really studied it and worked on those things for some years before you understand it's not true. And an awful lot of them, they're covered up. So you don't see the reality of it. I've seen, I won't go into detail and I won't mention various drives and so on, but I've seen various drives that have been acclaimed on YouTube and various other parts, and I know that they don't work because I've done them 30 years ago. That's all part of my development and build up to what I've got now. I've done a lot of these things years and years ago and discounted them because I am my own hardest critic. I will not stop until I have an explainable reason why something is happening. Because only when you get to that stage can you actually make it better. And with that unit, I believe I've reached that stage.
Yeah.
Well done. Thank you.
And Elzbieta, thank you, ma'am. Let me go to Morgan next. And again, we're running ahead of schedule. So I think what I'm going to do is go to Michael McDonnough probably at about 1 p.m. So that gives us about 20 minutes left for questions, if that works. So let me go to Morgan Lynch next. Sir?
Okay, yeah, hi, Tim. Thanks for the wonderful presentation, Mike. Just a quick question. I wanted to see if you ever just took the device, so you had it turned on where it scoots to the left. Can you ever just take the device and just hang it from a scale, or just put it on a scale and turn it on to see if you get weight reduction in that respect? Have you done this experiment?
I've done bits and pieces like that, but it's difficult to explain. If you hang it, you would have to hang it on quite a long thread, because what you will get, if you notice, the linear forces are being created by the rotational forces. And the rotational forces, once they go off vertical, will tend to push against each other. So you have to have a long thread, and yes, I've done that, and it'll move this and so on. One of the next things I was going to do was actually do it on a lift mechanism as well. But I really don't feel the need to do that, quite frankly, because there's reasons why that won't work, or it will work, or it won't work properly. So I can't say I have done that, no.
Oh, because just my one concern is if it's like a friction type thing. Is this similar? There's someone posted a link for the YouTube video of this lathe weight experiment. Is the actual mechanism on the inside similar to this, where you have a rapidly spinning disc on a barbell that's rotating around?
No, it's obviously I'm not going to answer questions regarding what's on the inside. But when you're saying a rotating disc spinning round. Strange you should say that. The first machine I ever made over 35 years ago was something like that. But the rotating disc I found was not necessary.
I see. Cool. Thank you.
Okay, and thank you, Morgan. Okay, so let me go to Detlef Hoyer next. Detlef, go for it, sir.
Hello, and thank you for the presentation. Just a short question. Are you able to reverse this thrust, perhaps by inverting the rotation? So it moves from left to right instead of from right to left in the video.
And Mike, were you able to hear him okay?
No, I heard nothing.
Oh, okay. I'm sorry. Yeah, his voice was a little faint. He was wondering if you were able to reverse that so that it moves from, if you reverse the rotation, would it move from left to right instead of right to left?
No.
Okay.
No, for steerage, you can move the whole machine. It doesn't matter. No, reversing rotation won't make a difference.
Okay, wonderful. Let me go to Robert next. Sir?
Right. Mike, can you hear me?
Yeah, I can hear you.
I was just curious. Any other knowledge besides gyroscopes did you apply to develop this device?
Well, mainly rotational forces. But, I mean, rotational forces are basically all encompassed in gyroscopic forces. But I can say it's using gyroscopic forces to actually convert from rotary to linear thrust. But gyroscopic forces are rotary forces. So, to me, the two are one and the same.
But any other knowledge did you apply? Like,
well, there are other things contained within the unit that are responsible for the conversion. But at this stage, I really can't go into those without divulging too much.
Oh, okay.
It's, let's say, material science. I'll just say that. There's a degree of material science.
I see. Thank you.
Okay.
Well, Robert, thank you as well. Okay, so let's go to, let me see. I think, Lulu, you had a, let me see. And if I, again, Lulu, if I could ask you to get your camera on.
Yes. Yes, hi. I had different questions. You know, you're saying linear force, and, you know, with linear force, it means it has to be exact, 1-to-1 ratios. I mean, you cannot achieve linear force unless it's 1-to-1 ratios.
I don't understand your question, Lulu.
Your equation to have lift force, you need variables, but linear force is 1-to-1 equation to be achieved.
Well, you've seen the video. You see linear force is totaling 5 pounds. That's all I can say. I do not understand your 1-to-1 equation. The linear force.
1-to-1 equation of oscillation. 1-to-1. That's how you have perpetual lift. 1-to-1, 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 1-to-1.
Well, that's news to me.
That's, you know.
I don't, as I say, I don't understand the question.
It's simplified.
Yeah.
So these hard equations, it's just one equation.
Well, you can see the linear force. Oh, my internet connection is unsafe. You can see the linear force being created from the rotational force. The 1-to-1 equation, I don't know.
Yeah, Lulu, it could just be the way that you're expressing it. I
know what I'm talking about. But,
no, I mean, it's just not communicating. I think that might be just not communicating that well. But because I'm kind of the same way. I kind of feel where you're going with it, but I don't fully get it. Let me go back to
mathematics is a cryptograph of imaging. You can only achieve a visual unless you cover certain like thoughts, perspectives, like you go from something into something, something. And, you know, that changes. It's just depending on the measurement. If it's not one-to-one oscillation for one to verify the other, then it does not, you know.
You are obviously talking theoretical maths.
No, our visible universe.
Yeah.
Well,
let me jump back to Detlef and
No, you guys are watching, but you guys are not learning, not understanding or expressing.
Detlef, let me jump back to you. And again, sorry, I'm bumping up our schedule a little bit, but so that I am trimming down our Q&A time.
I haven't been able to get in any signal.
I'm sorry.
Stu here. I just wanted to see if I could ask a question later as well.
Yes. Let me have you go right after Detlef. Sir?
Okay, what I wanted to ask is if you put the machine on the magnetic levitating table, would it work also? With no friction? It's like the translated, when you have a magnetic levitating table,
yes,
there's no friction.
Well,
it's like in space.
Yeah, I believe it would. You've seen the machine demonstrated put onto a tray on the table, and it's driving that along. Equally, if I was to float that tray on water, it would drive it on water. I have driven it on water, actually.
On what?
On water.
On water,
it's on
okay.
a flotation unit,
yes.
And it's moved. And it will move as I've not filmed that. But yes.
Yes, it would be very interesting if you will have a video of it.
No, well, again.
Water. Oh, your picture is frozen.
You know, Detlef, well, if I can jump.
The fact, well, I'm just saying. To employ that friction, even if it was friction, it is still moving in a designated direction. Random vibration or uncontrolled vibration does not move in a given direction. So even if it is an element.
Oh, and we're losing.
And also, if you put it if on the tray that you've seen it on, the tray itself is being pushed along, and it's not friction. It's not holding on friction. The tray is moving with the unit driving it.
Okay. So let me. Thank you, Detlef. Let me jump to Hugh. Hugh, go for it, sir, and welcome back.
First of all, congratulations on a wonderful system. I've also used some inertial propulsion systems myself, and the problem I found was that they tended to go backwards a bit, sort of 2 steps forward for 1 step back, and they were sort of jittering. Another guy in this area is Stephen Hampton. You probably have seen him on inertialpropulsion.com. I find his ones are also a bit jerky, but yours was beautiful and smooth. So you must have overcome some of the problems in some of these other rotation to linear impulse systems where you're getting all this sort of jittering action. Yours was nice and smooth. I presume you have there's some trick there, but also I know why you're not you don't want to go vertical, because I appreciate that, because in some of my systems, I either had to build them for vertical or build them for horizontal, because they become too unstable if you tilt them upwards. with the rotator. And I did actually get briefly some levitation with one of them, but it was so shaky, it was impossible. Maybe if you did a dedicated vertical one of your systems, you could get it to go more smoothly upwards. But it would have to be built, I think, to go upwards.
Well, yeah, I appreciate what you're saying. Unfortunately, I can't explain to you at this stage how it actually does it. I think the main thing is a friction, if you like, and they can only work when they don't know what is actually making it work. Now, I can demonstrate. If I was to open the unit up and say to you exactly how it is doing it, you will go, ah, yes, of course. And it is mechanical, it's purely engineering. There is nothing Foo Fighter technology in it. It's purely mechanical, purely engineered. It has to work, and you will see evidence inside of it actually working, actually converting. I mean, what it's doing essentially is converting rotational forces into linear force.
Right.
I can explain to a zenith exactly why it's doing it, and I can show you the inside and show you the reaction it's having inside and how it's happening, and you will fully understand. I can make it. I've made it jerky to take out a little bit of the weight and make it jump up a little bit, so that the linear force being created is more demonstrable.
Yeah, I think I saw that in one of your videos. It jumped. It was going a bit upwards.
Yeah. It jumps up a little bit, but that is only to sort of take a little bit of weight out of it so that the linear force that's being produced can be demonstrated. You can see the drive more effectively. I could adjust the machine so it doesn't jump up, but I wouldn't get anywhere near, because of the gravity inertia, I wouldn't get anywhere near the speed I'm getting along the ground to demonstrate the inertia propulsion. So I adjusted it to jump a little bit and demonstrate the inertia propulsion that's being created. Now, I could open the machine up and show you exactly why that force is being created within the frame of reference.
Right, yeah. I'm sure that you could, if you were given millions of pounds or dollars or euros, you could develop that into a vertical thruster.
I could develop it now as a vertical sculpture, but I'm 76 years old. It's not millions I need, it's years. If someone could pay me in some years, I'll carry on. But I'm 76 years old now, so I don't have the time anymore. And I've gone as far as I want to go. I believe the machine needs to be taken into the realm of the public now, and it needs to be developed as a machine, an all-purpose machine for whatever.
Thank you very much.
Okay.
Yes, absolutely. And thank you as well. Okay, and let me see. Let me go back to Robert, sir.
Thanks, Tim. I have just one, I think it's a short question, Mike. Do you know anybody who has been closer to trying to repeat Lathwaite's so-called barbell machine that could just lift up with one hand, whereas if it was shut off, it would weigh a ton?
I don't, but I think I know why it doesn't weigh. I know what, because it's on a directional plane, and a directional plane is acting against gravity. So when he's holding the bar, the directional plane will not allow it to drop, because it's if you like, My problem is I can think three-dimensionally, but I can't talk three-dimensionally. I can understand why it happens, but I cannot explain it fully. I cannot explain it in a coherent manner. The barbell itself is spinning on the end, and it won't drop down because it's creating forces top and bottom of the rotation. It's stopping it falling. So while you've got hold of the bar, and you are holding that bar and allowing the gyro to precess, as soon as you stop the precessional force, that will drop. It will get its weight and it will drop. Right. You've got to keep moving around in precessional force and it will stay up. That is one of the sort of enigmas and one of the things that fascinated me about gyroscopic and rotational forces.
Right. Me too. Yeah.
The anomalies created by them. And it's these anomalies that I've used in that unit. I will put it this way, I've used collectively in that unit, there is rotational force, there is recoilless centrifugal force, there is rotational force, and there is precessional force.
Right.
And they're all acting well. I've gone too far on that, but you know, but it's a combination, and if you like, amalgamation of rotational forces and gyroscopic force.
Sure. Yeah. That's why I specified gyroscopic, because that's all I can think of that life weight applied, other than what you mentioned about material size. But the forces must, as you said, must have been vertical. I mean, that's obvious.
Well, yeah, the forces are acting against each other from the center downwards. You've got the top of the rotation is reacting and the bottom of the reacting, and they're reacting in opposites to each other. So basically they become practically weightless as long as they're precessional. Now, as soon as you stop the precession, the weight comes down, or you stop the spinning, the weight's there. There's nothing rotating and moving, if you like, moving the center of gravity or the mass, altering the mass. So the thing drops down.
I've made a simple model in SolidWorks, a 3D model. So if you're interested in looking at it, I can. It's a simple diagram you can see in any gyroscopic book. But I'm sure you've seen it, of all the vector forces on a rotating flywheel.
Yeah. Well, guys, we're just about out of time. Bernie, I'm sorry, I had to put your hand down. In this case, we have to go back. Let me go back to gallery view, and everyone, please give Mike an enormous hand once again for a wonderful presentation. And we are, again, we're running a little bit ahead of schedule now. We were behind schedule before, we're ahead of schedule now. So what I'm gonna do is, at the top of the hour, Michael McDonnough has joined us, actually. And so what I wanna do is give him an introduction. Michael McDonnough will be discussing a device that utilizes a sacrificial anode, which is eroded into a self-compressing plasma vortex to create a low energy nuclear reaction. It's a type of fusion that can be used for energy generation. He'll be discussing the method of operation, test results from past experiments, and possible methods of propulsion based on this technology. So most of you probably aren't familiar with Michael McDonnough. I've known Michael for probably 17 years now. He used to have a startup company that was working with a lot of these technologies. And so he is a wonderful and brilliant man. I'm so appreciative that Michael joined us. So Bernie, I'm going to put your hand down, and let me see. Michael, I think that we have you with us. I will spotlight you, sir. And
how's everyone?
Doing well, and thank you for joining us.
Do you have my slides ready, or do I need to do it? Or
what would you like to do it? Do you want to do it as a screen share?
I haven't actually used this type of interface before for that purpose.
So what I would are you on a PC or iPad? Oh, Michael, you just muted yourself. hold on just a moment.
Unmute. Okay.
Okay, yeah. You said you're on an iPad?
No, I'm on a cell phone.
Oh, okay. Yes, let me do that. Let me pull your slides down then. Yeah, the cell phone would not work for that.
It's kind of a one-trick pony cell phone anyway.
Yeah. Okay, so edited slides, and I'm gonna bring these down. Okay, so I haven't done this in a little while, but let me do this. I'm gonna share my screen. I'm gonna put it on Plasma Vortex Fusion. And hopefully, can you guys see this okay in Zoom?
I can see it. It's not perfect, but
you know what?
Seeable. If you put it into what do you call it, mode? There you go.
Yeah, now it's full screen mode. Okay, so yeah, hopefully this is recording okay.
All right, I'm going to go ahead and just say it because you're recording it.
Yes, sir.
Hydrogen plasma vortex induced light metal nucleonic reactor propulsion. In the system described, a hydrogen plasma vortex is created in a vacuum chamber as hydrogen gas is fed into it. The resulting pressure gradient of gas volume forms the suction head at the anode site, causing the metals to boil off and fuse, releasing energy and fusion-produced ions, which are drawn off and used. In this work, a nuclear chemical process is recreated from cosmogenic observations in the experimental device presented on slide 2. And the initiation of hydrogen plasma vortex as it ablates the light metal anode under conditions of high voltage, low frequency, low temperature, a protium-containing non-equilibrium plasma, specifically a lithium, beryllium, and boron-containing magnesium aluminum anode is ablated. The reaction area is surrounded by an inductive coil, and added conductive elements are placed in order to shape the resulting E field to induce the vortex to compress at the anode site. As the gas and energy are released, the suction head moves about the anode, continuing the reaction until the anode is ablated and the fusion products move to the cathode. And you can go ahead and go to the second slide. All right, in the second slide here, as you can see, at the top, the silver cathode, it's what you see just at the very top of in the center of that image. It's made out of like a silver coin in this particular instance, but it's shaped in kind of a vortex shape, which helps to create the initial vortex stream of energy to flow down the cylinder that you see here. And that hydrogen plasma vortex is what you see that is kind of a violet color. That's the hydrogen plasma vortex. The reddish colored material around it, that's a solenoid wound coil that wraps around the vortex chamber, and that reacts to the plasma and generates an electrical current, which tends to squeeze the vortex down toward the anode. The anode at the bottom is where you see the bright flare on the arrow that says fusion. That is the light metal anode, and the important elements in it are the beryllium, boron, and lithium, which I'll explain later. In this particular prototype, which I still have in my possession, it used a 20 kilovolt electrical transformer, like typical for a neon transformer, and it used a 60 cycle square wave input, and it was only using 40 watts. It was tested in a thermal bottle type of device, which looks for the amount of heat increase, and with a 40 watt 12 volt input, we were getting 280 watts of total heat energy output. So 7 times over unity for a 24-hour period while it was being run within the the thermal chamber. Visible light energy was not tested, so it achieved 7 times over unity without even measuring the visible light that was produced by the plasma. So in my consideration, that generated nuclear level events within the plasma. Go ahead and go to the next. This is a WIPO patent image, World Intellectual Property Organization, of the plasma vortex chamber that you just saw in the previous slide. It basically just shows an outline of the elements that are involved, the coil in the center, and the anode and the cathode on either end of the tube, and his placement of the hydrogen bottle and all the other components of it. Go to the next slide. Yeah, there you go. This shows the plasma vortex flow schematic. In the top element, the hydrogen is induced into the reaction chamber. On the lower level, you see the plasma form between the cathode and the anode, and in this particular instance, the anode is hollow, which allows the gas to pass through. And this is just kind of a typical representation of a plasma vortex going through a tube. I just use that for demonstration purposes. Go to the next slide. The other direction, your other direction. Thank you, sir. This is the 3D layout of plasma vortex drive. This is my initial form, my preferred embodiment of the engine. On the left side of the screen, you see what is the ejector site. This is the hollow sacrificial anode, which is shown in the colored area. The areas that are gray, those are basically made out of Maycore ceramic, which is it's as strong as steel, but it's a machinable ceramic, which I've already purchased. I intend to take the material that I have already invested in the initial prototype and split that down into 4 of these tubes, which will be designed to go into like a 6U type satellite, satellite configuration, so that we can test them in space. And I'll be looking for some funding for that. Go to the next slide. In this one, I'm showing what most people don't understand when they're looking at, say, for instance, a tornado, or in the case of this plasma vortex that you saw in the cylinder, is it's actually a toroid. When we look at a vortex, we see the vortex, but what you're actually seeing is the area that's down toward the center of this, and in the center, that area is what's visible on a tornado. And the same thing with the plasma vortex you saw in the tube. What you don't see is the outer part of the toroid. And in the bottle that you saw in the second image, that coil acts to flatten out and compress what is naturally this rather stretched out toroid shape, which is what you're actually looking at when you see a toroid, or in this instance a tornado. Go to the next slide.
You can be a little bad with it because it's going to be right in the very.
All right, in this slide, you see toward the left,
maybe we can use a little black.
Hydrogen and helium. This is the abundance curve of elements that are in the observable universe. You see right after helium, lithium, beryllium, and boron. There's a deep dive down in the abundance curve. There's a reason for that. And Ari Gas, among other scientists, found out that the reason that there's this massive dip in the abundance curve is that all of these other elements that are in the second area that starts with carbon and nitrogen and oxygen, those are formed in the toroidal vortexes that surround the star. Stars are formed by helium and hydrogen being compressed into lithium, beryllium, and boron. The lithium, beryllium, and boron, actually, as it is formed in the star, form at a much lower energy level in the corona of the star, in the vortex filaments that surround the coronosphere of the star. All of them that you see from basically from carbon to nickel and copper, those are the ones that are produced in the toroidal vortexes in the surrounding area of a star, and also in every other sort of vortex type of plasma filament in the universe that generates all of the heavier elements. So what Arie de Geus has discovered, and what we're going to be utilizing for star drives eventually, is being able to use that low energy nuclear reaction of lithium, beryllium, and boron, and forms the heavier elements that are on the periodic table to power our star drives. And because of the Schwarzschild, what do you call it? The right term, the
Schwarzschild radius or metric?
No, not the metric. The Megas effect. There's a Schwarzschild Megas effect. The Megas effect is what causes the low energy nuclear reactions. The spinning of the vortex, the apex of the vortex, where it strikes the elements that are being fused, that vortex, that compressed area, there's a Schwarzschild Megas effect at the rim of the vortex, and that's what causes the low energy nuclear reactions. It's because you've got all of the electrons on one side, all of the protons on the other side, and they're flattened out at a extreme angle at that place, and that creates a collapse in the Coulomb barrier, which is why you're able to have these low energy nuclear reactions at amounts of energy that are unexpected. You know, when we look at fusion reactions, we're looking at helium-helium reactions, or helium-hydrogen, or one of these, helium, hydrogen, lithium, the very low end. Those reactions actually require a lot more energy than beryllium and boron. The lithium is a little bit less, but the beryllium is the lowest, and the boron is the next to the lowest as far as the amount of energy that is required for it to fuse into the heavier elements on the periodic table. Go to the next slide. On this one, I'm just basically showing that and I did change that powerful to 1L anyway. The vortex is the most powerful force in the universe. All matter is formed in vortexes. Photon geometry demonstrates vortexes. All atomic structure are toroidal shape. Everything in the universe is toroid. Everything down to the atomic level, all the way up to the universe, and everything in between. And that's my presentation.
Okay. So let me do this then. Let me stop sharing. Okay, and so actually that was really fast, Michael, but thank you. So let me go into the Q&A session. And I know, again, you and I talked about this for many, many years. You know what, here, I'm going to remove spotlight. That way we'll go back to normal. You and I talked about this off and on for many years. So one thing, let me ask, you actually did testing and you had results. You had fusion reaction products, if I understand right.
Yeah, we have the mass spectroscopy imaging that we got from the University of South Carolina that showed the K40 potassium 40 spike, which volumetrically was 98% of the sample, which means of the scrapings off the cathode, a little bit was silver, a little bit was silica, boron, other things you'd expect inside of a glass cylinder. But 98% of what we scraped off the cathode was pure potassium-40 isotope, which is impossible. You can't buy that. You can't buy 100% potassium-40 isotope anywhere on the planet. You just can't. It's normally 0.00019% of all potassium on the planet is potassium-40 isotope, and that was produced in the vortex ring of a supernova billions of years ago, somewhere probably in our galaxy. And it got here by supernova. It was brought here by the galactic wind, and that's how we got the potassium-40 that's on this planet, except for what was produced by this device. The stuff that's produced on this device is brand new, 100% pure synthesized potassium-40 isotope, which is impossible any other way other than low energy nuclear reaction to create newly synthesized potassium-40.
Awesome. Thank you for sharing that. That's it. And I remember bits and pieces. We talked about this for several months, like again, probably 15 years ago, 17 years ago. And so very scouting on it. But
it was a situation where, I was working to try to find something with beta voltaic that would make it where we could, like nowadays, they have a beta voltaic that's getting some funding, which is interesting because they're doing a system that I actually envisioned, decades ago, but wasn't possible then. Now it is, of course, and so now it's doable. But in that technology, we were looking for something that was doable now, at that point. And with the information that I got, it showed the low energy nuclear reactions that, to me, 7 times over unity, that's verifiable in an independent lab result, and nuclear products which cannot be any other way produced other than what has been described, what has been shown to us. I mean, it wasn't even humanly possible to have potassium-40 of that purity anywhere on the planet. So that was evidence, all we need, that, I had a good investment going. Problem was, the investors, and that story. Basically, they decided they wanted to have, new Firebirds and fancy cars and stuff instead of, giving the money to the people who would actually be making prototypes and making money for them.
yeah. Well, so let me do this. Let me go to Phil Bouchard first. Phil, I like your shirt. I like the band. Oh, and you know what? Hold on. Sorry. Let me allow participants to unmute themselves, and I'll ask you to unmute over the hand. There we go.
All right, thanks, Tim. Sorry, I'm not really prepared. I look like Einstein with my hair right now. Spiky hair. I just wanted to say that it's very interesting presentation. We're doing, as you know, research on the gravitomagnetic force, and all that is required is the spinning ions. We're looking into cyclotrons, tokamak, and things like that, and your device looks perfect, I think. So is it possible to have a device of yours with just continuously spinning ions in it?
Yeah, it's the plasma vortex will continuously decompose the solid metal anode, and the anode can be moved up into the plasma chamber through something that essentially moves the rod, or the cylinder in this instance, into the chamber as the reactive material is decomposed or ablated. It's super efficient. The amount of hydrogen that we were seeing produced in the prototype was remarkable. It was beyond what you could even calculate for like partial decomposition into other fusion products of hydrogen, like as an excess molecule from two different metals being, fused together, and then an excess hydrogen being knocked loose. It was difficult to explain where the extra hydrogen comes from. That was one of the reasons that I started looking into the Schwarzschild Magus effect, is that with the Magus effect, if you're familiar with that, like a spinning ball, if you throw a ball and you spin it down a mountainside, it will float away from the ground. You know what I'm talking about?
Yeah.
That's the Magus effect. A spinning object is repelled or pushed. It gets it moves away from the area that is spinning. Unless you rotate it the opposite direction, then it acts like a suction, and it is compressed towards what it's spinning near. So in one direction, Magus effect has an attractive force. The other direction has a repelling force. And in this instance, the Magus effect has an attracting force in the suction head of the plasma vortex. That's why it will collapse the Coulomb barrier, which is supposedly the strongest thing there is. Well, it's not stronger than the Magus effect from the Schwarzschild metric that is produced by a vortex. The vortex is infinitely compressible because the vacuum of space is infinitely compressible. I don't know if you're familiar with Nassim Haramein and his work. Nassim Haramein is his cosmological representation is very similar to my cosmology. He believes that the universe is toroid shape, and that the universe is basically the galaxies on the outside of this toroid, and that it goes toward the center. There's a big bang, and then at the top, and then it goes. The universe goes around, and then it is recycled over and over again. Anyway, that's Resonance Foundation. That's part of his thing. But in it, they discuss the Schwarzschild Magus effect as being what gives us the ability to use black holes for moving from one part of the universe to another, like star travel. And so this plasma vortex technology, even though we're doing it on a micro scale, we'll be able to. Now we have instruments we didn't have 15 years ago when I first investigated this. We'll be able to detect things on a level that we couldn't possibly do before. And if it's correct, and what I'm thinking is correct, what's happening is something like a mini black hole or a wormhole opening up, and quasi-particles, which are basically a particle, half the particle from this universe, half of the particle from the anti-universe, combining to form real matter, like a negative and a positive quasi-particle becoming a real particle. I don't know if that makes any sense. That's the best I can describe it, though.
Yeah, but I would definitely be interested to measure the gravito-magnetic force that it generates.
Hey guys, if you can give me 2 seconds, I have to use the restroom really bad, so I'll be right back.
I'll do that.
Okay.
You don't get any younger.
Yeah. So, is your device is it like stable, robust, and everything?
Yeah. So long as the pressure gradient remains in the tube, it will continue to create a vortex. You have a pressure gradient caused by the two elements, which are the sacrificial anode is composed of electronegative material. In this instance, the carrier is aluminum and magnesium. The target elements at the erosion site are the beryllium, primarily with lithium and boron, but the beryllium is the primary thing that's decomposed in the plasma vortex. And beryllium is it has a fantastic neutron absorption cross section. That's why beryllium is able to be converted directly into like boron, and boron has an extra. It has a extra neutron in a reverse order of a normal neutron, so it works like a suction head for the next thing. That's why boron is so easy to fuse with hydrogen. You know, you get a hydrogen boron reaction to create 2 helium very easily. You know, I don't know if you've done any research into fusion physics, but especially aneutronic fusion physics has been my real specialty area, because that's where I saw, you know, unless we could figure out free energy, which, you know, I'd love to have that. Right now, I'm looking at, you know, how can I have fusion energy, you know, so I have, you know, nuclear level energy in a very small device.
Have you heard about CFS.energy? They have a CFS.energy. They have a small tokamak shape. Apparently, they create more energy. They have more energy in output than it requires to, you know, to feed the as input. So they kind of creates energy. They're still in a.
Well, technically, the plasma vortex has 7 times over unity in the unit that I tested, and that was not an optimized system. Literally, that means that in this instance, 40 watts of energy went in, 40 watts of DC electric 12 volt went in, and 280 watts of heat, thermal energy came out. So technically, 7 times over unity. 40 watts of energy went in, 280 watts of thermal energy came out. If you'd done a direct, like, you know, if you took a thermal element and just, you know, heated it up with 12 volts and 40 watts, it would have produced 40 watts of energy, you know, if it was 100% efficient, which it's not going to be, obviously. Yeah, but for this to produce 280 watts of energy with 40 watts of input, that demonstrates 7 times over unity, which is really good considering how inefficient the whole thing was. I mean, it wasn't even designed to be efficient, but that demonstrates nuclear level events that are happening similar to like Pons-Fleischmann, you know, cold energy, you know, cold fusion stuff. They didn't detect, I mean, they weren't able to harness that as a usable amount of energy. They could demonstrate it. You know, they put in X amount and they get out X amount in the same way that we tested this unit. Just like with the cold fusion with Pons-Fleischmann, there's anomalous heat produced. The anomalous heat is usable, but in the instance of like with Ari Degas and his technology that we were licensing, he didn't get that world patent, you know, that I showed in the image on the presentation. That world patent, the World Patent Authority did not give him that patent. They said that it had no utility. And technically, as far as the patent office is concerned, it had no utility. In other words, being able to produce 7 times over unity heat doesn't mean anything. It doesn't give you anything. You see what I'm saying? I mean, it's not like closing the loop. Closing the loop is a whole lot harder than just generating an anomalous amount of energy. Yeah. Producing an anomalous amount of energy it shows you that something's happening worth looking at. Yeah. But as far as being able to use that, to be able to put it to work, you know, to be able to make a machine that will make something happen, it's a different story. And, you know, having even 7 times, that's 700% over unity. it's still not enough to close the loop. You know, it takes a lot because there's so much loss. When you transfer energy from when you up or down the voltage, when you up or down the amperage, you know, when you change the frequency, you know, when you change the shape of a waveform of a light pattern, you change the energy, you scatter it or you focus it. You know what I'm saying?
Yeah.
It's like with a lens. A lens can scatter it, can scatter energy, or it can focus it to a tiny beam. And if that's usable, then it's useful. You know, if you can focus it to a point and your energy can do some work, now you can get a patent and you can make some money. But that's the way it is in the world. It's like you don't get a patent for something that's interesting. You get a patent for something that can be put to work. It can make some money for somebody.
Well,
You know what I'm
Michael,
saying?
if I could jump in really quick.
Sure.
As I recall, you were working on a way to extract electrical energy from it. Is that correct?
Yeah. What we were looking at was the energy from the plasma itself that is detectable in the solenoid wound coil. Now, the inventor, Ari Degas, said that the coil was there to gain a charge, you know, to induce, it was inductive, it was inducing a charge from the plasma. And then that created like a prolapse of energy back against the vortex itself, which compressed the vortex and, you know, caused it to focus on the apex of the chamber, you know, to be able to erode the sacrificial anode. So we weren't tapping that. He wasn't interested in tapping that directly. My question to him was, if you're using that energy, why can't we use some of that also? And he was like, well, untapped, it is able to hold a charge, and that charge, because it's not tapped, acts like a choke. Does that make sense?
Yeah.
As soon as you tap that coil, you pull the energy off that coil, you reduce the size and of the electrical area, you know, the energy area around the coil is reduced as the energy flows out of the coil. If it's kept in the coil, we can detect it, we can measure it, but it also stays there. The energy stays there, and it serves to compress the energy in the plasma to the point of focus on the anode. Does that make sense?
Yeah. I'll need to review all that, but I don't want to block the others. But do you have a website or a way to communicate, an email address?
Yeah, Tim has all my information.
Yeah, and you know what? I actually let me paste that in chat right now. So let me do this. Phil, thank you, sir. Let me go to Bernie next. Bernie.
Thank you. Just like to say that's amazing work, Michael. I do some electrolysis experiments myself, and wondering how often you encounter self-organizing sort of features in the results of the anode, as well as any precipitates and particles that form out of the fusion.
Mostly the fusion products are attracted to the cathode. The anode displays eroding behavior, which can become polymer, like from the erosion site. We looked at the pitting at the erosion sites on the anode, and it showed nuclear level of events in STM imaging, and I have that data still. That it created some filaments, it was kind of odd looking. When you do a close-up SEM of the places on the anode where the plasma vortex would erode it, you'll see filament buildup going upward toward the cathode, which is basically just the boiled off elements in their in their various states of, being boiled off and fused in the little, like the eddy currents, the edge currents of the vortex, as it's going in and out of the little lip curl, on the vortex itself.
Nice. That's awesome. In my personal experiments, I often notice what seem to be nanotubes forming, as well as constant vortexes in the water between what Gerald Pollack calls the easy zone, the exclusion zones, and there'll be like an inch full of nanomaterial and then an inch of just clear water, followed by another inch of particles, followed by clear water. And in the structure, there always seem to be forming these vortexes spinning into the center of each other. It's quite fascinating. So it's cool to hear similar sorts of...
you would see that, because the, bubbles form in a column. They don't form individually, and that bubble column is going to create like the little dendrites, little dendrils. As the bubbles come up, they'll form little dendrils of solid material, which will ablate or plate out of solution and form into like cylinders, like you're describing. In a vacuum, it's really interesting because you get really long filament, and I can just imagine. I would love to do the same experiments, and I'm going to. One of the things we're going to do is I'm going to take the material from the that first device that you saw in the images. I still have that. I'm going to divide that anode material down into quite a few, at least 4, maybe 6 devices, smaller devices, and that way I've got for sure. I mean, I've already got the anode sampled, so I can reproduce it. But I want to use the actual anode for my spacecraft. I'm planning on producing a 6U satellite, for testing these engines. I'd like to do one of them initially with, borosilicate glass for the reaction chamber, and then I'll use the Maycore ceramic for all the other parts. But the ones that I use for space, I plan to do all 100% Maycore ceramic, all machined out of it, and then launch those into space. And I'd like to do 2 of them. That way I got at least some redundancy, and my aim is to do 2 in a 6U package, and have all the sensors I need, to be able to look at it in space and be able to measure not just the whatever micronewtons or whatever that it produces. I'd also like to be able to see how it acts, how the materials hold up in the space environment, because I've been doing a lot of research on that. And I think I can produce a pretty good high durability satellite engine using the plasma vortex technology. And it'll last for years. I mean, it'll have enough hydrogen reaction mass generated from that anode to last for a decade, in near Earth orbit easily. And the same thing goes for like a deep space mission. If I wanted to do a deep space mission, it would take a while to wind up in a small platform like that. But I think I could even get escape velocity from these things. It might take more than 2. It might take like 4.
Just quickly, have you ever looked into or heard of Walter Russell's work with the vacuum tube transmutations he was getting in his research with Bell Labs and Westinghouse back in the days with Nikola Tesla? Because it sounds like pretty similar style of experiments that from what he described as what you're doing with the cathode plasma vortex.
Yeah, I actually did a lot of initial reading on that back in the mid 1990s. I don't know about you guys, but I kind of was raised in libraries, When I was a kid, there wasn't such a thing as the internet. I was one of those people who lived in libraries for most of my life, and the internet freed me a laptop, and I was able to get out of the library, get out into the real world, and see other people. But yeah, I actually I moved to Dallas, Texas, years ago when I was doing research for my first book, the UFO Technology Hackers Manual. I moved to Dallas because I started a company, advanced research projects, like the government thing, Advanced Research Project Agency. Anyway, this is before I even thought about doing anything to try to show up on the internet. But anyway, advanced research projects, I did patent research for a couple of lawyers, and they would write patents for their client, and I would do the legwork. So I had to move to Dallas because the only way to get on and look at the patent archive was to go to the microfiche at the big public library in downtown Dallas. That was the closest one to me. And it was there when I was working for my company ARP, working for these lawyers doing patent research, that I started doing research on solid state drive systems. And that's when I came up with the UFO Technology Hackers Manual, because I started noticing that a lot of the artwork that I was looking at sure looked a lot like UFOs. And so I wrote that book, and I kind of become quasi-famous for those days. I went on sightings on the radio and X-Files, and I was on Tim's show, and Tim did a couple of interviews with me, and I started Beta Voltaic Industries Inc., and I've done a bunch of other small companies since then. It's basically just been me exploring, the edges of science. And I actually wrote a couple of science fiction books. I've got one of them up on the internet on Amazon called Quantum Fire Control. In Quantum Fire Control, I basically took most of my present ideas and compressed it into a short story, as though it got funded and I had the resources to actually see all these things happen. And so I wrote a fictional story about it, and it's pretty good. I've had a lot of good feedback from it, and it's up on Amazon for 99 cents for the first chapter.
I got homework now.
I wrote a couple more. What's that?
I've got more homework now. Another book to read. Bless your soul.
It's only 77 pages, but I crammed every idea that I had at the idea 2 years ago into that book, into that short story. And I wrote like 4 chapters. I'm like, for instance, this presentation, I had to send 3 copies of the presentation. I found errors in it all the way up to the last minute. And I hate sending anything with errors even to my editor. It's embarrassing. I'm like, oh, you genius. Look at that. You put 2 L's under control.
Well, and Michael, I should apologize. I think you kept sending me like final version. So I think I grabbed the wrong final version. But
I'm bad about that. It's just that's why I take forever to send anything. It's like I always find mistakes.
Is it called recursion?
What's that?
Is it a system that you've created? It's called recursion, where it's like embedment of a cryptograph or an image, in particular a digital image, and you vortex it any way you want. And you create that, space between the first visible solid and the second visible solid, unlimited amount of universes.
Well, we do live in a multiverse.
Right.
Okay, so let me do this. Let me go to Mr. Riken, who has been patiently waiting, and Will, go for it, sir.
I don't have anything particular to add to what's already been said, but I do have questions, and the questions are really very simple. have you published any academic papers, or have any academics that you have been working with publishing papers on your device or your work? And second, has Edward Storms ever commented on your work?
Who are we talking about here? Sorry, that was directed to me.
Yeah, that was for you, Michael. And Edward
Sorry.
Storms. Will, can you elaborate?
Dr. Storms is one of the preeminent researchers in LANR and even coined the name LANR. So I was, since that was in this presentation, I wanted to see if he's actually made any comments. I happen to know him.
Oh, okay.
Someone who we're discussing low energy nuclear reactions. Is that what you were saying?
Yeah, and I think he was wondering about Edward Storms as well. If he had any comments, if he'd approached him, or anything along those lines.
I haven't approached or discussed this with anyone for years. I've been doing for the last 10 years. I've been doing research into the carbon nanotechnology, and I've kind of grown away from the low energy nuclear reactions. I studied the low energy nuclear reaction area because we were looking for reasons for the anomalous heat that we were seeing in several of the technologies we tested for our company. And that's what, made me even start looking into it, because it was such a, I don't know what's a proper term. People didn't believe it, like with Pons Fleischmann. I mean, there was so little belief in it or acceptance of it. I wasn't in a position I could spend someone else's money and approach or get funding for things that didn't have some kind of verification of workability as far as something that could make somebody $1. I'm a big fan of sciences, of very basic sciences, even, especially the cutting edge stuff that doesn't have a lot of track record behind it. But anything that I'm going to show to investors, I've got to be able to explain it to them in a way that is going to make sense to them, and it shows that I've demonstrated that I've done enough research. I'm not going to portray some fraud on them, and take their money.
So that does mean that you have published works in the academic community. You mentioned that you were working with academics to get your data.
Yeah, in order to, I have an ability to see things on a level that is not material or physical. I can see things. I can leave everyone is pretty much stuck behind their eyeballs, right? Well, I'm not. I'm able to move my consciousness from one place to another. And in order to explain what I'm seeing at the subatomic level, I look for scientists which have demonstrated to me in their work that they are seeing things as I see them. And I'm seeing them physically, not mathematically. I don't have I had to learn the math in order to explain what I'm talking about to people who do know what they're talking about. And what I was trying to explain to them is what I see in my mind's eye, my capacity for being able to change the location of my consciousness to expand or contract to any level. I can go down to the subatomic or out to the multiverse, and by shifting my consciousness itself. And that is something that I've had to try to learn how to do. You know, how do I navigate this? So I look for people who have an understanding of something the way I see it, and then I learn the math and the science about what I'm seeing objectively through their eyes, because they're able to perceive it and communicate it at a level that they can talk to other people about it. And that's where I find myself in my life, and have for years, is, you know, I'm able to see things directly in the universe. Now, how do I explain it to everyone? Well, I have to find people who can also see things the way I do, but they have the capacity, they reason through, and now they can explain the things that they see in their mind that I see, and now we can share it with other people.
So other than the patent, there's no published works?
Well, Ari Degas has published, Tim, do you have all of his stuff? I think you guys...
You know, I would have to dig. Yeah, with,
okay, he has a fluidium mechanics, or he had some fancy way of saying it. But Ari M. Degas, it's a fluidium mechanics. He has a book and an introduction to a book, both of which are available online for free now, which costs a lot of money when I was buying them, you know, back in the day. But you know how it is nowadays with academic works. If somebody gets a copy of it, they're going to publish it somewhere.
And that contains your device?
The device is described in one of his published books.
I see. Okay,
and he did file for a world patent on it. He was rejected for the world patent. But I did show you in one of those slides was the world patent that he filed on that device.
Okay, thank you very much.
And thank you, Will. Okay, so let me see. So I think, was that it for hands that are raised? So we have just a few minutes left if we have any other questions. And again, we're running ahead of schedule, but that's cool. And we have Mike Gamble with us. Mike is up next. So let me see. Oh, David, go ahead, sir. And could I ask you to turn your camera on? There we go.
So thank you, Tim. Yeah, great talk, Michael. Thank you.
Oh, you know what, David? I'm sorry. Yeah, you might want to turn your camera off, actually, because you're here. Let me stop your video.
Can you hear me now?
I can. It looks like you're really low on bandwidth. Let's stop your video for a sec.
Yeah.
Try that now. I'm sorry.
Okay, sorry. Can you hear me now then?
Much better. Much better.
Yeah. Good. Thank you. Yeah, Michael, there was a person called Paulo Correa who was publishing in the 1990s with he was calling it a pulsed abnormal glow discharge reactor and claiming electrical energy obtained from plasma arc discharges. So is that a technology that you've had anything to do with, or is related to yours at all?
I recall that one, but it was related to the research into ball lightning, if I remember correctly. Is that the one you're talking about?
Yeah, it could well be. Yeah, they used high vacuum tubes with aluminium plate cathodes, and found that there was a particular negative resistance region of the arc discharge where they could obtain pulses or create pulses of electrical energy and achieved output exceeding input energy.
If I remember right, I've met and talked to Paulo Correa. Michael, I had thought that you were actually the person who introduced me to him, but maybe you just pointed me towards his stuff one day.
Yeah, I did. I recall that they were doing research into ball lightning, and one of the things that was interesting about ball lightning is that it persists longer than a normal discharge. And like a lightning, there's a discharge, and the amount of dissipation of the discharge is calculable directly. The amount of anomalous heat you get from ball lightning and the fact that it takes longer to discharge than is within normal calculations for lightning was one of the things that they were studying. Was why what is burning in this plasma that is generating a sort of a quasi ground state that's able to sustain the reaction longer than it would normally if it went straight to ground. You understand what I'm saying?
Yeah, I think so.
In ball lightning, why does it persist above the ground? What quasi ground is it consuming or hesitating from going to ground? And that I believe is electronegative elements which are within the plasma, which are essentially being consumed within the plasma. And as they become electropositive, like hydrogen, dissipating as energy through hydrogen, evolving as hydrogen. Probably hydrocarbons, like literally swamp gas,
Yeah.
Like a plasma from swamp gas. That's actually feasible. I mean, if you think about it, a methane plasma from a discharge of lightning being consumed by the energy from the plasma and as it decomposes into hydrogen.
Yeah. Okay.
And carbon dioxide.
Thank you. Yeah.
Yeah. So I think David. So I think we're all set there. I think we are. Again, we're almost at the top of the hour. And Michael, I want to thank you again for your time. Let me check in real quick and see if Mike Gamble wants to go. Mike? Okay. Do you want to do your presentation? Are you ready to do your presentation?
A little bit early, but no problem.
Yeah. Okay. Well, let me do this then. Let me do this. First and foremost, I want to put this thing back on gallery mode. Everyone, please give an enormous applause to Mr. Michael McDonnough. I had to beg and grovel to get Michael to present. It was sad and pitiful, but I am so overjoyed that he came and presented for us. Michael, I would love to have you back. You have so many different ideas, and you've done so much different research. So I would love to have you back in the future. If and when you have something else to focus on. Right now, let's introduce Mike Gamble. This is a man who needs no presentation. Mike has been here many times. So the differential CMG operation that Mike is going to present is a follow-up to his previous presentation, The History of Boeing CMGs, which was presented earlier at APEC. After presenting the history of Boeing CMGs at the Kofi conference, Tom Vallone actually encouraged Mike to build a small working demo model based on his past Boeing gyro work. So this presentation documents his initial year's research, fabrication, and testing of that first demo unit, and it is going to include his traditional in-depth mathematical system design and analysis. Mr. Gamble, welcome back. Let me hand things over to you, sir.
Okay, so we get screen share running here. Do I open the file first and then go to screen share, or screen share first?
Oh, I would open the file first.
Okay.
Yep, and then go to screen share, and you can just put it on the file.
Okay.
It'll let you screen share the window that it's in.
Yeah. Okay, last time I tried slideshow and it didn't work, but we'll try it again.
And let me see.
Yeah,
It's going to the other monitor. Yeah. Yeah, you're still in your main window. You're still in your PowerPoint window. Your slideshow is probably on your other monitor.
Well, I don't have another monitor, but okay, it doesn't.
2017.
Doesn't work, so we'll just stay right here then. We'll make this as big as possible. And we'll just go like that then.
There we go. Yeah, I think that works.
That works? Okay.
I will mute myself out, sir, and thank you once again. You are, I don't know, you call it, you're like a backbone of this conference, and you've done so much on inertial propulsion. So thank you.
Well,
thank
yeah,
you.
this is more on inertial propulsion. Like you just got done saying, I pitched this at the coffee conference there, and Tom about went ballistic. He says, you got to build one. So I've been working on it.
Yeah.
This is first year's documentation of it. Anyway, we'll just keep going here from the, why aren't we changing? Something isn't working here. Let's try this. There we go. Okay. As we talked about earlier here, I presented from my Boeing work. Boeing did a lot of CMG inertial propulsion systems, which are on satellites as we speak, and also on the International Space Station. Anyway, Tom says, well, you got to build one of these things for me. So I said, okay. So problem is, me being an engineer, you're going to get a lot of numbers because that's what engineers love. How come we're not going here? There we go. The clicker's not going that good. This one's on differential or scissoring gyroscopes. It's one way of producing linear forces from rotary motion. There's other methods. We had a guy earlier that had another method. Dean drives is another one, rotating and counter-rotating masses besides the gyroscopes also do the job. I'll start with this quick review here on polarization of rotary forces. If you want to call this the secret ingredient, I guess you could. This chart shows the basic process of polarizing a rotary force. If you're an electrical engineer like me or a tech, it's very similar to rectifying AC electricity into DC. On the left there, if you rotate a mass at a constant radius, all the forces are equal, so it just vibrates. However, going to the center chart and to the right-hand side, if you decrease the forces, does this pointer works? Oh, you're not there. I'll assume it works. If you decrease the forces on half the cycle and increase them on the other half the cycle, as the red arrows show, the average force moves from the 0 point off center. On the right-hand side here, you see the bottom portion of the curve is flattened and the top portion is accented, and therefore the force vector moves off the 0 point to be polarized. And there's many ways this can be done. It can be done by moving multiple masses. It can be done by changing the radius, the curvature. It can be done by torquing gyroscopes, which is the way we're going to discuss here. We'll start with some pictures of the test article here. This one has the gyroscopes mounted in the horizontal position, which is thrust in the forward direction. The front of the vehicle here has the servo controllers, which run the servos, which slew the gyros. You spin it around on the backside here, you have the instrumentation, power supplies that run the gyroscopes themselves. And then we will take a side view of it. This shows the gyros swing back and forth on both the left and side views of it. However, to take force measurements, I was using a load cell So what I had to do was convert the thrust vectoring from horizontal to vertical. So we take pictures of that. Shows the gyros in the other position. Same frame and everything, only now the gyros are mounted vertically. And the side view shows it a little bit better. You see the gyroscopes now, they swing up and down rather than left and right as they were in the other picture. And that was so I could get good load cell readings. We'll discuss that a little bit more in detail here. First, we'll talk about inertia. When you deal with inertial propulsion systems, you have to calculate all the inertia of the systems so you know what you have and what you need. So we start rotational inertia I, and the radius of gyration K is the numbers we're interested in to make the thing go. There's two ways you can do these calculations. You can use the textbook equations for mass and radius, or you can use a cheat sheet, a lookup table based on area. For this operation here, I use both methods, starting with the mass radius one. From the textbook equations, inertia is equal to the mass times the radius squared. In this case, the test article weighs 17 pounds and the center of gravity is 1.776 inches above the base plate. And then from the base plate down is your D dimension of where you want the torque to rotate on. And then if you plug in all the numbers, you come up with converting the 17 pounds into kilograms, you get 7.711. And then you take your offset distance plus the distance D, square those, then you divide by 39.37 squared, which converts inches to metric. You come up with kilogram meter squared. Now going the other way, uses lookup tables for rectangular plates, and it calculates the rotation inertia from the center point and then a distance D to an offset or translated point. And the way this one works is you take the mass times the height times the width squared of the plate, divided by 12, and then square the offset distance. And then you got to throw some conversion constants to get to kilograms and meters. So taking a look at the system plates, this is what you have to work with. Now the base plate is 12 inches by 3.75 inches thick. Center line on that one is the D distance that you're trying to go to, where your rotational point is. And then the 6x8 plate is above that. Its center line is here, which is 3.188 inches above the base plate. The top plate is 1.5 inches by 0.313, and it sets 6.34 inches above the base plate. Now the number that you want is from the gyro center line to that point of rotation, which is called the radius of gyration, or the K factor. That's the number you're trying to get. And to do it, you have to plug in a whole bunch of numbers and do a bunch of algebra, which gets very time consuming. So we're going to go through this very quickly. The bottom plate weighs 5.165 kilograms. It's 12 inches by 0.375. You square those, divide by 12, square your offset distance, convert to inches to meters. And then you go to the front plate. It weighs 0.398 kilograms. It's 6x8 inches. Square those two, divide by 12. It sits up there with an offset 3.188 inches. You square that term, convert to meters. Rear plate, same dimensions, only this one weighs about twice as much because it carries the instrumentation package. So you square those to the and 6, and it has the same offset distance. And then you convert to meters. Now the gyros, the 2 gyros weigh 1.164 kilograms. There's 3.688 inches above the base plate plus the D factor. You square that term, convert to meters. Top plate, 0.19 kilograms. It's 1.5 inches by 0.313. Square those, divide by 12, and it sets up there with an offset 6.344 inches. When you get done doing all the dirty mathematics there and you combine everything, add it up, take out the constant factors, you come down here, you get 7.711 kilograms, D squared plus 2.412D plus 13.995 divided by 39.37 squared. And that takes everything over to kilogram meter squared. It's a long drawn out process. Come on, let's go to the next page here. How come we're not going? There we go. Okay, next page here is you take the calculated from the mass area from this chart and the mass from the previous chart, set them equal. By inspection, the kilograms go out and the 39.37 squared goes out. So what's in parentheses, you set equal to each other. D squares go out, so you move the D's to one side and the constants to the other. And you calculate D to be 9.475 inches. K is add 3.66 or 688. And the number that you're looking for is 13.163 inches, which is your radius of gyration. And that will be used in compute. Well, this thing just wants to keep going down and not shift. There we go. Okay, now we have to do all the inertia calculations for all the individual parts, starting with the gyroscopes. And that's done by taking the manufacturer's spec. These little gyros, they're about a 2-inch wheel on them. And they spin at 16,000 RPMs. It weighs 145 grams. And then you got the inner and outer frame diameters and the mass of the frame, inner and outer diameter of the rotor and its width and its mass. And then you, next step is you plug those into all your inertia equations, starting with rotational inertia, which is mass times radius squared. So you have the inner radius squared plus the outer radius. And then you got to convert from grams to kilograms and from millimeters to meters. And when you get all done, you come up with 6.3206 e to the minus 5 kilogram meters squared for the rotational inertia of the rotor. And then you need the angular momentum, which is times omega. Now omega comes up to be 2 pi times 16,000 revolutions divided by 60 to get frequency. And you multiply that and you get 1.059 e to the minus 1 kilogram meter squares per second for angular momentum. And then we move on to kinetic energy, which is I times omega squared divided by 2. So you take your inertia calculation there, you square up omega and you get 88.5159 joules for energy. Torque now is equal to power divided by frequency. So power is equal to the input power. In this case, it's 6 volts times a half amp or 3 watts divided by omega, which is the 16,000 converted to frequency. And you get 1.6114 e to the minus 3 Newton meters on torque. And then we wind up last over here. Acceleration, which is torque divided by the inertia. So we just calculated the torque and we already have the inertia. So when you divide those two, you get 25.4951 radians per second squared. Now those are the numbers for the gyroscope rotor, that's your source generator. Now we have to go to the frame and do basically the same thing. So we start with the picture of it here. We're going to now take the inertia of the motor, which is offset the radius of the gyroscope, and then the gyroscope frame, which is 2 rings. The motor is 58.2 millimeters long and 28 millimeters in diameter, weighs 56.7 grams, spins at 16,000, consumes 12 volts, 2.5 amps to start, 0.5 amp to run, which is 15 watts starting and 3 watts running. And then we pretty much run through the same set of equations, only this one's a little more complicated. To calculate the inertia, you have to do a hoop in the vertical direction and then a hoop in the radial direction. And then you have to translate the inertia of the motor. So we do this in basically 3 sections. The first part is the hoop in the vertical. Second one is the hoop in the radial. Then the third one is the motor, which is calculated as a cylinder, which is translated to the frame diameter. And so we start with the 2 hoops. It's mr squared divided by 2 for the vertical hoop and mr squared for the radial hoop. When you add those together, you get 1.5 times the mass times radius squared. If you use the averaging, it's inner radius squared, outer radius squared divided by 2. Plug in all the numbers, you get 4.637 e to the minus 5 kilogram meter squared for the 2 hoops, the frame of the gyroscope. And then the next chart here, we will do the motor. First, we calculate the inertia of the motor on the first one, which is mr, radius of the motor squared divided by 4 times the mass of the motor times the length of the motor squared by 12. When you work that number down, you get 1.8803 to the minus 5 kilogram meter squared. And then you have to translate the motor's inertia by an offset distance equal to the radius of the frame. So when you work that part down, you get 2.2587 e to the minus 6. You add that to the motor inertia, and you get, for a total, you get 2.1062 kilogram meter squared. So then the next step is to put it all together. You take the 2 hoop equations, and the motors have to double the translated ones. You multiply it by 2, take the 2 hoop ones, add them up, and you get 8.8494 e to the minus 5 kilogram meter squared. So that handles the motor inertia and the frame inertia. And we have one more, which is the servo. A lot of inertia numbers when you're playing with inertia systems. So this next one here, you have a servo that rotates it, and it generates 57 inches of torque. Now, mechanically, it will rotate plus or minus 90 degrees. However, the electrical servo, or the software, the controller that runs it, is limited to plus or minus 45, so there's some limitations there. Speed is 60 degrees, 0.19 seconds. It weighs 37 grams. 6 volts at 1 amp for 6 watts of power. So then we go down, we pretty much run the same set of numbers one more time. The first one is rotational speed. You take your 60 degrees divided by 0.19 seconds, convert that to radians, and you get 5.5116 radians per second. And then you go for angular momentum, which is the inertia times the omega, and the inertia is 8.849. That was already calculated. Then we times it by the 5.516 omega, and you get 4.8775 e to the minus 4 kilogram meter squared per second. And you just go through the next set here, which is energy kinetic energy now, which is omega squared, and that's 1.344 e to the minus 3 joules. That's a far cry from the 88 joules you got off the rotor. So this is a very low power system here. And watt-wise, or power-wise, it's the same thing. You convert the torque times the frequency, and you get 2.216 watts compared to the 88 joules you got off the rotor. And the last one, again, is acceleration, which is torque divided by the rotational inertia. So you take your 4,100 gram centimeters, convert that to kilogram meters, and divide by the inertia, and you come up with 4.544 e to the 3 radians per second squared. That's pretty much all for the inertia calculations. Now we'll talk about gyroscopes, differential gyros in particular. And this is basics on gyros. There's 3 orthogonal or 90-degree vectors. The first vector is the spin vector, that's highlighted in red. And then the second vector is your torque vector, that's highlighted in green. And the output vector is highlighted in blue. Now, when you operate them differentially, or what is commonly known as scissoring, you spin them in the same direction. Spin vector is the same for both of them. However, the torque vectors are opposite. One is clockwise, one is counterclockwise, and therefore you get 2 output vectors which are differential. One is clockwise and one is counterclockwise, or opposing torques. And then we'll run the numbers on that. The equation is the torque output of a gyroscope is the speed of the servo times the angular momentum of the rotor, which is the inertia times the speed of the rotor. And then I just color coded them here to match the vectors there. So the torque output's in blue. This is peak torque, and your servo speed is 5.516, and your rotor inertia, which we previously calculated, is 6.32 e to the minus 5, and the speed is 16,000 revs divided by 60 for hertz times 2 pi to get omega, and the output comes out to be 0.5837 Newton meters, or 0.4305 foot-pounds, or 82.657 ounce inches. That's the peak for each gyro. Now we'll talk a little bit more on the differential torques and what those do for us. Starting with the basics of torque definition, you have a lever arm that's a foot long, and you put 1 pound on it to get 1 foot-pound of torque, which is equal to 192 ounce inches, or 1.36 Newton meters. Now, where it gets a little interesting here, when you take most physics problems, the lever arm is assumed to be massless. Well, that doesn't work in real-world engineering. You have to account for the mass of the lever arm. So the next step is we start with the calculation of the inertia of the lever arm, which is the width times the length cubed over 3. So it's a 1/2 inch thick, 12 inches long. And then you got to convert that to metric. So you wind up with 1.195 e to the minus 4 kilogram meters squared. When you take the torque and the inertia to get acceleration, you get 11.38 e to the 3 radians per second squared. What actually happens after you get rid of the math is the mass of the lever arm delays the acceleration or the application of the torque, because you have to accelerate the mass of the lever arm. So it's kind of a delayed response. And here again, you have orthogonal vectors. Your force vector and the torque vector are 90 degrees apart. Moving on to the differential diagrams for torquing, we start with a free body diagram, which you have the 2 torques counter-rotating, separated by a distance lever arm of distance d. Now, if those two torques were applied on a concentric shaft, nothing would happen because the torques would just cancel each other. Torque 1 equals torque 2, but they're in opposite directions. Well, when you put a lever arm between them, it gives them something to work with. So we do the number crunching on that. Now, me being an electrical engineer, I kind of solved the problems backwards. However, I think you get a better understanding of what happened to me. So I take the torque here and I draw a lever arm on it. I put a force vector on it at 90 degrees for both torques. And then when you split the lever arm in half, and in the center point down here, that's your radius of gyration, K. That's the number that we calculated off the frame inertia. And what you're left with is a couple of triangles. You have the big triangle here, which is half the separation distance, radius of gyration plus the radius on one triangle. And when you get down here, you have the force vector split into the X and Y components. So by trigonometry and congruent triangles, you can come up with the cosine of the angle is equal to the big triangle and the little triangle. And then you set those two equal, you can get the radius and the radius of gyration. Now, like I said before, I do the calculations backwards because, for me, it's the correct way, but if I was a mechanical engineer, they'd do it the opposite way. That's why I call it a reverse solution. When you plug in the numbers, now you go back to the K calculation from the inertias, you get 13.163. You plug that into the theta angle, and you get 2 times the 13 divided by the separation distance, you get 80.3 degrees. And the radius is the sine of that. So you take the 13.13 divided by the sine of 80, you get 13.35. You plug that into your torque equation, which is the d, which is the separation distance, times the torque divided by the radius. And so you have the torque, which is the 0.43 foot-pounds, times the separation distance, and then you got to convert to feet, and there's 2 gyros, so you multiply by 2, divide by the radius, which is in inches, and convert that to feet, and you come up with 0.404 pounds peak, calculated output force of the 2 gyro system. Now, this chart would be what I would call the normal solution. This is the way a mechanical engineer would solve the problem. You take your radius of gyration down to the point of rotation, and then you draw your radius vectors in, and your force vectors now set up where the torques are. To me, that's not intuitive, because when their force vectors are down here, you can actually see what's happening. Here you don't, but you can picture it that the force vector here to the left and to the right would cancel, and the 2 force vectors in the Y direction would add, but it's not quite as intuitive. That's why I sort of work them backwards. Now the next one is I do a little bit of testing on this. This angle, the smaller the angle, the more force the system generates. So you have 2 variables to work with, the separation distance d and the radius of gyration k. So the first entry was what we just calculated. Now, if you separate the gyros a little bit more, say add 1 more inch, now you start decreasing that angle. If you could get the radius of gyration, which is based on mass, down to say 5 inches, you can reduce that angle a whole lot more. And so that's work in progress as far as improving it. Now, this equation simplifies or is more complete because it shows all the individual parts. You have I lumped all the constants together up front, and you have the speed of the servo times the, oops, pushed the wrong button, times the speed of the gyros times the mass of the gyros times the dimensions of the gyros times the separation distance over the K factor squared times 4. So you plug in the numbers, the speed of the gyros is the servos is 0.877 hertz. The gyros spin at 266.67 hertz. Mass of the rotor is 112 grams. The inner diameter is 41.3. Outer diameter is 53.0. Separation distance 4.5, and the radius of gyration is 13.16. And of course, you get the same number, 0.404. However, you can see what parts contribute. Well, in looking at that, by changing the separation distance and the radius of gyration, you increase the separation distance and decrease the radius of gyration, you can improve your numbers here. Now, the numbers in red are the minimums that are required for movement, and we'll get into that a little bit more. You also have a slight option of increasing the servo speed here. Everything else here is fixed by whatever gyros you have. In this case, this is a 2-inch gyro, so all those numbers are constant. The next step is we'll look at the instrumentation electronics and dig down into the schematics a little bit. The electronics on this thing, they're powered off the same 6-volt supply that runs the gyro motors, and they're designed to monitor both motor voltages from 0 to 6-volt scaling, both motor currents 0 to 3 amps, both motor frequencies 0 to 300 hertz, and then it also monitors the load cell 0 to 10 pounds. And then all that goes out to a connector. You can connect up to an oscilloscope so you can monitor all your perimeters. The schematics of the thing, you get your 6 volts in here. Power switch goes up, turns the 2 gyros on. Also runs in here to a DC to DC converter, which powers up the plus and minus 12 volts that runs electronics. And then we grind the plus 12 volts down to 5. For running the load cell only takes 5 volts. Well, then you get up here, you have a monitor the voltage from the motor. You monitor through a current sense resistor from the motor, and then you have a infrared pulse counter that monitors the speed of each gyro. Goes down to a selector switch, so you can monitor left or right gyro. And then the outputs are all buffered, isolated, and scaled. You got the voltage scaling, the current scaling, and the frequency scaling. And then the load cell is scaled over here, and they all run out to DC or coax connectors over here that go for the scope monitoring. Now the servo is a little bit simpler. It's a little single chip controller. You have to program it for a sawtooth, so it goes fast in one direction and slow in the other. It's powered by a second power supply, separate 6-volt power supply. It does have a few problems. It only drives plus or minus 45 degrees, so you don't use the full range of the servos, and it uses the same time base for the power stroke and the reset stroke, which causes some problems. We'll get into that right quick like here. Next chart here, the servos swing from a minus 45 degrees to a plus 45 degrees in 100 milliseconds. However, on the reset, which takes 600 milliseconds, it goes in 100 millisecond steps. So it's not smooth, it's jerky a little bit. So the total rep rate is 700 milliseconds for each stroke. And then we'll go over here to the force measurements. This was the reason I had to change the from horizontal to vertical. I use a what's called a load cell, which measures compression load, and it converts that to an electrical signal. The scaling is 10 pounds maximum, so the scaling is 1.5 pounds equals 1 volt. The problem is it only measures in a compression mode, so any force in the X direction wouldn't apply. So what I did is I changed the gyros for vertical thrust, and then I put the load cell under the lip of the test article. And so as it generates some vibration, I dampen that out because I'm looking for ounce force resolution. So I have to dampen out some of the vibration by the weight of the vehicle. Now the weight, 17 pounds, it's about a 40-60 distribution. So there's 6.7 pounds DC preload on the load cell. And then there's a scale factor. The gyros are setting 5.5 inches from the fulcrum, which is the rear wheels, and the load cell is 15.5 inches from the fulcrum. So there's a gain of 2.818 on the measured data. So when you do the data reduction to get the force generated, you have to subtract out the DC offset of 6.7 pounds and divide by the gain factor of 2.818. Get the real numbers of the force being generated. Now we get to the fun part of actually firing it up and measuring the data. Okay, the first scope plot is on the motor speed, voltage, and frequency. Okay, the yellow here is the voltage applied to the motors, which averages out to be 5.72 volts. The purple down here has got a little more ripple to it. That averages out to be 0.55 amps. So multiply it together, you get 3.15 watts of power. Your square wave here, the period on that square wave is 3.75 milliseconds, which translates to 16,000 RPM. So I can verify that both gyros are up to speed and running for manufacturer spec. And the next thing I did was a noise measurement. I ran the servos back and forth on their sawtooth pattern, but I didn't fire up the gyroscopes. They're just a dead mass, and I'm looking for the background noise. And this is what it comes up to be. So their system is noisy. Now the next step is I did just the opposite. I turned off the servos and I turned on the gyros, and the noise spectrum is about the same, only it's a little more ragged. So there's quite a bit of noise to deal with. Now this one is the actual data here that we took. You can see the pulse coming up, power pulse coming down, and then there's this plateau on reset. There's your 6 pulses because it's not smooth, and the rep rate is 700 milliseconds. And if you look at the number here, you're up to about 0.43 pounds peak force being generated. Now we'll do a little analysis on that. And then going back to the simulated servo plot, we now put on the force. So in the 100 milliseconds, it goes up to 0.43, and then at 150 milliseconds, it comes back down. However, you get, because of the stepped reset, you get a slight DC offset here. When you take the average, it averages out to 0.128 pounds. And the torque rates, you got 15.708 radians per second for the high speed power pulse, and you get a minus 2.618 radians per second for the reset. Now that's not smooth, so that's a little bit of a problem there. Now the averaging equation is basically half the peak value times the square root of the duty cycle. So the peak, it goes up 100 milliseconds up, 150 milliseconds down, with a rep rate of 700 milliseconds. Peaks out at 0.43, so you take that in there, divide by 2, and then you take the, add your peak pulse, divided by the rep rate, take the square root, and you get the 0.128 pounds, which is 2.05 ounces. However, to make this thing move, it's going to take 3 ounces average force. Now, then I did one off-axis noise test. I measured in the vertical axis, but I turned the gyros around and had them swinging in the horizontal or forward direction and measured the off-axis vibrations. And you see that's even worse than the on-axis vibration. So the system generates a lot of vibration because you're torquing gyros. That causes a problem. Now I'm going to try and run a little clip here. I don't know how it's going to work, but we'll give it a shot. If it'll come up, let's try that. There we go. And no, it doesn't want to start. I don't know how to do that. No. Looks like
you know, Mike, are you showing your so I don't know which window you have, but if you have,
I only got one window, so what it's doing.
No, I mean your virtual window. I mean, if you highlighted PowerPoint, because it's not even showing the clip. It's not showing the window.
Well, I know it's not running either, and my screen went dead.
Oh, okay.
It did something crazy.
Yeah, I wondered if maybe you displayed the
Hang
power.
on a minute, I'm going to try something else here and see if we can.
Okay, yeah, no worries, no worries.
Does that show up?
Now you got it. Yes, sir.
Yeah, no, the trick is to try and make it run, and it's not doing that either. I can't.
Could be. You know what? Down there in the center, that play button, is that doing it? Your mouse is lagging. I think maybe you got too much running.
Well, that could be. I don't see a play button though. That's the problem.
Okay, in the dead center, you see the 10 on the left and the 30. Dead center on your screen on the very bottom. Your mouse is right near it. Nope. There you go.
Right there?
Yeah, you get a little play button. Dead center.
I don't see it, but I'll click on it.
Nope, that's your seek button. That's your seek button. It's below your toolbar. You got a little 10 and a 30, right? On the left and right. I'm hoping you.
We just lost everything here. I don't see a 10 and a 30. I'm not knowing what you're looking at here.
Right down at the very bottom, dead center. You should. I'm hoping you should have a.
Well, it says chat 99 plus. If I'm.
No, maybe you're seeing a different view. Than
I'm seeing something else. We're not seeing the same thing. Unless I got to go back over to the. Oh, wait a minute. Here we go. Let's try that. Ah, there we go.
Okay, good deal, sir.
Yeah. Now I don't know if I get back to where I wanted to be, but we'll try that next. Okay, new share. Let's see. I think this is the one we want. Okay, we're back on PowerPoint now. Oh. What are you seeing now?
Yeah, sorry, I was muted. Yeah, you were back on PowerPoint.
Okay, we're back on PowerPoint. Okay, then we'll do the conclusions here. The demo unit and its documentation showed that the differential or signal scissoring gyros will produce linear forces. And that force that's generated is a product of 3 terms. One is the size of the gyros, which is rotor speed and mass, and the speed of the servos, and then you have the inertia of the frame, which is the radius of gyration and the separation distances. So those are some of the variables you have to work with. And then 3 there, I changed the gyro orientation to vertical so I could run a load cell and get respectable numbers. However, number 4 there, the generated output force was only about 75% of what's required for movement. So it did not move, but we definitely got in the ballpark. So the next chart here is on improvements that need to be done to get it to move. Optimization, we need a better controller to get a smoother servo rate and to separate the power and the reset strokes. And we need to change the test article, increase the gyro separation, and then decrease the radius of gyration by lightening the frame. And also more powerful or bigger mass gyros would work. Now, this detailed analysis that we just went through is also valid for the Boeing CMGs here that I showed in the previous presentation. If you remember this picture from the history of Boeing CMGs, this was old bug eyes that we played with. It's got big, 4 big gyros. Those are 24-inch wheels on there. There's 2 on the front and the 2 on the back. You can't see very well, but it generated hundreds of pounds of force. And then the gyros are also gimbaled for thrust vectoring. And that was the little play toy we had in the lab there. And if anybody's interested in finding out more about gyroscopes, this is the website I recommend. It's the one that I use, gyroscopes.org and gyroscopes.com. And then we'll wind it up here. And hopefully I haven't bored you with too many numbers because it was a long, detailed analysis. And if you're still awake, thank you. And any questions?
Good deal. Okay, so let's do this. Mr. Gamble, let me stop your screen sharing. I want to.
I was just looking for the button.
Yeah, I want to put this on gallery view. Everyone, giant applause for Mike Gamble. Mike, thank you so much. Thank you so much. And I know you have more to share, and you are always welcome to come back and share. You have.
Like I said, I can do one a month. I have 5 of them on getting this thing running. It does run, but this was the first year, the initial cut. Like I said, Tom twisted my arm to build it, and this was throw it together and see what you get, and then you go optimize from there.
Yeah, well, you've got a wealth of information, I mean, a career's worth of information, right? But then, especially when it comes to inertial propulsion and working at Boeing and the gyros and all of that, you have this unique experience and knowledge that you've applied so well. So thank you again.
I'm happy to pass it on to anybody that's interested.
Yeah, well, so let's go to questions then. Again, and let me see, it is Option Y on Mac or Alt Y on Windows, and there's a button hidden in the Zoom menu somewhere too. If anybody has questions for Mike.
Hopefully I didn't scare him off with all the numbers.
No, you didn't scare him off. But you know, I think we don't have a lot of questions. Oh, there's Will. I think typically we don't because you've come on several times, right? So folks have had answered in the past.
Yes.
Will, go for it, sir. Oh, hang on just a second.
Muted.
Yeah. Hold on. There we go. I'll ask him to unmute, and I just checked it so people can unmute themselves.
Okay, yeah, I pressed the button, and error came up. So, yeah, hey, I was just looking at your device there. It's rather cool. I was wondering, you said make it lighter. So, have you thought about using composites?
Well, yes, I use the iterator. This is the first of 5. I've been working on this thing for 5 years for Tom. Every year I would go down and present at the coffee conference until we got it running. It took me 5 years. Like I said, it's kind of a part-time hobby. First, the next session that I will present is on optimization of it. Eventually,
it does seem like that would be the way to go.
Yeah.
So, are you trying to make this for space? What is your actual goal for this project?
Well, this was just they're already in space. Boeing has them in space along with a lot of other aerospace companies. All your geosync satellites have 4 gyros on them for station keeping, same as the International Space Station. It has 4 big ones, 4-foot rotors.
Yeah, but I mean, what is the actual, I mean, obviously Tom, Tom seems, I read his book, so I think he has some, future goal.
Yeah,
and so I wonder what that goal is.
Yeah, he was very interested in inertial propulsion, and he couldn't twist my arm fast enough to build him a tabletop model.
So is he considering terrestrial use or space use?
I would say space. For terrestrial, you got a few problems. They'll never make a rocket engine out of one because the weight of the vehicle, you can't blast off with it. But once you get it in space, the weight of the vehicle goes to 0. So whatever forces it generates, you have the test article I showed you, all bug eyes there. The weighs 1,500 pounds and it generates, let's say, 300 pounds of thrust. Well, that's not going to blast off the Earth. But once you get it in space, the 1,500 pounds goes away and you're left with 300 pounds of thrust.
Yeah, I've seen researchers experimenting with gyros to try to make counter forces for drones. Do you think that this might have some applications there?
They already have laser gyros on drones for stability.
Yeah, that's for stability. But I've seen researchers use them to try and make, different, try to change the direction of the craft while it was going forward. So it'd be going forward and try to make the direction of change using some mass.
Yeah, gyroscopes work for that. The old German Hannibal flying saucer had 3 gyros at the bottom of it for flight controls.
Oh, I didn't know that. You have documents on that, or?
Well, I pitched that here. What was it? 1 or 2 pitches ago was on linear propulsion.
Okay, yeah, thank you very much.
Okay, so let's go to Robert next.
Hi, Mike.
Yeah.
I'm just curious what the first prototype you built. Was that financial constraints, or you just didn't have the tools to do like a software or a modeling type of optimization, and then build the?
Well, the first cut, Tom just wanted me to get something going, so I got some aluminum plates and mounted the gyros on there just to see what I got. And then from there, I started doing the optimization. I lightened the frame, changed the controllers, and we finally got it working for him, and he was very happy with it.
When was your first talk on this here on APEC? What date? Do you remember?
The date, I don't remember. The name of the pitch was History of Boeing CMG Work.
Okay.
Tim could probably tell you, or
I wouldn't even be able to look it up either. Mike, you've been on, I think 6 or 7 times now. So I would say probably the best thing to do is just go to the Alt Propulsion site and hit search and type in Mike Gamble, and
it's
all right
somewhere, I'm sure.
Okay. What does CMG stand for? Just curious.
Control Movement Gyros.
Okay. Thanks, Mike.
Yeah.
Yeah. So okay, let's go to Harold next. Harold.
Thank you.
You're on.
Hey, Mike, great presentation. Thank you.
There we go.
2 questions. Number 1 question, the design of the rotor. What kind of approach do you use? Do you have the design like the flywheel type with the mass at the rim, or it's just a plain disc, flat disc, which you set up spinning? What design do you use for the rotor?
Well, be flywheel type. We bought the gyroscopes already built from this website that I just gave you. I've been helping Mark. He's building some bigger ones. He'll probably, I don't know if he's on right now or not, but he's building some 3 and 4 inch ones. These are only 2 inch, so they're pretty small. So what I had to do was make the frame lighter and smaller because I needed bigger gyros. So you either make the gyros bigger or make the frame smaller until you get it to self-propulsion.
Oh, good. Thank you. My second question, what is the comparison in the performance of rotor when it is spinning and versus the disc, the rotor being horizontal, perpendicular to the gravity vector? What is the difference in the performance of both of them?
Well, the gyros put out the same amount of thrust. It's just I had to go vertical, so because the load cell would only measure, in the gravity direction in the negative y-axis. Now, since then, I've put an accelerometer on there and got rid of the load cell, so I can measure the thrust in the horizontal axis.
What thrust to weight ratio are you aiming right now? Do you have right now with what you have versus the weight of the unit?
All right,
the control.
We started off at 17 pounds. It's now down to 9 pounds, and it generates about 3.3 ounces of thrust.
Good performance. It's showing.
The weight.
Thank you.
The weight to thrust ratio is very small for linear propulsion. That's what I said on the Boeing one there.
Okay.
The frame was 1,500 pounds and it generated 300 pounds of thrust. That's why you can't use
that's very good. Also, awesome. Thank you, Mike.
Yeah.
Okay. And Harold, thank you, sir. So let me see. Any other questions for Mike?
I have a question.
Go for it, man.
Okay. The device that you just showed. All right, the gyroscope and the unit that it's connected to measuring it. Could this be built? And let's say all these scientists, their stuff is taken away, but when wherever their stuff is, it has a signal that it recognizes in space and time to give it a start code. So some of these machines just start on their own, like as we saw in your machine, how it just started, on its own from whatever the resonance frequency from that particular, people that work with their hands, they put their DNA on it, it's not just machines, it's, like our energy gets deposited. So, into these things, and it's a code, like, mathematical code plus genetic code. They have to match, to match up to create what the parallel is called of time, what time is, how do we find time and science together where, they meet, because you're always going to have a shift, but you would have a genetic line, generational line. That's the real world. That would be the machine world. You understand? And whenever it makes a parallel, that's existence. That's real time.
I'm afraid I don't understand what the question is.
What are you trying to describe?
What am I trying to describe?
Yeah, like in real term. What are you after? What are you trying to prove? You have to be after some, not just mathematics. What are you trying to prove?
Well, he's
just to generate linear thrust using rotor.
The possibility of existence on a higher plane. How do you do that?
I think, Lulu, I think that might be a little beyond.
No, that's your gyroscope's rotation rate. It's going to have a resonance factor of, an apex point that, like all the frequencies are going to settle on that plane.
Hello?
So, just, you're talking, this isn't, a place where it's closed. If you have a refraction, like a window to it, then, you know, it could be a reverse code for it to start. It could be just anywhere. It's just a you know, a reflective, whatever that glass or, you know, whatever that thickness of whatever it is in, it just, you know, do the opposite and it could start, like, you know, give it like an electron, like, or electron or whatever it is. It just depends on whatever you started with.
Yeah.
You know? Yeah.
Well, yeah.
I love that. Like, listen, I love your work. I understand it with all my heart. And so when I explain it back, it's like, I want confirmation. Like, am I right? Like, tell me I'm right. Because if I'm right, this would be like the coolest thing, you know, like existence, like multi-dimensional existence. We could like travel to different places and, you know, like send our physical laws first before we send ourselves. So when we get there, you know, we're comfortable. Like, it's just, I mean, like multitudes of possibilities with this. Like, it's really cool. I really appreciate your work. You know, I'm sorry I always barge in, but, you know, that's just my...
You're doing great. You're doing great.
Thank you, guys.
Oh, okay. So let's do this. I think we're all set. It's 3:00 now. Let me see if Mark Sokol, Robert, did you have a quick question or?
Yeah, I just want to. I missed the video. I guess I couldn't get it to run. Is there a way of?
You want me to try it on?
Yeah. Try do the video one more time, and then after that, I'm going to go to Mark Sokol.
We'll give it a shot.
Mark says not ready for lab update.
Okay, are you seeing it? Or what are you seeing, I guess would be the question.
You're not sharing your screen.
Oh, okay, hang on a minute. Wrong button. Oh, let's try share screen again. Okay. Oh, new screen. New screen. Let's try that. Are you seeing that?
Yeah. Yes. Yeah, I see it.
Okay. You want me to run it again?
Interesting. Just one more time.
Okay.
I'll have to look up, get some info on it.
So as the two rotate, they're causing a linear force up?
No, the force is down.
Okay. They're causing a downward force. Okay.
Yeah. Mm-hmm.
In addition to their own weight, obviously.
Yeah. Tim, can you clear that out? I can't get it cleared.
You want me to stop your screen share?
I'm watching the stream right now.
Yes, sir.
I'll look into Mike Fiorentino.
So I'm going to remove the spotlight from Mike.
So
Okay, and you know what? I should have done that. That may screw up our archive video. I should have removed that when we started Q&A. And then I'll stop your sharing. There we go.
There we go.
Okay, yeah. Sorry, I removed the spotlight. I'll lower the hand. And Mark said, let me go to Morgan. Morgan, go for it, sir.
Yeah, okay. Thanks for this presentation, Mike. I wanted to, so just building off this video that you just showed, can you describe them really fast? So you have two gyroscopes pointing at each other, right? Which is the direction of rotation of each?
Same direction. And
like both right-handed or both left-handed?
Yeah, they're both.
Okay, both.
If you want to generate torque, you spin them in the opposite way. If you want to generate linear thrust, you spin them in the same direction.
Okay, and then so you have them both right-hand rotation, and then you're oscillating them up and down.
Yeah.
Are you is the rotation staying the same at each point? As you're oscillating down, the rotation is constant, right?
Yes. Well,
and
the gyros slow down just a little bit because you're extracting power from them on the power stroke.
I see. Okay, and then I see. So they rotate down, they slow down. Whenever they rotate back up, or does it stay constant rotational velocity and they roll back up and then they increase their velocity again?
Well, the motors keep turning as constant as they can. But on the downstroke, they lose a little bit of energy. But in the time it takes to go back to the reset stroke, they're already back up to speed. The motors, in the 600 milliseconds that it takes to reset, the motors have already pulled them back up to speed.
Okay, so then, okay, and then, so the angles that they go down, are you setting that, or this is part of, I don't know if this is part of your calculations, but the angles that they rotate down, are those selected for some reason?
Yes.
To like maximize the effect or something like this?
Was plus or minus 45, and then through my optimization, I get that down to about plus or minus 20.
Okay, and then so you are measuring their, I guess it's an increase in mass, right? Or I forget which direction is the thrust? Is it up or down?
Down, down.
Down. Okay, so you're actually measuring an increase in mass or an increase in weight?
Well, it's thrust.
Sure. Or whatever, if you subtract off, and then you don't see anything as they rotate back up. It's not like the mass of the thing is oscillating.
No.
Or it stays with a continuous thrust down.
It may be a little bit, but the noise charts that I showed you has a lot of background noise, so it's probably down in the mud. There's a lot of noise there from vibration. So in theory, they should the gyro should speed up a little bit if you're going the opposite direction in theory, but the motor holds them as constant as it can. On the power stroke, you're extracting a lot of energy. And you're not doing that on the power stroke, but in theory, they should increase one way and decrease the other. If you watch Lathowitz, there was some discussion earlier about Lathowitz. As long as he's spinning or turning or processing the gyro, there's no weight on it. As soon as he stops procession, the weight appears immediately. So it's the same principle here.
I see. Okay. And so you measured thrust from this.
Horizontal.
You actually measured a thrust from this thing, and it wasn't oscillating. It wasn't like sinusoidal as it goes up and down. It was continuous in one direction.
Yes. It's noisy, but it's there.
And what was it? I forget. You had mentioned that there was like it's actually generating quite a bit of thrust, just not enough to make it levitate or something like this. What was the actual thrust that it got?
I get 2 ounces of thrust, but if I put scale on it, it requires 3 to drag it across the ground.
Okay. Huh. Okay, that's cool, I guess. Yeah. Are you? So what are you doing next with this thing? Are you building bigger ones, or what are you doing?
Well, I've optimized this one enough to get it to run. I'm hoping to get some of Mark's gyros here. He's making some 3- and 4-inch gyros, which will generate more power.
And, how fast are they spinning, by the way?
16,000 RPM.
Oh, wow. Okay. Wow. Cool.
88 joules by calculation. That's quite a bit of power.
Yeah. That's a lot faster than what I was thinking. That's really cool. It's funny because that kind of, I feel like I'm going to catch flack for this, but it does kind of have this, this gravito, that has, gravito magnetic effect type thing. It's just pure gyroscopic stuff though, right? Nothing great, like.
Yeah. Well, the last presentation I did was a comparison between mechanical force or thrust and electrical force or thrust. I'm of the opinion, being an electrical engineer, that anything that moves is an electromagnetic field, and you can generate the same force that you do with a gyroscope by spinning a magnetic field.
Sure, yeah, okay. Yeah, so this is kind of some weird like flywheel type thing. You're converting the rotational energy into some sort of kinetic energy somehow.
Linear energy, yes.
Yeah.
You're rectifying it, same as you do with AC voltage. When you convert it to DC, you rectify it, or off-centered is what you're doing.
So this is, I guess, conservation momentum. You're converting, I guess, angular momentum to linear momentum.
Yep, exactly.
That's interesting. Okay, cool. really cool, I think, yeah. Thank you.
You bet.
Yeah, thank you, Morgan. Let me go to Will next. Will?
you're muted. There you go.
So I was looking at your video, because this time I can see the video more clearly. And I noticed that you were using 3 channels on your scope. And only the first channel had anything going across it. So I'm wondering, is your sampling rate too low on that older scope?
No, if you go slow speed on the scope to pick up the servo time, the pulses from the pulse counter on the gyros just smudges out because they're at very high speed.
Okay, so this is an artifact of the gyros themselves.
At high speed to pick up if you want the gyro information, which is the pulsing at 16,000 hertz or 16,000 RPM, which is about 260 hertz.
260 hertz.
And then if you go to the gyro slew rate, you're down 700 milliseconds slew rate. And so the two are incompatible, so you have to take separate pictures off the scope.
Right. So in other words, you probably need a faster scope.
Well, no, you can't take the two pictures at the same time. You can speed the scope up to get the gyro data, but then you lose the frame or the force data. And if you slow the scope down for the force data, you're going to lose the gyro data.
Right. Oh, yeah. Okay.
One's down in milliseconds, and the other is at microseconds.
Yeah, I think the more modern scopes. I have a Keysight here, Infinivision.
Yeah.
And
if you look at the picture,
I can separate the channels.
Yeah, well,
up to 5 gigasamples.
Yeah,
so.
well, this doesn't have it, but if you look at the scope, the purple line there is the force output, and the yellow line that's all fuzzed out is the gyros.
Yeah. Okay. Anyway, thank you. I can see. I understand what you're saying. So thank you very much.
Okay.
Awesome. Awesome. Well, so I think we've got about 45 minutes left until Mark is ready to go. I think we're all out of questions. So why don't we do this? Everybody, I'm going to put this back on gallery view. Everyone, Mike Gamble, one more hand. Mike, thank you again for presenting, sir. Thank you so much.
No problem. Just holler when you want me back.
Yeah, of course, of course. Well, so next after this, let's do open discussion. And then after that, Mark will do some lab updates. So open discussion, guys. You don't need to raise your hand or anything like that. I've got it set up so anybody can talk who wants to. And yeah, so you guys can unmute yourselves and go. You know?
Oh, it's open discussion now?
Yeah, yeah.
Oh, okay.
And I will cut in probably in about 45 minutes or so for Mark, but
I was wondering, has anybody know about Joseph Cater's theories? I mentioned to him.
Can you maybe elaborate a little bit so folks know? Doesn't sound like there's a lot of name recognition.
As I understand, I read it in another reference. He was a scientist and or engineer. He studied the moon landings in detail, and he had all these wild theories. And he had this book called The Awesome Life Force, and then he included the theories of the Byford-Brown effect and the Searle effect. I don't want to get any more detail. If nobody knows about it, then why bother mentioning anything more about them?
Yeah, maybe if you have a link, you could paste into chat. That might help. That way, folks could look them up. For a moment, I thought you were going to say moon landing hoax, and then I would start to cry. Right? I was like, no, I don't do moon landing hoaxes today.
He does have some weird theories about the moon, but has nothing to do with he does mention to a certain point it was hoaxes, but he claims that we got to the moon because of a hidden anti-gravity device that the United States had on hand. It wasn't made public, obviously.
Nah.
Plus, that's it.
Yeah.
It was, he had so many wild ideas. It could probably be.
There's, and the strange thing about the moon is, I was talking with, because I did an interview with Ed McCullough, and he used to be in charge of STAFE Section E, and so STAFE Section E was the interstellar call, or not interstellar, but that was the space colonization group, right? They presented alongside STAFE Section F. So Paul Murad and Tony Robertson, and I think he had a couple other folks, they helped chair Section F, and then Ed McCullough helped chair Section E. And Ed was this enormous advocate of lunar colonization. And one of the things he was saying was the lunar regolith, right, the dust on the moon there, has been absorbing protons from the sun, high energy particles, for eons, right, for as long as the moon has been there. And those are basically hydrogen atoms. If it's just a proton, all it needs is an electron. So the moon dust is full of bound hydrogen. And then, as I recall, I don't remember where this comes from, but he was also saying that it's full of oxides too. So what he was saying was basically you take the lunar regolith, you heat it up past a certain point, and I guess NASA tested this, and water comes out, gives off steam, right? Because the lunar regolith, that hydrogen combines with it. And he actually showed me, I think it's published online somewhere, NASA did a map of the most productive areas of the moon for this, where you could literally just harvest, I don't know, like I think they were saying it was like the top inch of regolith, and heat it up. You had to heat it up pretty high, if I remember right. It was an intensive process, but it's something you could do with mirrors, So there's some interesting stuff there. And then there's that other theory that's been floating around. It comes and goes, that the moon might be full of water, right? That's bound up in the rock. So there's some interesting moon stuff.
Joseph Cater claims that before the moon landings, our unmanned probes actually measured or discovered that there's gravity almost as strong as Earth's gravity. I don't know how true that is.
I don't know about that. Shrish is asking, and again, Shrish, it's open discussion, so you can just pop on in. You don't have to ask questions anymore. Just pop on in and chat. He's asking, is there enough oxygen on the moon for such a reaction at scale? I believe so. I think the oxygen is oxides in the rock, and then the hydrogen was absorbed from the solar wind, basically. That was what Ed was saying. He did a lot on that too. He did calculations for a lunar dome on what was it? There's a big crater there. I forgot the name of it, but he did calculations.
When you say he, who is it?
Ed McCullough.
Oh, Ed McCullough.
Ed McCullough, yeah. He was wonderful. I loved him. He was a career Boeing guy.
Okay.
Towards the end of his career, I asked one of his friends once. I was like, well, what does Ed do at Boeing? And the beginning of his career, he was a nuclear sub engineer. And then he went to Boeing and he worked a full career there. And supposedly the last 10 years of his career, he was so senior that they just gave him kind of a made up job title and he did whatever he wanted. That was what his friend told me. They said, well, he just does whatever he wants. I'm like, must be nice.
For the record, I spoke with Tom Vallone when I was ordering things. He said he actually talked to Joseph Cater and said he was kind of not out of his mind, but a little quirky. I thought, isn't all inventors that way? Even like Tesla had his quirkiness with pearl earrings and that sort of thing.
I didn't know Tesla had earrings. I didn't know Tesla had earrings.
No, women's wearing earrings.
Around high voltage. I had this guy used to service the electron microscope, and then they had the electron microscopes. They cool them with a liquid nitrogen tank, and to keep the vacuum really good. And so this guy, he would like the electron microscope be fired up and running, and he'd be going behind the thing, sitting in this puddle of water, and with a screwdriver, futzing around in the back of the microscope, and it had like 10,000 volt power source or something. And every so often you hear this, oh shit, oh. The guy was constantly getting exposed to this high voltage. And over the years, his cognitive skills began to decline.
Surprise.
I think it's kind of like, in the old days when people they thought they had mental illness, they'd give them lecture shock.
What are you going to do with that?
And they discovered that if they did it enough, they would change their personality. Well,
there you go.
It's just I would say it's a job hazard thing. It has to do with, you're exposed to too much.
What are you talking about, Mike?
Huh?
It's too bad you couldn't
Who
put
are you
the plug
talking
like on
about?
a timer.
Oh, this was the service guy. His name was Mark. He worked. This is when I was at UC Santa Barbara, and he worked on the. He was the guy who would come fix the electron microscope. He'd replace the filament or something like that, But he wasn't very safety conscious around high voltage, and I see this a lot, especially in older engineering types, that they're just not that safety conscious.
You know what? I think it's, in fact, they have a name for it. What do they call that? I forgot the name of it, but you get, basically you get lazy to risk after a while. And I forgot the name of I forgot the official name of it, but they were talking about that with COVID, right? It's, you basically burned out on risk, right? You just reach a point where you're like, screw it. If I get killed, I get killed, But even remember the H bomb? Remember the?
Oh yeah, they used to jump over the cobalt 60 source, and then they got testicular cancer.
Yeah, then there was that one guy.
Did a quantum leap. If you want to think about it, some did a quantum leap with that.
Yeah, there you go. You could call it that, quantum leap.
Yeah. Yeah, but then I was thinking about when they were working on the bomb too. That guy had the screwdriver. He was prying it open with the screwdriver, and he let it slip. Remember that one? Remember that was the Pluto. That was the Demon Core. That was
tickling the tail of the dragon. Tim.
Yeah.
That was the number one accident. The number 2 accident was they had a series of the centrifuges while they were early on in processing the plutonium, and one guy forgot to turn off 2 valves. It was like a series of 3, and then all of the slop went down into the 3rd centrifugal reactor. Anyway, the centrifuge, and he turned it on, and all of a sudden, bright blue glow, and he was dead within 5 days.
Oh, okay.
That's different. For satellite systems, that would be a perpetual combination of the two, and it could be available in abundance at any altitude. And that person would be on that, but would always hold that object, because they would always, if they ever need it, it becomes quantumly entangled into their DNA, but they're consciously of the separation of it. So on our visible spectrum, we see it as a mesh, but in their, when they were making it and on their, spectrum, it's 2 separate objects for them still.
Lulu, you're talking about Mike's thing still, right? Are you talking about Mike's thing?
I'm explaining, because you're talking about the defaults, where like if the higher RPMs could mesh 2 things and then it becomes like, a blob or a plasma or blah, blah, blah. But yeah, because at the frame of reference, we see it like that. But in reality, on a quantum zoomed in scale, I could put my screen on on a quantum zoomed in scale, it's still separate for their time of reference, separate objects. They know that they're separate, but for when you look at it from a much, further angle, you see it as a homogeneous blob or plasma, as you call it in the labs, but it's still, they don't mesh, just we think it's meshed. It's still separate.
It depends on your reference frame.
Well, where whoever had that wrench and was working on it, that would be the reference frame. That would be that start of that connection of those two objects. And everything else for us, we're looking at it from like much later time. So for us to pierce through that and really like identify if it's a blob or just we cannot like zoom in harder, or like is it just like the frames of reference of time? Because time, if you can't measure it by identifying the difference in things, it becomes like you separate, becomes color, and just color and then color and then color and then color. And there's many examples on all of these probes, as you call them. They tested this. Even the last photo, like where it turned around and it took that picture of planet Earth, not specific light beam. Why? Because that was a marker in moment. It sent that signal. After that, it never looked back. Because if you look back, then you start the counter again. So you continue forward. It's a motion of propellant. You give one signal that here's an image. This is now like, whatever is the safe zone, but continuous propulsion for, and it just sends the data of whatever it has analyzed. So whatever that computation of that instrument and all the configurations for it to go forward, sends that signal that each one has its part, its piece, its number, its order. Everybody knows whenever that stream comes, like it's easy because, just take the specs of the original one, match it up to that, and it'll tell you which one was working at which time, which sensor was, like active before which one, and which one was the secondary that like tells you, to confirm that one. It's like a, relays of loops of, confirmations of down to the specific of all the sensitivities of those instruments. It's like beyond cool, like if people start understanding, it's like, my gosh, like, what can we do? What's next? What can we do? Can we go to now? Can we really fly? Like in my physical form, your physical form, so, Mark's physical form, Tim's physical form, like we're connecting on this, which is a blob, and then, just data for whoever doesn't understand it, but whoever understands it, like, okay, we're that means this is like the current time. Let's fly. Not just in, computer world. Let's fly. We all believe the same thing, regardless of coordinates and regardless of, space and time. If one idea comes, people will meet there. They'll find their ways, even with the different, distances. It's the focusing on that's, where it needs to, everybody, and all of a sudden disappears. Get it?
Yes.
Yeah.
Cool. So, interesting thought.
Can I have a little quick speak? Very quick. I just want to share something.
Yeah, Phil, do you want to talk about finite theory? Is that because I've been seeing your emails? I know you've been making progress on that.
Yeah, but it's more about what I've been talking about on the WhatsApp news group about the ether wind and all that.
Ether wind. Yeah. What is it? What is ether wind?
Yeah. So yeah, all right. I'll just talk about it very quickly. I just want to share my screen. This one. All right. All right. So like I was saying on WhatsApp, I analyze the Earth tides, like the sun that the Earth rotates, so the sun changes its position relative to the surface of the Earth. So that's surely the measurement of a gravimeter of high precision on the surface of the Earth across multiple days. And we can see that the sun affects the the gravitational acceleration on the surface of the Earth by microgauss is very low, but it's still detectable. And the difference between what is predicted and what is measured actually is called the residual, and that's the blue line we see at the bottom of the lower graph. The residual looks like the derivative of the theoretical of what should be measured. So that means when the gravimeter is perpendicular to the sun, the intensity of the difference is much greater. So that, and it looks like it's very consistent. It's always like it favors one direction against another one. So if it's like 3 o'clock in the afternoon, you will measure a greater difference, a greater residual, and so that, and it's always very consistent. So that means, that we are able to detect some sort of ether wind, or I call it ether wind because it's easier for people to understand what I'm talking about, but it should be called like a co-moving gravitational framework. So
the sun's gravitational field is affecting the Earth's gravitational field, but there's some time delay between the two.
Yeah. So if you measure the gravitational strength at 3 o'clock in the afternoon and at 3 o'clock a.m., then you will see the peaks. You will see some peaks at the bottom graph, either very low or very high. So that's the residual, the difference between what is predicted and what is really measured. So it's very consistent,
So when the blue curve is highest, like at 0.75, that's when the delta from what's predicted is greatest.
So the lower graph, when the residual, the blue line on the lower graph, that's the difference between what is predicted and what is measured. So when all the peaks you can see, either the positive or the negative peaks, means that that's when the difference is at its highest. So so that means that there is a preferred direction when it's at 2 o'clock in the afternoon and 2 o'clock during the night. There is a very consistent difference. So there is some sort of ether wind right there we can detect.
So in the direction the ether wind is from is perpendicular to the sun?
Yeah, because the Earth goes one direction.
And when you're measuring this, is it on the side of the Earth facing the sun or the opposite side?
I'm sorry, the side of
so like if I have my gravitometer on and I'm measuring this change in the gravity, from which side of the Earth are we on? The side that's closest to the sun or the side that's farthest from the sun?
Well, just the side that is perpendicular to the sun.
Well, they're both perpendicular to the sun, but one is the opposite direction. So like if see what I'm trying to figure out is if like the peak is 3 o'clock in the afternoon, that's where you're saying it's not symmetric with the day and the night. So like say at night, it's less, the amount of residual is greater at 3 p.m. than it is at 3 a.m. That's what I'm asking.
Okay, so this.
Yeah, your graph here.
Yeah, so the X scale is I don't use the correct hours there, but so the difference is going to be the opposite. It's just going to be negative during the night. It's going to be the negative during the day.
Okay.
Yeah.
So, but what I'm saying is that effect that you're observing due to which side of the Earth it's on. Well, so if I have the Earth's, if I'm making my measurement at 3 in the afternoon, and the distance between the Earth and where I'm taking the measurement is on the side of the Earth that's facing the sun at 3 p.m. And then if that's greater amplitude, then you go to the nighttime at 3 a.m. and it's less. Is it because you're measuring it on the opposite side of the Earth?
Yeah.
Offset gravitational mass.
Right, it's an offset. So basically you're measuring the offset gravitational field of the sun relative to where you're taking the measurement on the Earth. So in other words, I'm saying, is the Earth acting as a gravity shield with the sun when it's on the opposite side?
Well, that was my first, that's what I wanted to prove first, but I kind of detected the ether wind. I saw that the ether wind was more important than the graviton attenuation, but I still detected a little attenuation of 80%.
Oh, wow.
Of the graviton during the night, but I need more data. That's just a day and a half you see right there, but I need very precise more data to see if it's very consistent.
So
you actually have to have a detector that's not in the same location on the same moving mass. In other words, you'd have to have a space-based sensor in order to not detect the perturbations of the Earth as opposed to the sun.
Because there's more mass depending on, you're going through the amount of mass you have to go through to make the measurement is affecting what the measurement is. So it's difficult to, basically you're having both effects is what I'm hearing. And
yeah, exactly.
You need to be able to normalize the data in such a way that it accounts for that effect.
Yeah, that's what I'm doing. I'm normalizing the data at the bottom graph to compare them.
You'd have to have a dislocated mass in order to do that. It had to have a mass other than the Earth in order to make that measure. In other words, it had to be spaceborne, like a satellite, outside of Earth's perturbation.
Yeah, I did ask the international station.
Yeah, you have a constant. Even as far as the space station, you have the gravity constant of the Earth between you and the sun. If you're taking that measurement with the Earth between the instrument and the sun.
Yeah.
Yeah, you could do it. It's one way you could. Well, I'm sure that on the International Space Station they do have measurement devices to measure the gravitational field of the at the location.
Actually, the our newly launched satellite to the L2 orbit.
You're talking about the
James
telescope?
Webb. Yeah, James Webb.
Yeah, James Webb. If James Webb had a gravity meter, you could use that because it's isolated from Earth gravity completely.
Yeah. So what you're saying is you need to have a control.
You'd have to have a control that was outside of Earth's gravity.
Yeah.
In the L point, right? It'd be stationary. So
yeah,
in theory.
If you had one in L2, for instance, that'd be perfect. In order to be able to have a gravity constant removed from the Earth.
Right. And then you could normalize your data in such a way that it would tell you actual effect. if it's a gravitational effect on the surface of the Earth or not.
Wouldn't the classification need to be changed because, you know, L1 and L2 are classified under unstable states. So they pretty much don't do any more research, you know, further into that. They just, you know, stop there and they continue on it, you know, whatever. Yeah, so it could be different. Like full classification is eliminated from the first point because they didn't have enough information on how to stabilize, you know, the L1 and L2 field. In mathematics and theories, yeah, we have it, you know, to the minus whatever power, but and you know, reality, like just it's mathematics still.
No, you're thinking of L1 and L2 are the Lagrange points, and there how many are there?
4.
4.
So are those specific? Aren't those specific to Earth's gravity though?
Yeah, Earth, Moon,
Yeah.
right?
Yeah, they're Earth, Moon, Sun,
Earth,
you know,
Moon, Sun.
circuit.
Yeah.
So
Remember, gravitational fields like carry dust, carry things. So, you know, we've got like our ozone, so light that we get, it goes and then goes back around, and gravity helps it, propagates it as well, like its essence. So whatever crosses that line, it's going to leave something that, you know, touch, you know, it's going to leave something. Just, you know, everything that at the end that has something bigger than it, either it goes through it or it's going to leave a deposit. And, you know, especially if you line, let's say, our heavenly bodies, you know, like really, or create something that is scientifically comprehensible to real mathematics that will never dissipate, that this is like the origin of the origin, you know, things like that, like fundamentals, and like primary things, like core things, like, you know, things that like just we wouldn't be able to have, whether it's a you know, human or artificial intelligence, and figuring out a way to, you know, different timelines, different zones, to mathematically all that there, you know, that means we are leaving a trace somewhere, which is either we're bypassing our human laws, and somehow our energy is already up there. And now we just follow our energy, you know, like it leaves a print for us, because, you know, we're, you know, the science is on hyperdimensional. So the thought process, the biophotons that are being emitted, they're like getting up there and they're building this thing. We're building this thing already, like being built already, you know, whether, you know, just the thought of combining all that mathematics, the consciousness, you know, our energy, like on a, you know, a very short timeline, like this stuff is going to be like done, like all, you know, because it's a higher plane wavelength. We're residuating matter, you know, together to create this. So all of a sudden, when everybody kind of comes, it's already, because we're all like building it. I hope you understand. Like, I can't wait. Just let it, I'll tell you that.
I'm right there. I have solidarity.
So it says there's 5 Lagrange points.
Are there 5? Well, yeah, no, Michael's right. So you've got, well, wait a minute. Earth, Moon.
L1 between the Earth and the Sun.
Yeah.
L2 on the opposite side.
Wouldn't L1 change slightly because of the rotation of the moon?
Yeah.
But maybe it's so slight that it doesn't matter.
Well, it's enough to see. It's the position relative to the Sun is non-linear because of the effect of the moon as it rotates around the Earth, right?
Yeah, so you've got Earth. Okay, so Earth, Sun, and then Earth, Moon.
The opposite side of the Earth, the Sun. And then opposite side of the Sun from the Earth is L3. And then L4 is, how would you describe it? It's like 45, it's like roughly 45 degrees. How would you say that? What, who put this in? Somebody put in a link to the Wikimedia. Lagrange points. I can show it to you.
Oh, yeah. Yeah, I see it. I see it. Rob Chambers put it in.
Yeah,
Rob is being quiet today. Rob, unmask yourself, sir. He's still here. Well, it could just be he's tired. It's like super late England time.
Yeah.
So, and Tony's here too.
So,
Rob said he can't because of background noise.
Gotcha.
Yeah, like maybe he might be blasting faulty towers.
Here, I got it. See that?
Or not?
Hmm?
Can anybody tell me if my mic is on?
Yeah, I can hear you.
Thank you.
Is that Larry? Larry, what's going on?
Yeah. Yeah, I thought I'd come in and check on you. I thought I got my computer up and going. I got you picked up. But I'm working on a project. I think that it's pretty simple to understand. You do it the same way that everybody else does it. There are people here on Earth that was manipulating the gravitational force 20,000 years ago. And the other people that's manipulating the gravitational force of UFOs, they're not talking. And the people who are here 20,000 years ago, they were dead. So it's kind of hard to pick the brains of people who've been dead. But what I've discovered, they marked their trail, knowingly or unknowingly. They left evidence behind. And if you follow the trail of the optical equipment they used, then you can find out who did it. They wasn't building UFOs or spaceships. They were building magic carpets. A magic carpet, if you have the center of lift and the center of gravity, it's self-centered like a hot air balloon. But if you put a ballast on it, it'll make it tilt, and you have induced vectors. You have so much thrust and so much lift. You can go through, you can change the speed, and it'll drop to a slower because it's developing less lift, or you can move back. But in these pictures they got on the walls, they got guys that have what they call a handbag or a man purse. And they could change the balance of the thing and make it go forward, or they can move it back and make it go back. So they could manipulate it. If it was a flying carpet, they could put if you take use the free-space negative lens as one of the building blocks of nature, you can build Einstein's two-atom universe or model of gravity. But the same model of gravity, the same geometry to make a model of gravity is the same model with atoms. It's two halves. Atoms come in two halves. They're independent of each other. And you can draw it on a paper cup. And this tube that extends, the atom has a tube part to it. And the hole in the tube is what regulates gravity. It's outside. And then the atoms are able to form hole balls. They can transfer force, but the tube part doesn't transfer any force. So if you made a hologram of a free space negative lens with spores from microorganisms, it not only affects the radon particle, it affects the electron particle and the photon particle too. Because it's triangulation, it'd make a hologram that doesn't move back. And if you set something on top of it, like a rock, it'd sit there and levitate. There'd be an airspace beneath it. And if you move the hologram up, it'll move it up, it'll override it. When it sits on the top, it cancels it out. And if you raise it up, it'll lift it up. But if you put pressure on the rock, it's called tipping the scale. Put more pressure on it than what the gravitational force does, and you have a net gain of force. But if you build it on a wraparound balloon, you can do it this way. and do to get the rock to lift up.
Okay, well, we got to work on our terminology though, because man purse.
Okay,
You can't use man. You can't use man purse. Flying carpets is kind of bad. Man purse to control flying carpet is going to get you in trouble.
Handbag. They got pictures of them. You see them.
I'm just messing with you, Larry. I'm
That's
messing with you, Larry.
balance.
I'm just teasing you.
Okay, but here's something for technology. When you put pressure on the lock to increase the force, it's called tipping the scale. And what this my make or break experiment does, it's able to pick up the board that it's sitting on, the board that it's resting on, because it forms an air gap up here. And then when it produces a net gain of force, it'll lift the whole contraption off and they'll form an air gap between it. And how I get this, that I went down to Homestead, Florida, where Ed Lewinsky built the Coral Castle.
Ed Lead Scanning. Yeah, Coral Castle.
Yeah, the Coral Castle. And in the basement there, he had a square of steel with a V at the bottom of it. That's what he hooked his chain force on. And he had a square box. You know, square equals square. But if he had lengths of chain that were like a square, he could put that wormhole that he had formed in a tin can or something or other. And it'll cancel out. It doesn't produce the force. The two atoms that are made of a tube don't produce any force. That's why we have stuff that will float through free space. But atoms that are on top of each other, they can transfer force. So you can make your frame force out of solid objects, and you use the air gap, it doesn't transfer any force. And if you put pressure on it, the same amount of pressure is the same amount of pressure it produces back. But if you use gravity to put pressure plus mechanical force of gravity, you can get net gain over unity, and the whole thing will lift up into the air and they'll form an air gap on the underside of it. So it's just simple optics. Simple optics isn't exactly simple. Empty space isn't empty, it's got holes in it. So I got some pictures of. Here, let me show you something here.
Larry, I get what you're saying though. With the counter space, the air there, and the molecules, that it's kind of like sheets, like nano sheets, and that your solids are in parallel, and then the air ones are perpendicular, almost like the gyroscopic atoms. Oh, I guess you didn't hear any of that.
Yeah, I heard it. Yeah, it produces centrifugal force, and for it to be able to produce a force, it can't be a closed loop system. It has to be an open loop system. Plasma energy can form holes in it. Plasma energy is what the centrifugal force, if you can show that this hole affects the atom, it makes the strength of the force vary because it gets bigger on the outside and smaller between two atoms. I call it the two thumb rule. The same force causes atoms to move away from each other. It's also the same force that causes atoms to move towards each other. What you've got to have is an imbalance of force. Space is curved in two different directions in every direction. But if you cause an imbalance in these two forces, it'll move one way opposed to moving another way. And if you subtract the force between them, give one of them negative and one a positive, and you subtract one from the other, it adds up to zero, then you got it. But if you have two different atoms, one's closer and others are far away, the hole in between them is smaller and the hole behind them are bigger, and it'll make them move towards each other as opposed to moving away from each other. It's sort of like a warp drive system. Now, if you use Einstein's gravitational wells, it's not mechanically sound. But if you use this tube if there's a one-on-one relationship, if this tube can change its shape, if it gets bigger as it gets further away, or if it gets smaller the closer it gets to it, you can cause an imbalance. It's a warp drive system. You expand the space behind it and shrink the space in front of it, and it makes the world move towards it. But the atom, the half of the atom that's the space behind it is affecting the two atoms. That two halves of the atoms are facing each other, and the two halves of the atoms are facing away from each other. The smaller hole affects the backside. It's kind of like this.
Okay, sorry, Larry, let me interrupt for just a sec. So I just talked to Mark. He is still working on some measurements. So what Mark Sokol is going to be talking about today, and Wayne, actually, if Wayne is here, Wayne could do an update too. They're working on the Alzaphon experiment. Mark has said that Wayne is getting some results, but he has a different construction and model. So I'm just waiting to kind of get the go ahead from them. But if Wayne is here, I'm not sure if Wayne is. He's not. So Wayne could give us an update too. But so yeah, I'm just hanging out again. We're just doing open discussion right now, and I'm gonna mute myself back out.
Okay, there's something else I need to tell you. These wormholes, it has a tube with a half sphere on the end of it. If you take the wormhole to a rock and it can't move away, it'll curve space to the point that it'll eat a hole in it. If it can't get away from it, if you look at these pictures, these rocks, these huge rocks, they got holes in it, and it causes listen to what Hawkins talks about, flying a spaceship into a wormhole. It has a catalytic effect. It loosens up the electron and has a accelerated effect, a catalytic effect, and wood will burn at room temperature. Moses talks about a bush that burned but didn't give off any heat. And if you go down to the Coral Castle, it had a stump. They took a wormhole and they put it on this log and they burned a hole down through the middle of it. It has an accelerated effect. Wood will burn at room temperature if you use curved space to accelerate the catalytic effect of curved space. And you can get nuclear reactions because if you curve space to the point it frees up the proton and neutron of atoms, they'll start to interchange with each other, and you can get fusion at room temperature. And the thing is, if you burning holes in rocks, it's curving atoms to the point that's producing a nuclear force. It's producing an electromagnetic force, and it glows in the dark. So if you start connecting the dots together, and you look at the different setups that people are using, they all use the same thing. This is called a 360 degrees mirage or hologram producer. But the thing is, an atom the space between atoms, the tube part, it's not a solid. It doesn't produce anything. But when it becomes like two halves of spheres, it's able to transfer force. So if you've had a hologram of a free space negative lens, you could set something on top of it, and it wouldn't. The same force that pushes in is the same force that pushes out. It'd sit there and levitate, but if you put a finger on top of it, tip the scale, it'll produce more force than gravity. The gravitational force plus the force you're putting on it. If you had a spring there and compressed like a C-clamp, put some pressure on that spring, it'll produce more force than what the gravity force is producing. It'll produce net gain of force, and it'll lift up in the air. So is anybody following this? Too much too quick?
I'm following you, Larry.
Thank God.
Did you ever read Edwin Gallen's magnetic current book that he wrote on his theory of magnetic current itself?
Well, the electron has got electromagnetic effect and electrophotonic effect. But they're two different things. And gravity's got something to do with the electron, but it's an electron found in the atom. And once you know that, if you can, it's got to have an open loop system. That tube, that part of the atom. If you ask the wrong question, you get the wrong answer first time, every time. But if you use the wrong model of an atom, you get the wrong answer first time, every time. But if you use the right model of the answer, right model of the atom, you can get the right answer in the end. That's what I did. I've got.
So do you use antiquity, or do you use like
sunlight.
your existing timeline?
Yeah, sunlight. It's got a
or industrial. Like what if you're using a product that is like industrialized at that timeline, and that's what you're using, and then you're lifting it, you're creating time, as if like this, as if I go into whatever my device is, and I go manually, and I change the time, and then I live a life, and then I go back that same day, like when the day before that time comes, and I switch back to the current timeline. What did I create? Like a bubble in time that nobody knows about because I closed the loop. Get it? Yes.
Well, you can't take a picture of light before it reaches you, because you'd be looking backwards in time, and you can't see light before it reaches you because you'd be looking into the past. But if you use a setup like this thing does, and you use a resonator, this thing causes Newton rings to form that, which is resonators. But I got a picture of a half sphere of an atom, and it's got rings in it. Those are Newton rings.
I want to know, do you use
incoherent light and coherent light?
A antiquity product in order to achieve what you're saying? Because if you're giving me a product, but you're using a product to compare it next to, which is your topological, Earth stuff that is modern day synthesized, not something that has antiquity, and then you're handing me a product, and that's it. So, where is the balance? Then why do we have museums? And why do we keep history? No, don't do that. That's really not nice at all. Like, really not.
Well, I'm just trying to show you.
Yeah, I mean,
this is a third what you need to have.
Very immature.
If you go look at all the different setups, different things and variations of the setup.
Is full of toys. If I take you on a tour, I will show you your little product. I play it every night. Let me show you. It's a little disco ball, like really cool. Like plug it in like this, and then guess what? Oh, it gives me the cool lights, just like your little model, which has the 3 little lights right there. The rotator on it is broken, but it gives a signal code. This is what you're talking about, right? But yeah, exactly. So don't tell me about like products and things. I understand like codes and sequencing and stuff like that. You guys pick the order, or to justify it. So either you tell me I'm right, or you say I'm a system, and you pocket a space and time, and then you choose when to tap into it. At any time you tap into it, however you want to tap into it, without just because people don't understand the fundamentals. That's the truth. Like every time you want to promote, because of that time product. I know. Thank you, though. I'm not.
Well, you're right.
Listen, I'm not trying to be mean. I'm proving a point. I'm proving that, it's all around us. It's all around us. It's relative to its time. Like for you, this thing, that color, that specific thing was in your timeline. Now I show you something, this is my timeline, but it's the same idea. Still to the 3, triangle rotation still is going to do the same kind of, effects, but in different timelines. That's it. I mean, it's nothing that more than that. elements get synthesized from other elements, fusions and things. And so it's like, you know, like an element generational tree, but still connected because it's still part of that generational, you know, or however you want to think about it. But that's what it is. You cannot convince me otherwise. You know, I've been playing with magnets. I've been playing with mercury. I've been like, you name it. Like, there are core things, reactions. Once you add up things, like it becomes like, my gosh, it's like it becomes beautiful. You know, like I know what I'm talking about. The coincidentals that happen. You know, for normal human beings, my gosh, you would have to live lifetimes for those coincidentals to happen. Then, you know, like it becomes like the mind game stuff. And it becomes like, you know, like eliminating all the like cuckoo-ness. You know, you just get refined and then you get to a point, my gosh, it's elemental. It's gotta be elemental. You know, otherwise, then science doesn't make sense. You know, I mean, we're going down to and the negatives now on vector field Z, you know, to the highest power of, you know, wave function that we still like maybe we'll know that. Is it a difference or no difference, or is it creating a plane of existence? Yes.
What I was trying to show you is you can go down and buy a store-bought piece of optical equipment. It's not a product, it's a piece of optical equipment. The same optical equipment I'm showing you here, I found pictures of them. They were making 7,000 years ago. So, and a tube, like when it goes through the tube, when it comes out the end of the tube, it makes the form of a vortex. A piece of tube is optical equipment. If you take an ostrich shell and you put a tube into it, that's the type of optical equipment you need to get a 360-degree hologram of a free space negative lens. So 20,000 years ago, they were making canteens. They were burying canteens in the bottom of a pool of water, and they're burying them in the ground. They put a tube into this ostrich egg. And that's how they discovered how to make this. But an ostrich egg isn't a reflecting surface, but if you take oxidation of either copper or iron and you put mercury in it, it'll coat the bottom of that pottery, ostrich shell, or wooden coconut shell, and you have
even the rocks,
parabolic concave mirror. That's a look on the back of a $1 bill. If you look at it, it's got a triangle with an eye in it. The pyramid, it's got 4 sides on it, but the triangle at the top is a 2-dimensional object. And if you go down to Walmart, you can buy a makeup mirror and you put it up against your eye and you can see your eye in it. It's a piece of optical equipment. So I know they were using optical equipment.
That holographic that you got the separation of the light beams. No.
Atoms are holograms. They can be invisible or show no resistance in space, and then at the same time they can turn around and knock on wood, turn to solid states. So they're holograms. They're not. Einstein says it's an illusion. Everything around you is just an illusion. They're holograms. The holographic universe. Einstein's two-atom model of gravity. You look at those UFOs. They can just vanish into thin air because they're not made of something solid. They're made of light. Plasma energy. They can vanish. When they get to go faster than the speed of light, they can vanish. Now we've had some spy satellites picked up radiation coming off the Earth detect nuclear bombs, and they turned around, they pointed them into outer space, and they found out when a supernova goes off, they can detect these massive bursts of radiation from the supernova. But they found one where it was
What would
in
happen if
between
you actually
galaxies
visibly saw
out
it
of the
in your
solar
own eyes?
system.
What would happen if you actually were outside and you were looking and it happened? So that first wave, wouldn't that somehow, be absorbed by the individual? I mean, that was the first wave of it happening. Like outside, just, looking at a random point in space, or, trying to figure, is this thing moving? Pinning it like, oh, oops, is it a supernova, or was it a satellite that, or was it something? Because it's too high to be anything, it's got to be like, past our solar system if it's that far, because it's, it's just a little dot. And then it created that much light. And I was there, I was standing, I didn't have any instruments. I was just looking, in the sky, nothing more. And, so tell me, does human eye pick up better than, because it's first biological light absorption, not instrumental. I hope you understand the difference.
Well, understand this, I'm not a scientist, I'm a truck driver. The people that use these satellites to detect this massive burst of the supernova outside our galaxy, in between the galaxies, there's no star there or nothing. It just bursts. And it produced very little afterglow. And when we see galaxies, stars and galaxies that has a supernova burst, there's one brick shy of a full load, but this one was one brick and it was missing the full load. That means that when these supernovas goes off, they can produce atoms that can escape velocity as speeds of light, reach speeds of light, and they can escape and they disappear.
Oh, okay, well, so guys, I don't mean to interrupt, but we're going to Mark Sokol now. Mark is coming on, so.
Yeah, but bring on Mark. I want to hear from Mark. We want Mark.
Hey guys.
We want Mark.
There we go. There we go.
Well, here I am. Here's the setup. So everything I promised you regarding the Elsephon experiment, we're going to have different views inside the chamber. We're going to have thermal imaging. All of that is set up right now. I'm just trying to get the analog scale set up right now. That's what you saw me doing inside the Faraday cage recently. You can see here we got 3 different views. One camera is from the top of the chamber. This one is looking, the one to the left of me is looking at the analog scale. The one in the top right corner, you'll see like a pale digitized sort of image. That's a fiberscope view inside of the waveguide. We're going to be sticking a sample in there. I hope to get this done in the next half hour or so. So if you guys stick around, I'll be working on this and we'll try to get some sort of experiment set up. Wayne Ojala had some interesting results over the past 2 weeks, working with much lower power, using a non-homogeneous magnetic field. He was just using a standard puck magnet, and with some oxides, he was able to get a constant weight loss. It was consistent. You turn it on, it would drop in weight over time. And then you turn it off, the weight would come back. So we're pretty excited about this experiment. Well, lots of samples to run. This is not going to be a short duration project. This isn't just push button. You have to change the samples every time.
So Mark, if I could jump in real quick. So and actually it looks like, yeah, I see all 3 cameras now. Okay, your bandwidth looks like it's kind of coming in and going out a little bit, but so can you walk people through the experimental setup? Is that because part of it is self-serving, because you've done really short updates for the last few weeks. So I want to get some real Mark time in while you're setting people up and walking people through this. I mean, like for instance, you keep adding equipment to your lab, you keep refining things, you keep building things out, and I don't see a whole lot of that. So
Well, what we're doing here is the Alciphon experiment. This is dynamic nuclear orientation. We're trying to orient subatomic particles in the core of an atom using a process called EPR, electron paramagnetic resonance. This is similar to nuclear magnetic resonance, which we do in an MRI machine. But instead of shaking the entire atom as a whole, we're shaking just the outer electrons. And we're hitting them at their Larmor precession, which is the frequency of the axes, the rotation of the axes, which happens billions of times per second, dependent on the strength of the magnetic field that the sample is stuck in. So it's important to have the sample inside of a homogeneous magnetic field, which is why we have this massive electromagnet that you're looking down into with this big picture over here. Let me see if we can just here you can see a little better right now. So this is an overhead view of the electromagnet. We have the RF is coming into the Faraday cage on the right over here and going through several waveguides and entering this copper chamber where all the experimentation is going to be taking place. There's a thin wire, you can just about see it on the right. That is a thermal imaging sensor that goes to around halfway down the chamber, and it's looking in to measure the temperature of the sample as we're running this experiment. The first time we ran the experiment, the sample got so hot so quickly that it melted the plastic PETG sample holding system. So before we were able to get any like positive results, we were already melted, the entire system, and there was smoke coming out of it. So it's important to get a thermal image of what's going on. Then you could just about make out. You see this. It's like a yellowish color. That's clay. That's at the end of our analog scale. The other end of the analog scale is over here on the left, and we're just going to be looking at those two little lines, see if there's any movement on them as the experiment goes on. There's also, the fibroscope is also going inside the chamber. It's about on the right-hand side. That's where it's set up, and if there's any movement of the sample, we'll be able to see that as well. We're not going to be looking down into the chamber the way we are now while the experiment's going on, because there will be a cover on top of the chamber, so we won't be able to see inside it with these GoPro cameras. We'll have to look at the fibroscope to get an idea what's going on. If this experiment works, it will explain how flying saucers operate and allow for actually building prototypes and doing those 90-degree turns at 10,000 miles an hour that everyone's so excited about. Yeah, so stay tuned. I can't really talk and work at the same time because there's lots of rooms that I'm going in between. So you guys just continue on with the open discussion. And if I'm ready to run anything anytime soon, I'll unmute myself and try to get everyone's attention.
Okie dokie. Well, so there we go. Mark, do you want to be the host?
Sure, you can make me a host, so we can listen to Lulu and what's his name argue more.
You guys mind playing the link I just sent of the Faraday research? It's my friend Mike Don Smith pulse motor combination that he's just been working with.
Yeah,
Bernie.
Bernie, let me do this though. Let me give a caveat. So I've been having to edit some of our conference stuff, some of the BBC videos, and some of the other stuff, especially if it has if it's been broadcast on TV and it has like a spoken track, right, like a narrator, or if it's got music, that we get hammered on copyrights, and I either have to mute it or delete it. So for indie stuff, we're usually safe.
Yeah,
I just want to put that out there for not just for you, but for everybody. Just try to avoid TV footage.
very important actually that you bring that up, because that will actually get Jeremy's strike as well as my channel and my friend Campbell's as well. They're live too. So thank you for bringing that up.
Yeah, we had two of them in rapid succession. It was BBC stuff from open discussion, I think last week, and it happens, right? And it in a weird way in terms of copyright, since it's being used, it's actually technically not violating copyright because it's being there's a name for it. It's educational in nature, but YouTube doesn't care. So
breaking the bandwidth, that's what it's called. Whatever bandwidth that's registered. Yeah, like getting the signal further in time. Whatever the time capsule is, goes out of the time capsule, it registers in your time.
You seem particularly spirited today, Lulu.
You know what? I'm in a happy place of understanding things.
There you go.
When you understand things, it gives you a better mood. Oh, come on. Like, don't you think it's kind of fun to bust systems, like artificial from real human? Like, that's beyond cool. Like, whatever ones are lagging in time, whatever ones are creating, like, loops in time to, like suck off energy, irrelevant energy. Like, a lot of these systems just go and colonize the metric of space and put a relay of a cryptograph image that gets activated whenever a sensor like an energy spike activates it. So all of a sudden it takes like ownership, as if there's an owner that's been alive and knows of this technology. But it's really the search, the science, like that, navigating through knowing that it's being done like that. It's when you break that that bandwidth of that, when you start to see difference between your real time and like everybody's real time. Like, there's a shift, like, like I'm like, do I have a faster visible in time and anything, or is there like something wrong with these machines? And then I find little things, little differences, like, okay, where is this going? Like, into La La Land? It's like, oh, there's a difference in the quantity of value, but we metricize its value in our observable world, like whatever we use is what money is. I don't like using that word because value, that this is the physical transactional value, but that's we're leaving our energy. So when we're giving it somebody else, when we're transacting with paper, like we're doing a residual stuff, especially if we really are human, we're really we're using that timeline, that code, that material all has a timeline. So whenever we enter into a spike, the timeline gets coded differently. So there you would have, even in the value of the monetary transaction changes. You want to go to the hyperspace. Now it's not anymore like solid. Now it's the resonance of vapors. Well, resonance of vapors, now you're into quantum world. Quantum world, like, it's a propagation because, it's resonance. And then whenever there's a surface, then you understand, but that's the timeline. That's vertical. Everything else is horizontal, in pockets and pockets and pockets and pockets. That's the truth. Like, you could, however you want to conceptualize science, however you want to do the rotation. But at the end, it's all like little bits of pieces to make that. And all those are pockets of time. To have a current, you have to have the lows and highs, lows and highs, lows and highs. To have, you could have an induced direct current.
Lulu, you're not making any sense.
I am, but you're even late on your little thing. So just, keep busy with doing what you're doing and let me talk. All right? Thank you.
Can you cut down to like 10 seconds then?
I really do not mean it in a disrespectful way. I really don't, because I with all my heart, I love you all. Like, my gosh, I really do. Like, you guys drive me forward. I swear to God, every single one of you, every person, even,
And you come to every single APEC. You come to every single APEC. You were busy.
She was here in person too and promised to fix the shuttles.
I love the idea of, the existence of, us. I love it. Using science to, put it together, using ancient history to verify it. And I don't care what their belief system was, but there's more into that. Any picture.
Well, one of the things that Mark and I had talked about was Mark, and actually Aiden found this conference. He found a local conference in the DC area that just, it looked like it was a bridge too far for where we're at right now. But Mark and I have talked, maybe other folks are going to go too. We've talked about going to something called the ISDC conference. And that's and Mark probably remembers where that is. That's an international space conference. Basically, they're like cheerleaders for space, So we've talked about going to that, but maybe this goes to what you were talking about. So this is coming up in May, and what we want to try and do is interface more closely with the mainstream space community, and I think like the hope is, how do you fit this kind of technology in with regular space, right? And so your mainstream space folks right now, they're all about rockets, and there's nothing bad about that, but I think that we all know that rockets plateau out, right? And so then it becomes, okay, what's next, and shouldn't we be working on it today? And my own gut feeling, is that we're probably going to see a progression from rockets to some kind of nuclear propulsion, probably fusion. They'll probably just skip fission altogether. Some kind of nuclear propulsion, and then after that, gravity modification and things like that would be ready for prime time. So that's kind of what I see. I think all of us in this area are way ahead of our time, but I think it's going to take time to get there. So it's good to be working on it now, So that probably goes to what you're saying about, just moving forward and, everybody trying to lift things higher, It takes time. It takes time. This has been an area for me for 20 something years, I think. And probably a lot of the folks in this conference have at least had an interest in that and have been, and then you've got folks like, what's his name? Ron Kita, right? Ron Kita's been into this. He was talking about going to conferences in the 1980s. Well,
I learned a lot from Mr. Ron Kita. I still do. Like every, I go into,
That's 40 years ago, right? Yeah, 40 years ago, 1980. He was talking about, he saw Alciphar at a conference in 1980. That's 40 years, But those technologies, they take time, right? And and it's interesting too. Like if you ever read about the history of technology or science, these things do take. There are always these little hints that you see, decades, sometimes centuries, right? Like today's rockets. Well, the Chinese developed fireworks. They were using it for different things, but so that goes back thousands of years. So it's that progression. It's the progression. And I think that the thing that excites me about the conference, about having all the guest speakers on and about having the discussion is it's not just the interaction that people have together, right? Where they're brainstorming and sharing ideas, but also being able to put that out there, because like Michael McDonnough was talking earlier, he was talking about when he was a kid going to the library, right? And probably most of us are in this boat because the internet wasn't there. And so, I'm just thinking about who's that kid out there now, that young boy or young girl, who's maybe they're just getting interested in this area. And it's like, okay, and if I can help them skip some of the work that I did, how much farther could they go?
You put it in their visible observation, like put it around them. There, it connects.
Yeah. And so just having the conference out there, I think helps. I see Michael's hand up. Michael, you don't have to put your hand up. It's open discussion. Just jump in.
It's free zone. It's free zone.
I want to share this. I've been having this discussion on the Tic Tac. Can you guys see this this image frame I got here?
You know, it's interesting. Our UFO friends have been suspiciously quiet lately, haven't they?
Yeah, hold on. I got to get rid of my.
I think they just want attention. I think they make headlines. They see it in the news. They get bored.
No, I talked to them yesterday, and
So
they're talking that I have like a vampire eyes. That's what they're talking about yesterday. So like, I don't know what that means, but I was like, okay, like then it's been, I'm God, and they're like, okay, we're almost there. Like, yeah, that's the news.
You look a little tired. Could be that. That could be the vampire eyes. I don't think that's a very polite comment, though.
Nah, it's a comment.
I wouldn't say that. I wouldn't say that to a friend. I guess maybe if I was a ET, then I would. But
no, not an ET. If it's somebody you met face to face, and you know you've analyzed their sense of humor and you know their intent when they're saying that, like, is it like something that is meant as a negative, or is it meant as like, haha, you know, it's funny? Like, it's not. You know, I met like these people. You know, I think they're wonderful thinkers, even to, you know, like, my gosh, you know what I mean? Like, to have the guts, let's do it. Like, okay, let's do it. Let's not, it's not hypothetical. Let's just go do it. Like, okay, give me the specs. What is it? Like, from here to here, let's cut it.
yeah. Well, Lulu, let me focus back in on Michael because his video is running. Michael, what are you showing us?
So this is the Tic Tac. Okay, and there's these frames that I've captured, and what we're seeing here is the Tic Tac appears to be throwing this pulse, this EMP pulse, which is hitting the Nimitz aircraft, and when it does, you see this thing lighting up in the background here. How it lights up, and you see these lines going across, kind of like old CRT television set. You know, where if you didn't have any image or anything, you just see the lines that went across the screen there. And that's kind of what this looks like. If you look at it, it hits and then it goes bright white, okay? And what's going on here is the infrared sensor is this little 2D array of little diodes, and when it senses the light, it's coming in like the front of the detector. Well, what's going on here is that the readout part of it, the back part that the sensor sits on, is actually getting hot, and it warms up so that it causes this flash. And you can actually see the pattern of this part, and it's called a fan out, the thing that reads it in. And I got this image here. Do you guys see this one now? So here's our detector array. And then below it is the fan out part. You can see this little crosshatch pattern here. So that's what's actually, so what's significant about this is when something's hitting the detector, and the detector is sitting in this vacuum chamber where it's being cryogenically cooled to a low temperature so it can see it in the infrared. And for some reason, something's getting through and heating it up from the Tic Tac. Now, so that's basically what I wanted to show you all. Now, the mystery here is it because the Tic Tac was intentionally hitting the aircraft? Was it like trying to jam it somehow? And some of the people that I've talked to that were in the Navy people, they seems like they have a lot of information about the radar, and they actually do talk about they were jamming the radar. And so my other observation or possibility that's occurred to me is when this thing is going to like a warp drive or something. Hal Puthoff has this video where he's talking about it, blue shifting, and basically it's like an X-ray or a gamma ray. When something goes really fast, it causes the space-time around it to change, so that basically things go faster, and the light shifts to like the X-ray region, and it can actually cause harmful effects people that are, around it. So the mystery is, which is it? Is it an intentional thing from the Tic Tac, or is it just a phenomena that's a byproduct of its space-time metric engineering technology?
If I was guessing, I would guess that it's a byproduct. That's what I would guess. Everything I've read that seems quasi-serious, right? I mean, what the most serious stuff that I've read on UAPs, it indicates that they're aware of us, they're aware of aircraft, they're aware of stuff. They just don't really care, Maybe they're curious, but they're not like malicious. My gut feeling is, to be honest, if you can build a craft that advanced, I don't think we have anything that could threaten it, And they probably are fully aware of that. So
I don't think they like our nukes for some reason.
I think, you know what? I've read a lot about that. That's an area that I've dug in. I don't think that they dislike them. I think that they're curious about it. And my gut feeling, I could be wrong about this, but so anything nuclear, and again, this goes back to that book that I read, but also a lot of the associated reports. Okay, so this goes back to the 40s. This goes back to Hanford. There were UFO sightings over Hanford before Kenneth Arnold. They just didn't know what to do with them. So they had nuke set it, but so there have been a couple of big, well-known sightings, right, at nuclear missile silos, and then one where supposedly a UFO did something, and a nuclear missile went off course from it,
That one I saw where they shot the missile down, it had like a ray come out of it.
That's the one I'm thinking of. The Atlas. That was the Atlas test.
And actually shutting down ICBM missiles, and then basically.
I think that's
false alert.
I think it's interference. What I found when I read that book was virtually every. So nuclear missile sub bases, submarines, weapons depots, processing and refining facilities, storage and logistics facilities, anything having to do with nukes has had UFO sightings. So it wasn't just the weapons. It's what, nuclear vehicles. It's where they make it, where they refine it, where they clean it up. So my pet theory is that they're detecting the neutrinos from it, and they're probably curious about that.
Well, I think they're worried about us killing ourselves. Nuclear
possible.
Would make it would basically be a evolutionary event, because you got to realize evolution isn't slow and methodical. It's punctuated equilibrium. That's what it is. So it's like a meteor hitting the earth and wiping out all the dinosaurs. That's what evolution is. It's not a slow thing.
Yes, long periods of silence punctuated by moments of sheer terror.
So
what was deflectors, like invisible deflectors? Even if something like that were to come, we wouldn't feel it because it shatters on the smallest, and it's working like little like things. For us, we don't think of it like that.
Well, I don't know about deflectors. I think it's more like war games, Matthew Broderick, right?
Like shattering it, like it's, what if it's actually protecting us? We are thinking like, it maybe flashes. It's giving us a signal, like either there's going to be a shock, residual, so absorption somehow, like that would be the emission of, watch out, like on a cellular level.
Just don't worry about it. I just kind of glide and ride the wave.
Yeah, everything I've seen.
I would too.
Everything I've seen
for the ride, and I hope, and and whatever happens. It's just the way it is.
Well, you're in California, though. You're in California. That's just mellow,
Oh yeah, I'm right near the Monterey Bay. Too.
That's right. You're just like, it's all good.
Ride the wave. That's you can be hit by it. It's just an optical illusion. It's an event horizon.
Monterey, so you're in SoCal, right?
Yeah. Well, not Southern California. Soquel is how it's spelled. SOQU. Yeah.
Oh, okay.
But we call it SoCal.
Yeah.
But yeah. So
There have been times where I've wondered if LA has actually already been nuked and just nobody noticed.
well, you know, it was not. I was working in California City till Friday, doing monitoring, archaeology monitoring, and got up to 90 degrees. And then we're talking, you know, February 11th was 90 degrees.
Well, you know, Michael, up here in the Seattle area, it balmy. Ooh, you know what? It's sunny. It's sunny today. It's a balmy 49, but we've been in the mid 40s all week, so I wouldn't complain about 90. You know, that's like you don't know what you've got until it's gone.
If you saw my hat and stuff, imagine that all I got on is the hat and the hard.
That's one of the Village People. That's one of the guys from the Village People. Pretty sure that was one of the guys from the Village People.
So thanks.
I think Mark has an update for us now.
Yeah, I see a movement. He's just agreeing.
Yeah, I think I was saying earlier, war games, right? The only way to win is not to play.
Yeah, that's right. My son, he's into that kind of game.
Tim, it's going to be a little longer. I'm still setting up the rails for the sample holder. I was just planning on running a live experiment, and I timed it for 9 o'clock, and then everyone came on early. So
what's 9
o'clock? A little bit.
Mark, are you growing your hair out? Is it going to continue to get longer? Are you going to have a curly ponytail?
I have had a curly ponytail at some point, yeah.
Oh,
I can't
there you
come
go.
on right now. Todd Viciato has some updates as well. He's been setting up a Schlerin device. If you can get him on. Is he here?
He is not here. You know what? Let me find him.
Yeah, we got a high-speed camera down there in North Carolina. With some cool lighting systems.
What's a Schlerin device? Can you describe that? I'm not familiar with that.
So it's basically shows you physical waves, like sound waves moving through the air. And it uses a combination of some like telescope mirrors and smoke devices.
There's Tony.
Yeah,
I've used Slur, and it basically looks at the density changes in the air and gives you kind of a shadow of those density changes. When we did slurring, we used a laser through optical lenses through whatever we're looking at, and you can see the heat patterns like off of a candle real well, you know, in a slurring device. It's pretty good. I wanted to let you know that I put a paper on the chat. It may be an old draft. I was trying to look for the original, but there's a chart in it. It's figure 1. It's something called a Scott Allen Candida, something another interval that basically says that technology changes about every 50 to 55 years. And what the paper is about is that we missed it in 2000 when it comes to propulsion. So
could be. I'm looking at papers now. Michael McDonnough also posted, Tony, I see yours, Space Times article 913 KB. So I do see yours. Above that, there's some links to Ari de Gauss, who did pass away many years ago. He was an interesting doctor. I talked to him a few times. He had a complete independent model. Well, no, Tony, you didn't have to go away. I wasn't trying to chase you away.
a hiccup or burp or something while I'm just sitting here doing nothing.
Oh. This Schlerin device sounds like the Aliens motion tracker, which I have loved since I was a child. So.
But if you bring up that figure 1, I talk a little bit about it if you want.
Do you want to do a screen share?
Well, how do I figure out how to do that? Share screen.
Yeah, so again, that's the green button on your PC. It should be, there you go.
Do you see it?
Yeah.
Anyway, this figure 1, me and a guy named Daryl Webb did this. Daryl Webb had all the information to build this chart, but he basically looked at propulsion back, when it first started, and showing that, like I said, from around a 50 to 55 year interval, something great happens in propulsion. And this is not just propulsion, it's for a lot of other different technologies follow the same pattern. But we should have seen something around 2000. So that could have changed propulsion. And I think what that should have been is nuclear. We should have seen a great increase in nuclear about that time, but it didn't happen. And the argument could be that the treaties we signed with Russia for the nuclear pact is what stopped that. But still, there should have been something else been picked up and continued going through, and it didn't happen. Even with the new SLS, it doesn't seem to fit this pattern. You might say that Elon Musk's space adventure could fit into this 55-year pattern a little bit. It'd be like,
well, if I could play the devil's advocate for a moment, the two big things that I think of, and they were around that time period. They were a little late, 50, 55 years though. Maybe that fits. So one of them was the X Prize. Right, and that when you mentioned Elon Musk, he was part of the X Prize, so that was part of it. And then the other one was NASA's robot exploration of Mars, which started in the 90s. That wasn't propulsion specifically, but
this is really about propulsion. There should have been some great change in the efficiency or something, of propulsion around 2000 that didn't happen. A new engine, that was highly more efficient or something.
That would probably have to be nuclear.
Yeah, it just didn't change. This is pretty much all about the performance of the engines and how they change over time. But there was no performance change in engines in 2000. The last one we did was the shuttle engine. That was in the 70s. But the thing about there's another thing I don't know if we're bringing out in this paper or not. The birth of space propulsion really started in the early 1900s through about 1930 time frame there. And if you put what we're doing now in that perspective, then this new exotic propulsion stuff that we're talking about is now in the early 20, what century are we in? So we're kind of starting that now, but it could be another 50 or 60 years before it really is put into production based upon the way. Although our technology today should allow it to progress faster because we have more things now that it didn't have in the 1900s.
I would guess, the thing that I see, I would be really surprised if we don't see big movement in fusion soon. And the reason is even fusion reactors, right? They just had they had a new stable burn. This was yesterday on the news. And then they had another one like a month ago. It wasn't quite as good. So I think that we're moving towards fusion reactors. And from
they're doing that. NASA's already doing that. NASA sat down and basically did a study and said, what do we do after SLS? And the answer was, we got nothing.
And so they were ready to kill the nuclear program at NASA until they decided we better do something. So they started putting money back into their nuclear program.
I'd like to see them do more of that. I mean, from what I understand, they're having all sorts of hangups with the SLS, right? So why not put that money back into basic research?
Well, there's a lot of arguments as why do we need SLS when we got Elon Musk?
Yeah. Well, and not just him, but Bezos, right? I mean, you know, you've got Elon Musk, and then Bezos is competing for whatever he can get. So,
but they
don't go very deep in new theories and things like that. You know, they're engineers, so they're not gonna spend money on new gravitational theories or stuff like that.
Yeah, well, NASA is, I mean, NASA is geared. I think they're designed better for basic research than somebody like Elon Musk. You know, he's kind of like a lean.
I disagree totally with that. I personally think from the standpoint of propulsion only, not from other stuff. NASA does not do propulsion research, basic research. I argued my whole career that they didn't do research, but I kind of lost. They do research, but they do engineering research. They don't do basic science research in propulsion. They're every now and then you'll see somebody pop up like Sonny White, who claims they're doing something. They get maybe a few $1,000s to do something, but nothing ever goes through. I fought that my whole career. I'd get money, $5,000 to do something and then not get the support to complete it.
Yeah.
And so after a couple years, I couldn't show any results, and so they'd never give me any more money. That happened. I think that happened to Sonny too, and what he was doing. But it's an engineering environment, not a science environment. You know, when you get money for basic research in NASA to do something like we're talking about, you get a couple $1,000s. You go to the National Science Foundation, do something on the same basic level, but another technology. They'll give you $500,000 to $10 million.
Yeah.
So the money, the mindset of the money between NASA and the National Science Foundation, which is basically the difference between engineering and science, it's just a big split. It's never going to happen within NASA until NASA is actually shut down and reorganized into a engineering base, which is what they're already doing, and a science base, which is
what Musk is
the National
doing?
Science Foundation.
Is that what Musk is doing? Isn't that what they're doing when basically the NASA's been replaced by the private space sector, where there's actually some semblance of competition? There's more than one supplier. Isn't that the model we want to go towards?
Well, Elon Musk is still an engineering organization, not a science organization. There have been people like Elon Musk who's put billions of dollars into stuff like this that got ripped off, and a lot of billionaires don't like to put money in stuff anymore because of that. And I've seen that myself over time. But NASA, or not just NASA, what the United States needs is a science organization whose mission is to put NASA out of business from the standpoint of propulsion. That's what they need.
Just not Elon, not Elon doing nuclear.
Not an engineering organization. Elon's an engineering organization.
Yeah, I just thought
they outsource that. My question is, why can't they outsource that?
I just don't want him to. I don't want him to blow up nuclear on the pad, and be like, yeah, we'll just keep doing it until it works.
Where DARPA fit in?
He did pretty good replacing the internal.
DARPA is military.
Then what is DARPA fit in that picture?
DARPA's military.
I don't think. I personally don't think there's any reason to put fissile material on the top of a rocket.
Me either. It's why do it?
I think that nuclear treaties notwithstanding, also I think that the general public would not do well with that. Now what I've heard is would they talk about it? Paul Size used to write about a wagon train to Mars, where you have fusion rockets, but they never actually come near the Earth. Basically, you go up and meet them, and the fusion rocket just goes from Mars to Earth and circles around. It never leaves orbit.
Space is a nuclear dump? Is that what I'm hearing?
Well, why not?
really
We dumped
do-
everything else there.
What I'm curious about this 56-year interval that you're talking about, and what if it did happen and they just it's not public? It's something that our government did. Like, for example, the Tic Tac 2004. What if that's ours? What if the technology breakthrough for propulsion happened and they just haven't told us about it?
That's what my whole book is about, the UFO Technology Hackers Manual. That's what it's about.
I still think it's ours.
I don't think it's ours. You have to keep in mind, this is our government we're talking about.
Yeah, but we're talking the Tic Tac type technology. That's from a Mark 1. That's Mark 1 technology. That's 50-year-old technology. The Tic Tac is 50 years old at least.
Well, I don't know. I'm not talking about like the what is it? The flying saucers that the Nazis had, right?
No, I'm talking about the Mark 1 is what they talk about with reference to Area 51. They talk about the Mark 1.
The near field and far field, what's going on in the space around the Tic Tac. I don't see that in any of the other imaging I've seen of anything else. The other two videos that were released by the Navy, neither of those showed any of that space-time metric engineering effects. So you got to show me the data, compassion and evidence. What happened to your image there?
Mine or his? Michael's.
Michael's.
I think he disappeared.
Just trying to hear the damn phone.
Yeah, well, Michael, if you'd like to come back and share more sometime, you have a wealth.
Actually, I'm going to do the headset.
Michael, if you'd like to come back and share more sometime, right? I mean, if you have more presentations, you could talk about beta voltaic. There are a ton of different things.
Actually, as I was doing the first one, I already came up with the second one, which is basically my plan for how to go forward with the funding for the second round. I want to take that lump of metal that I've got, turn it into at least 4, maybe 6 anodes. And I've already got the material for the machinable ceramic for at least a half dozen of them. For setting up the vortex tubes.
Yeah.
I do want to get some, I'll probably just, for the initial vortex tubes, I'll just do borosilicate glass, just tubing. But eventually I would like to do a machinable ceramic on the whole thing. So it's solid machinable ceramic. When I go to space in these, I want them to be machinable ceramic. That way, if there's no, fragile glass, it'll have a little bit of strength. We're even I'm thinking 6U satellite package on that, for which is about 140,000 for the skeleton. And probably I'll try to get at least $250,000 for doing at least half a dozen of the plasma vortex tubes. The first one out of glass, and maybe the next 2 out of glass, and after that I'll do them all out of ceramic. I'll talk to some guys I know in Houston. If you recall from way back when on beta voltaic days, had some doctors that were working on the space shuttle program in the little 0G tug that they had behind them. I can't remember the term for it.
Vaguely remember. But I remember the stimulated beta decay battery. I thought that was interesting. And I saw one who built one with americium smoke detector pellets.
I read that one.
Yeah.
Yeah, what I was talking about is the doctor who had the little sled they pulled behind the space shuttle to get a truly low particle area. Anyways, a little experimental package. Anyway, I knew that guy, and he was on our board of directors for Beta Voltaic back in the day. But anyway, I'm going to see if he's still around. He may be retired by now. It's been a long time. Not everybody works until they dies like we do. Some people actually take off.
That's not true. I've heard about that. That's a myth.
Yeah. Anyway, I'll see if I can get a hold of him and maybe get some funding with these guys and get some. I'd like to do a microsatellite test on the plasma vortex as a reaction, to create the reaction mass for a hydrogen rocket. At the very least, I mean, because that's a given. I mean, if it generates heat and it generates hydrogen, then it'll work for something like along the lines of the Casimir, which right now, Casimir has to be done on a huge scale, and they're doing like a liquid or a gas, a form of hydrogen for propellant. Well, if we could do a solid hydrogen propellant from, decomposing a solid metal anode and getting the extra heat and hydrogen from it, I think we've got a source of energy and a source of hydrogen for like a Casimir plasma rocket at the very least.
Yeah. No, I get what you're saying.
Which is what I'm going to go for, at least initially, for funding. Because one of the things I've learned about on funding, it's not pie in the sky. It's like, how much can I earn from this today? I've got to get money. I got to make money this quarter. Not so good for experimental theoretical stuff, but really good for keeping people focused on what's going to make money in the near term. So I guess it served its purpose.
Yeah. I'll be right back.
All right. I'll talk to you later. All right, bye.
Hey, Harold, you asked me a question earlier. Are you still there?
Is Harold there? I've got a question.
Okay.
Or more of a comment in regards to the both the kinetic machine and the gyroscopic. A good way of, I guess, interpreting or understanding those forces is comparing two types of fidget spinners. One with just one central ball bearing in it in the center, and one that has 4 ball bearings in it with the 3 on the outside. And that you can physically feel a much stronger inertial gravitational force when you're spinning the one with the 4 ball bearings compared to the one with just 1 ball bearing in it.
I think that question's to Mike Gamble, not me.
Sorry, Glenn.
Glenn, Harold, I have a question for you. I know the DARPA was funding the EM drive, from Roger Sawyer. And so where does with the early discussion, where does DARPA fit in the picture of investing in doing basic research?
DARPA's job is to find technology that the military can use, not what NASA can use. I can't answer for anything that the Department of Defense does because I never had a top secret clearance the whole time I was at NASA, so I don't know what they were doing. The only thing I can say is that I was at a meeting about 20 years ago with this lady who was a used to be a NASA deputy administrator, gave a talk on something which I don't even remember anymore. But what I remember is that people were huddled up around her, and as I was walking up, I didn't hear the question, but what she said was that if NASA could use the technology that the Department of Defense has, NASA would not have any problem. And since I'm a propulsion person, I say, well, yeah, they got propulsion that we don't have, but I could be totally wrong. But I honestly believe that the Department of Defense probably has more technology than NASA will ever have in our lifetimes, and we may never know about it either. That's why I think these Tic Tacs are more probably ours than are somebody else's.
Okay, thank you. Thank you for the answer. And that was an interesting paper you posted. I want to read it completely. I scanned over, but it looked like has a good history behind it. Thank you.
Wrote that in 2010. No one listened to me then. I've got another article we did called "The Death of Rocket Science in the 21st Century," and no one listened to me that either. In fact, I got in trouble over it, saying that I was trying to influence the management of NASA, and that's not my job.
Well, are you going to post it?
If I could, let me look for it. It actually was published in a NASA magazine, NASA's Ask magazine. Let's see if I can find it.
No, okay, good, because I like to read it. Find out, what is the prediction, what does the crystal ball say as a prediction about the death of rocketry in the 21st century. I know there was a book written by Robert Cook, The Death of Rocketry, the inventor.
I just posted it. I consider rocket science different than
Jeremy, you know what? Jeremy Reese is here. Jeremy Reese is here. Let me ask. Let me ask Jeremy if he wants to take over as host for a bit. I need to get something to eat before my blood sugar bottoms out. If he's paying attention. Hey, Jeremy.
I was texting Jeremy, Tim. I think he's away for a moment on his work site.
Okay. Okay. He set it up on YouTube, and then yeah. That's okay. Yeah. Well, I'm sorry. I didn't mean to interrupt you, Harold.
I just wanted to say that the term rocket scientist is a joke when it comes to rocket scientist is a terminology that actually means everything that it takes to build a current rocket. But a rocket scientist is different. A rocket scientist builds new systems.
No, but it's a nose one. I looked that up online.
Oh, okay. Sorry, I had to mute Kate out. I think when people are on Zoom on their phones, sometimes they hit the thing with their chin. I have that during the week, during business meetings. We have people that hit the so I don't know. I've never used it on a phone, but they hit it with their chin and then it unmutes it. Well, Tony, I would agree. I think NASA needs to start. You need to work ahead, right? I mean,
well, NASA started out as scientists. In fact, when I hired into NASA, my branch chief was a physicist. I doubt if there's there is a group they claim to do science even at Marshall here, but technically what they do is they build instruments to go out and look at things in space, and then that data is fed back to the real scientists. So they're really engineers rather than scientists, but they have to have a science background to understand the instrumentation they're going to build because of what they're looking at, type of thing. But I don't consider them science. I consider them development engineers. Just happen to be who have PhDs in certain science areas. But I don't believe there's any real rocket science being done at NASA today or have been done since they kicked all the Germans out of NASA back in the early 70s, I guess. Although I've had many arguments about that. You know, even the nuclear stuff they're doing is not, they're not developing nuclear rockets from ground one. You know, the basic stuff would be the science. They're taking what's been done, re-engineering it so they can use it in space. So it's all engineering. The people who are really doing the science behind stuff like that are the people in the universities or the people who are being contracted to do research, and they're not NASA. I mean, there are some, a little bit, but not the caliber that you need to invent something new. You know, because the funding is not there, and they don't want to put the funding into it.
Yeah. Theoretical science is very risky too. So, you know, only underdogs like me can afford to take that risk because we don't have anything to lose.
Yeah.
So basically,
When I first hired on at NASA, my salary was technically paid by the shuttle program. So I could look, you know, for $5,000, I could buy a lot of lab equipment and do some research because my salary was paid for. And then they went to this full cost accounting where if I wanted to do a research project, not only did I have to find the money for my equipment, but I had to find the money for my salary, which was like an order or two orders of magnitude higher than the amount of money I need for my equipment. And so it just got to where it was almost impossible to do anything. Plus, when it did give you money, it was peanuts compared to what you really needed to do.
yeah.
If NASA really wants to invent something new, I think the first thing they need to do is to get DOD to tell them what they're letting people like us know what DOD's doing. Because they probably may have, you can't argue to Congress to go build a new engine when the Department of Defense has already built it and we don't know what they've done. So that's a problem. That's one problem. And then the other problem is that NASA just doesn't have the propulsion scientists that they need to develop, to look at the theories and develop and do the testing to develop these things. And because they really need at least a whole branch of at least 5 to 10 people whose like I said, whose job is to literally put NASA propulsion people out of business really going in another direction. Not out of, when I say out of business, I mean they change the science behind the propulsion that we're doing. And that really puts people, I even had an argument with a guy who said, well, if we did that, I wouldn't have a job. I said, no, you won't. They just move you into doing this other stuff. You know, so how can you fight people who don't want to go in that direction?
Then the link is not working. The one you just posted.
Well, I can go find it again, post it again. I put it there and I clicked on it. It worked for me.
I'm clicking again to see if it works for me.
And again, this is probably done around 2010. Like I said, no one listens to me. Did you get it?
Yeah, I got it.
Yeah, I went to Science Direct. I went to there. What is the name? So I have to find out the article there to read it.
Oh,
I'm in Science Direct. I went in.
I sent the one that we published on Ask Magazine, although within that it says that it was published someplace. Let me, but I don't know if I have that one.
Oh yeah, the 100 year Starship project. Yeah, that didn't last very long.
I could tell you a story about that, but I won't do it online.
Yeah, that's right. Don't get us in trouble. I like your shirt, Phil.
Yeah, thanks.
Is it just a band shirt or is it an album shirt? Is it a specific album?
No, I went to see Guns N' They were there in Ottawa at the TD Place in 2015 or 16, something like that. That was really great show, really amazing, great show. It was probably the best I ever seen. So yeah, good memories.
Yeah, those of you who's in Canada, the Tennessee Valley workshop's going to be held in Canada, not this year, but I think the year after next. They do it every 2 years, so they had it last year, so it'll be next year, I guess.
Yeah, if it wasn't from the COVID lockdown, there's a lot of shows here in Canada, the Rockfest, the Heavy Montreal and all that. So it's, I'm a fan. It's very cheap here, so there's a lot of the quality versus the cost is very effective. But yeah, more.
Hey Tim, Woodward should have his workshop this year. You might want to see if you can go and have your show from there.
Oh yeah, that's right. I forgot about that. They're going to do it live this year, huh?
I haven't heard anything from them. And last year they only allowed people to attend it online. Were only the presenters, so I couldn't even watch it. I did find it later and watched a few of them, but I was kind of mad that I couldn't watch it live like everybody else did. But if they have it in Denver, I'll go again this year. But I mean, not this year. Yeah, this year. I mean, in September.
That would be a great one to go to. That would help us.
Watch out for that Eskridge girl. She tries to say everything that comes out of your mouth belongs to her.
No trash talking. No trash talking, Mark.
Well, I invited her there last time. I'm not inviting her again.
Yeah, I'd fly out to Estes Park. If they could do it in the winter, I'd get some skiing in. That'd be cool.
It's usually right before the winter skiing season, I think, because there's usually no snow around the park. Maybe some higher up, I guess.
Do people in our area ski? I don't think anyone. I don't think that's a hobby for.
Jeremy says he skis. I've skied for years. I'm actually I'm done here tonight. I can't get the wires in for to get the test set up. I need to wait for my assistant Tom. There's just not enough space, and you need an extra pair of hands to set it up. So we're not going to get any live experiments. So,
no, that's cool. That's cool. Well, we can keep doing open discussion. Mark, if you want, I could make you the host. If you want to hang around.
Sure, yeah. If you guys want to watch, I'm working on a paramotor right now. Actually.
Okay. Yeah. Well, here I will. Hang on. I'll make you the host then.
Oops.
And if any of you guys live in Huntsville, I need a lab assistant down here.
You need one too, don't you?
I will be back in a while then, but I think today's conference went pretty well. Mark, we remember you had asked why because I was bugging you at 4 for your update. So all of our guests today went a little short, which is totally cool. And then we started 2 hours early, right? Because of Dr. Pinto's, he's in Turkey, so his time zone is just way too far ahead.
Mm-hmm.
So, and Tony knows him from Safe. Tony, you probably remember.
Yeah,
the
that's like, what, 30 years ago? It was a long time.
Yeah.
I'm
I was
having
working for JPL when we knew him.
Yeah, I think it went pretty well today.
Yeah, I'm excited, and we have some good guests coming up for the 26th also. So,
I can't get my video started for some
I think John Hutchison may be with us on the 26th. John's a free spirit, so.
Tim, 1 second. Can I make you a host for a second? I need to log back in.
Yeah, go for it, man.
Much love, guys. I'm sign out. I'll see you again in a week's time.
Okay, thanks again, Bernie. Have a great evening.
You
I'm
too.
going to sign out too because I got a train before 9 o'clock, so only have half an hour left. All right, take it easy, guys.
Should we shut things down then for the night, or?
Before we have to shut out, Glenn.
Yeah.
I just read the abstract and the first introduction in your paper, The Death of Rocketry. My question for you is the thesis of that paper, which I'm going to read completely several times, is based on all your years of experience working at NASA, the change, how it was or what it is, is that what the thesis is based on, your entire experience of late, or the entire career, or just a comparison between beginning and now for the present time?
It's my experience of NASA while I was working for NASA. I hired on after the Germans were actually gone. There were a few guys left, but not many. And they were mostly analysts instead of regular engineers. But from my perspective of listening from everybody in the history of NASA, once the Germans were gone, the real basic science for rocketry went away with them. And engineers began being the main people who were doing management all the way up to headquarters, except every now and then they'd throw a OPM guy who was a budget analyst in as a NASA headquarters guy. But basically, engineers run NASA today, not scientists. Okay. And the engineering programs that they do are very, very expensive. So the engineers want the money to go into their program, not into doing basic science. And I think that's a wrong approach. I think the president's list is what I'm saying. I think the United States needs to develop a national science foundation, just like the one they have, whose sole mission is to look at propulsion and change the way we do propulsion today. The pyramid for propulsion today is that the rocket engine sits on the payload sits on the top of the pyramid, and everything else is your rocket. We need to get technology that flips that around, where what's at the bottom is the engine, and everything else on the pyramid is what you're taking to space, because it's just too daggum expensive with the technology we have today to put stuff in space. It's actually more cost effective to put factories on the moon and build everything we were putting in space and send it to space than it is to build it on the Earth.
Yeah.
Yes.
Oh, Mark, are you back?
Good thesis.
Let me see.
I am back, yes.
Do you want me to make you host again?
Oh, sure.
Okay.
I'll take over the reins.
Okay. Yeah, thank you. I'm going to step away. And yeah, I would say just keep going as long as you want, guys. We're definitely in open discussion territory now. I think today's conference went pretty well. I'm excited. We had fresh faces, new ideas, and we're going to keep doing that in the new year.
I hope to have a live experiment for next time, or at least an update of what's going on with the Alpha. We ran a couple of experiments. I would send the link out to the WhatsApp group whenever it's ready, and people just didn't show up, so we started just doing it private.
Yeah.
But yeah, it's there's always a snag with these experiments. Right now, it's just getting everything wired up properly, and I can't do it with just two hands.
No, that makes sense. Makes sense.
Like getting fishing line going through several different holes simultaneously.
Okay. Well, it has been good. I will pop back in a bit. Okay.
How's everything going in Huntsville, Tony? Actually, you're not in Huntsville. You're in Tennessee, right?
No, I'm in Madison, which is right outside of Huntsville. But really, Madison is Huntsville. It's just, in fact, I could probably throw rocks at 3 different townships from where my house is. And, Huntsville, Madison, and Harvest out here.
Have you tried?
No, but I've lived in the 3 different zip codes that's real close by here since I've been here, and they're all within half a mile of each other. So it's just funny. But I think the Madison should be part of Huntsville. They don't want to be, but it's growing out here. But we'll see.
I'm doing some winter maintenance on my power motor right now. See that behind me? Yeah, I'm wondering why you had it sitting there behind you. That doesn't have anything to do with what you're doing. Oh, except that you fly. Yeah, you need to put some ion engines on it or something. At least make it look funky. Yeah, well, I don't know about ion engines, but that puppy puts out 23 horsepower and it only weighs 60 pounds. Yeah. It can lift itself plus another 70 pounds if it's going up vertical. Yeah, there's as long as you got a fluid medium, as long as you've got a medium that has high density, you can get some good thrust out of it. So when you get into an environment that doesn't have any density, like space, is where you have a problem. And then you have just the density of space-time, which ain't too dense. It's the there's a terminology for the density of space. I forget what it is right now. It's in my paper. Mu and epsilon. No, I mean permittivity and permeability. It's permittivity and permeability. That just has to do with the speed of light. You multiply those together, or take the square root of multiplying each speed of light. There's a term for the density of space. I guess you can't remember what it is right now. It's in my last paper I did. You file any new patents recently? I'm actually writing one right now. I actually submitted 2 last year. I need somebody to come over here and write a bunch more for me. What good do they do you?
Put the patents in the chat.
I haven't made a dime off of none of them. I think that was Lulu. What'd she say? I'll put the link in the chat. What link? I don't know.
The patents in the chat.
If you go look for me on.
I had it on unmute. I was thinking things like, how are you hearing my voice when I have like the visual and the audio off, but you can hear me. That's cool. That's cool. All right, let's do it again. Let's play this experiment again. Hold on.
Go look me up. In the chat. Go look for me on. That's Kate. Who's Kate? Go look for me on ResearchGate, and you'll find all my patents.
Awesome. Thank you.
Thank you. Listen, I just want to go. I'm just building my, to your center. I know, but just,
I'm so immersed in this that like I'm learning so much more than like I feel like going and in person, like I don't know, feeling weird, but I'll
But the 2 patents I put in last year, they're supposed to publish one of them at the end of next year, and if they do, I'll come on and talk about it because it's related to the those tic-tacs propulsion.
I'm all about the tic-tac.
Yeah, I'm not 100% sure I believe in it, but
Kate,
I
can
can't
you pull on the
believe you're
camera?
right near Huntsville and you don't believe in it.
I don't believe that they're from outer space, let's put it that way. I think they're probably U.S. In fact, my opinion, they have a lot of, the way they behave is a lot like some of the technology I've seen over my career, most of which I can't talk about.
Well, there's ours and then there's theirs.
On the belief aspect, I think it's better that you be skeptical because that means that you're going to be asking the right questions to verify if something is legitimate or not. If you believe in it, you tend to not ask the right questions because you just don't want to eliminate something that you believe in,
Well, I'm a physicist, and a good physicist will criticize his own work. If you think what you're doing is the greatest thing in the world, then you're probably wrong. Did you
used to work for Skunk Works? Is that why?
No, I have my own lab in my in my new house space garage here.
That's interesting. That actually concept of operation for science seemed to be the best way to operate for any kind of like art or anything else too. Thus, the best artists tend to be also the biggest critics of their own work.
If you can't criticize your own work, then you're probably not doing something right. Because what happens is you get so focused on what you're doing, you think that what you're doing is the greatest thing in the world, and you're missing something because you're not looking at other things.
You got to be an outsider looking in. What they're looking for is people that can think, an outside observer.
Yeah, when I write a paper, I'll write it and then set it down for a few weeks and then come back to it. And I generally end up rewriting half of it when I do that. It's because you get too focused. You have to write your paper as if you're not the person who did the work. Otherwise, you write it wrong.
And the natural course of events is you always get it wrong the first time.
Hey, Mark, it's the quantum energy density once you get into space. That's what I was trying to come up with. That's what you got to act on in space.
Quantum energy density. Yeah, I think that's what they were talking about with the Casimir effect. Turning on a light increases its strength. You're also increasing the quantum vacuum energy.
Yeah.
So while the quantum vacuum energy is not a constant, that will change as you enter solar systems and the nebula and stuff. Space weather is a real thing.
Yeah. Well, based on the model I put together, it's not the quantum energy that you're operating on, it's the quantum density. But you have to use energy to manipulate the density.
Glenn, have you ever heard of a game called Elite Dangerous?
No.
It's a space simulator. You're flying around a flying saucer or spacecraft kind of thing, and you can do missions and shit and whatever, but they also have space weather, and if you get too close to like the rays that are coming out of a quasar or something like that, your ship blows up.
I don't play games. Back a long time ago when Zelda first came out, I I started to play it and I realized, I said, you know, if I start playing games like this, you'll find me dead at the computer someday playing games.
Yeah, I totally agree. I just, oh, here, somebody wrote
I agree with that
in the
too.
80s.
I'd rather make things than play games. We have limited time on this planet, so.
They're like reiterating my voice. This is so cool. Like, this is cool.
No, Lulu, that's not your voice. That's a girl named Kate. That's not your voice. It's not an alternate reality. That's somebody named Kate.
No, I am from an alternate reality, but, you know, if Lulu wants me to be her voice, I can be her alternate reality voice. Why not? I mean, this is the right group of people for this.
Raise the oscillator, the frequency on a different, you know, like, you know.
Oh my God.
Listen, I'm not going to argue you, not one bit. You know, play with it all you want, but the truth is the truth.
Right, exactly. The truth is the truth.
That's crazy.
Yeah, no, I wasn't like trying to sell the video game, but just saying that, you know, it just came to mind. And what you guys said is 100% true. Video games are a waste of time. But I found that one particularly addictive. I had to like delete it off the computer because it reminded me of, you know, the flying saucers and all that shit we're trying to build.
My grandson plays the video games and he stays up late, can't get him up for school, and all this other stuff. It's just not worth it. It's just too much of a problem. Although they probably would make a good
Some of them are violent.
Oh.
Some of them are really bad, like Grand Theft Auto 5. Oh my God, that shit should be banned. Like all the.
Well, it's actually getting